Hey, David here. Welcome. We're live back for another Science of Philosophy stream. A lot of good material this week. Uh, 8 out of 10. So, rounding the corner, this number 8 will probably finish the majority of like the heavy lifting, the major topics in philosophy of science. And then the next 2 weeks, I will read topics and related issues. And then hopefully go on to metaphysics. It's just such a huge topic, important topic, a lot of research. And hopefully from there, I will then start to make some significant advances in my coming out with my multiple truth hypothesis. I have put a lot of thought together, and you just wanted to do the due diligence to a large analysis into this important topic. And the topic interests me in general, as I mentioned in the introduction. Almost all of these streams, the philosophy of science is not a well understood topic. It's not well researched. There's very few departments, places to study. There's a few famous ideas and books, like Thomas Kuhn on the structure of scientific revolutions, or Karl Popper. Besides that, most of the names are not even well known. So, I covered in the first half of the series the Vienna Circle, the Neo-Kantianism, and the history. Ernst Mach and the founding of the Vienna school appointment, and then the Vienna Circle of Franz Schlicht, and the diaspora of the Vienna Circle, mostly to America. That the handful of places in the U.S. that have departments of philosophy of science are largely because people from the Vienna Circle ended up there from after World War II. Big names like Hempel and Carnap and many others. And as we talked, we'll get back to metaphysics, but almost everything in science philosophically is disputed. It's unclear. All these questions of the meaning, how do we know things, how do we understand things, how do we put things together, what does it mean? There's multiple theories, multiple schools, and even the attempt to have such a concept as universal laws with mathematical equations has largely failed, except in physics. And even in physics, it's largely failed, and there's a lot of questions. So last week we talked about mechanisms in science, and the week before we talked about a reduction. And these are important philosophical concepts. How do we understand theories? Do theories reduce to each other? Are there laws that can be derived from each other? And what's the difference between a mechanism? I read the ceteris paribus laws, where you have laws that are not universal, that hold in all things being equal, the ceteris paribus laws, but relatively scientific laws that are not universal. They only hold in standard cases, some cases, but outside of those standard cases, that they don't hold. And so that's one of the things we covered last week. So there's a lot of reading this week. As I said, this week will be the end of like the heavy lifting. I've covered almost all of the major topics in the philosophy of science. Philosophy of science is a huge topic. So, God forbid, just reading through these, every single one of these small subtopics is another thing to read through, and becomes more specialized. A lot of times there's single names. So in the olden days, you saw certain names like Hempel and Carnap that thought about a whole bunch of things, and then other names of people that had researched or thought about a whole a section of issues, to modern day where you kind of have just one or two thinkers. So in Week in Review, I read an article from talking about inevitabilism and contingency in Ian Hacking in his Mangle of Science. And one of the first episodes, I talked about the historicity of science, which has similar to this inevitabilism versus contingency, where this concept of truth, is there some truth out there, and the more research and the more minds are put into it, it's inevitable we're going to discover the truth, or is it contingent upon um, um, is it contingent upon uh, certain factors? And then like the role of mathematics, we're going to go more into mathematics today. Talked about the Quine-Putnam hypothesis and contingentism, where science is contingent upon math, because almost all scientific theories use mathematics. So then also you have mechanisms, and how do you formulate mechanisms, logic. We talked about models in science and various things. Hey, Mr. Boston Shalom, thanks for tuning in. Thanks for joining the Discord. And beyond this, like I'm going to end after series 10, and I'm only going somewhat in minor detail into the logical formulation. But past this, it's almost completely based on logic, mathematics, set theory, model theory, various aspect of um, um, what would be part of, say, mathematical logic. So when you do say, well, scientific theories are logic, can you reduce them to logical format? Last week we talked a little bit about Ramsey sentences and Carnap sentences, and um, even theories of models, where models of science are contain various things. They contain uh, differential equations, but they also contain sentences, descriptions, definitions, and how much of those could be reduced to pure logical notation. We talked about theoretical terms in science. Are the theoretical terms in science the same or different? And even concepts like the electron. Does the electron in physics and chemistry mean the same thing, or biology, which is related to reduction? So today, you'll start the screen share. So today, a lot of reading, probably be like 6 hours. Yeah, Mr. Boston, we're going to look at mathematical explanation, which we'll talk a little bit about Pythagorean. Um, so today I have scientific explanation, mathematical explanation, computer simulations in science, the incommensurability of scientific theories, and scientific objectivity. So if anyone wants to follow along, let me post these links. And so, yeah, for my own research base, like this is very useful because I don't really have too many people to talk about this stuff with. So one is the like a learning technique, a memory technique, just to say these words coming out of my own mouth to um, as the words leave my mouth, it makes me more comfortable using the words, understand the concept. Like if you learned this in university, you'd be readings in a discussion group. So I've read through quite a bit of the original source material, and I'm probably going to take a week off next week because I want to catch up on some of my reading. We'll see. I have 9 more that I've pulled out. I want to talk a little bit about your mind brain operationalism, experiments, the Copenhagen interpretation, quantum theory, and mathematical rigor. And then the last week, I'll probably cover related topics like the philosophy of architecture, statistics and history, and computational philosophy. And so, people want to see the series up to now. You can see the series up to date right now. So this is part 8. And last week we covered analysis of so since I restarted the series back up, this is the third time. Last week we covered models in science, realism and theory change in science, theoretical terms in science, ceteris paribus laws, mechanisms in science, and the week before covered indispensability arguments in the philosophy of mathematics, scientific reduction, measurement in space, philosophy of neuroscience, and reductionism in biology. So with that, let's jump right in. We'll start with scientific explanation. All of these are long. All of these are in-depth. This one's probably the most complicated of them. Scientific explanation, which might cover one of the single most important things, the deductive nomological model, going back to Hempel. And there's some dispute over the expectation, but to some extent, this is one of the single most important things. Like we talked about models, but this is the most widely accepted current model, the deductive nomological model of scientific explanation. What does science actually explain? And then also you have statistical, inductive statistical models, or various things. And this will lead to your topic I'll cover, but probably not in this stream, which would be more mathematical model theory and reducing these concepts more to straight mathematical logic. Okay, so let's jump right in. Got a handful of people here, so hopefully this is beneficial to you. So let's jump right in. Scientific explanation. Issues concerning scientific explanation have been a focus of philosophical attention from pre-Socratic times through the modern period. However, modern discussion really begins with the development of the deductive nomological model. This model has had many advocates, including Popper, 1959, Braithwaite, 1953, Gardner, and Nagel. But unquestionably, the most detailed and influential statement is due to Carl Hempel. These papers and the reaction to them have structured subsequent discussions concerning scientific explanation to an extraordinary degree. After some general remarks by the way of background and orientation, this entry describes the deductive nomological model and its extensions, and then turns to some well-known objections. It next describes a variety of subsequent attempts to develop an alternative model of explanation, including Wesley Solomon's statistical relevance and causal mechanical models, unificationist models due to Michael Friedman and Philip Kitcher, and pragmatic theories found in the work of Van Frassen. And it also provides a summary and discusses the direction for future work. This article thus discusses treatments of scientific explanation up to the end of the 20th century. Background and introduction. As will become apparent, and so sorry to mention this before, red is for title headers, purple and green are for key terms. Usually purple is more key or general than the green. Gray is for numbers, lists. Orange is for names, dates, and titles of papers or books. And yellow is for examples. As will become apparent, scientific explanation is a topic that raises a number of interrelated issues. Some background orientation will be useful before turning to the details of competing models. A presupposition of most recent discussion has been that science sometimes provides explanations rather than something falls short of explanation, mere description, and that the task of a theory or model or scientific explanation is to characterize the structure of such explanations. It is thus assumed that there is some suitably abstract and general level of description, a single kind or form of explanation that is scientific. In fact, the notion of scientific explanation suggests at least two contrasts. First, a contrast between those explanations that are characteristic of science and those explanations that are not, and second, a contrast between explanation and something else. However, with respect to the first contrast, much of the recent philosophical literature assumes that there is substantial continuity between explanations found in science and some forms of explanation found in ordinary non-scientific contexts. It is further assumed that it is the task of a theory of explanation to capture what is common to both scientific and some ordinary non-scientific forms of explanation. These assumptions help to explain what may otherwise strike the reader as curious. Why, as this entry will illustrate, discussions of scientific explanation often move back and forth between examples drawn from bona fide science and more homey examples. With respect to the second contrast, most models of explanation assume that it is possible for a set of claims to be true, accurate, supported by evidence, and so on, and yet unexplanatory. Instead, such an account is merely descriptive. However, different models of explanation provide different accounts of what the contrast between the explanatory and the mere descriptive consists in. A related point is that while most theorists of scientific explanation have proposed models that are intended to cover at least some cases of explanation that we would not think of as part of science, they have nonetheless assumed some implicit restriction on the kinds of explanation they have sought to reconstruct. It has often been noted that the word explanation is used in a wide variety of ways in ordinary English. We speak of explaining the meaning of the word, explaining how to bake a pie, explaining why one made a certain decision, where this is to offer justification, and so on. Although the various models discussed below have sometimes been criticized for their failure to capture all of these forms of explanation, it is clear that they were never intended to do this. Instead, their intended explicandum is very roughly explanation of why things happen, where the things in question can be either particular events or something more general, regularities or repeatable patterns in nature. Finally, a few words on the broader epistemological and methodological background to the models described below. Many philosophers think of concepts like explanation, law, cause, and support for counterfactuals as part of the interrelated family of concepts that are modal in character. For familiar empiricist reasons, Hempel and many other early defenders of the deductive nomenological model regarded these concepts as not well understood, at least prior to analysis. It was assumed that it would be circular to explain one concept from this family in terms of others from the same family, and that they must instead be explicated in terms of other concepts from outside of the modal family, concepts that more obviously satisfied what were taken to be empiricist standards of intelligibility and testability. For example, in Hempel's version of the deductive nomological model, the notion of a law plays a key role in explicating the concept of explanation, and his assumption is that laws are just regularities that meet certain further conditions that are also acceptable to empiricists. As we shall see, these empiricist standards and an accompanying unwillingness to employ modal concepts as primitives have continued to play a central role in the models of explanation developed subsequent to the deductive nomological model. A standard issue has to do with whether all scientific explanations are causal, and if not, what distinguishes causal from non-causal explanations. Hempel recognized both causal and non-causal forms of explanation, but held that both were captured by the deductive nomological model. In his view, causal explanations are simply deductive nomological explanations that cite causal laws, which he regarded as a proper subset of all laws. Many, but not all, of the accounts discussed below, in effect, assume that many of the problems with deductive nomological model can be traced to its commitment to an inadequate account of causation, thus that getting clearer about causal notions would lead to more adequate accounts of explanation. By contrast, a substantial amount of recent discussions of explanation has moved away from this focus of causation and instead explores the possibility of non-causal forms of explanation. The deductive nomological model, the basic idea. According to the deductive nomological model, a scientific explanation consists of two major constituents of an explanandum, which is a sentence describing the phenomenon to be explained, and the explanums, the class of those sentences which are adduced to account for the phenomenon. For the first explanums to successfully explain the explanandum, several conditions must be met. First, the explanandum must be a logical sequence of the explanums, and the sentences constituting the explanums must be true. That is, the explanation should take the form of a sound deductive argument in which the explanandum follows as a conclusion from the premise of the explanums. This is the deductive component of the model. Second, the explanums must contain at least one law of nature, and this must be an essential premise. In the derivation, in the sense that the derivation of the explanandum would not be valid if this premise were removed. This is the nomological component of the model. Nomological being a philosophical term of art which, suppressing some niceties, means roughly lawful. It is In its most general form, the deductive nomological model is meant to apply both to the explanation of general regularities or laws, such as why light conforms to the law of refraction, and also to the explanation of particular events conceived as occurring at a particular time and place, such as the bent appearance of the primary submerged oars of a rowboat on a particular occasion of viewing. The role of laws in the deductive nomological model. The notion of sound deductive argument is arguably relatively clear, or at least something that can be regarded as antecedently understood from the point of view of characterizing scientific explanation. But what about the other major component of the deductive nomological model, that of the law of nature? The basic intuition that guides the deductive nomological model goes something like this. Within the class of true generalizations, we may distinguish those between those that are only accidentally true and those that are laws. What exactly is it that distinguishes true accidental generalizations from laws? This has been the subject of a great deal of philosophical discussion, most of which must be beyond the scope of this entry. Hempel assumes that an adequate account must explain the notion of laws in terms of notions that lie outside of the modal family. He considers a number of familiar proposals having this character and finds them all wanting, remarking that the problem of characterizing the notion of law has proved highly recalcitrant. It seems fair to say, however, that his underlying assumption is that at bottom, laws are just exceptionless generalizations describing regularities that meet certain additional distinguishing conditions that he is not at present able to formulate. In subsequent decades, a variety of criteria for lawhood have been proposed. One of these so-called best systems analysis is probably the most popular, but no single account has won general acceptance. Finding an adequate characterization of lawhood is thus an ongoing issue for the deductive nomological model. One point at which this issue is particularly pressing concerns the explanatory status of the so-called special sciences, biology, psychology, economics, and so on. These sciences are full of generalizations that appear to play an explanatory role and yet fail to satisfy many of the standard criteria for lawfulness. There is considerable disagreement over whether such generalizations are laws. Some philosophers suggest that the generalizations satisfy too few of the standard criteria to count as laws, but can nevertheless figure in explanations. If so, it apparently follows that we must abandon the deductive nomological requirement that all explanations must appeal to laws. Others, emphasizing different criteria for lawfulness, conclude instead that generalizations are laws and hence no threat to the requirement that explanations must invoke laws. In the absence of a more principled account of laws, it is hard to evaluate these competing claims and hence hard to assess the implications of the deductive nomological model for the special sciences. At the very least, providing such an account is an important item of unfinished business for advocates of the deductive nomological model. Inductive statistical explanation. The deductive nomological model is meant to capture explanation via deduction from deterministic laws, and this raises the obvious question of explanatory status of statistical laws. Do such laws explain at all, and if so, what do they explain, and under what conditions? Hempel distinguishes two varieties of statistical explanation. The first of these, deductive statistical explanation, involves the deduction of a narrow statistical uniformity from a more general set of premises, at least one of which involves a more general statistical law. Since deductive statistical explanation involves the deduction of the explanandum from the law, it conforms to the same general pattern as the deductive nomological explanation of regularities. However, in addition to the deductive statistical explanation, Hempel also recognizes a distinct sort of statistical explanation, which he calls the inductive statistical explanation, involving the assumption of individual events under what he regards statistical laws. While the explanandum of a deductive nomological or deductive statistical explanation can be deduced from the explanums, one cannot deduce that some particular individual, as most of what could be deduced from this information is that recovery is more or less probable. The inductive statistical explanation, the relationship between explanums and explanandum, in Hempel's words, inductive rather than deductive, hence the name inductive statistical explanation. The details of Hempel's account are complex, but the underlying idea is roughly this. The inductive statistical explanation will be good or successful to the extent that it confers high probability on its explanandum outcome. Motivation for the deductive nomological model, gnomic expectability, and irregularity account of causation. Why suppose that all or even some explanations have a deductive nomological or inductive statistical structure? There are two ideas which play a central role in Hempel's discussion. The first connects the information provided by the deductive nomological argument with a certain conception of what it is to achieve understanding of why something happens. It appeals to an idea about the object or point of giving an explanation. Hempel writes, a deductive nomological explanation answers the question, why did the explanandum phenomenon occur? By showing that the phenomenon resulted from a certain particular circumstances specified in accordance with the laws. By pointing this out, the argument shows that given the particular circumstances and the laws in question, the occurrence of the phenomenon was to be expected, and it is in this sense that the explanation enables us to understand why the phenomenon occurred. One can think of the inductive statistical explanation as involving a natural generalization of this idea. While an inductive statistical explanation does not show that the explanandum phenomenon was to be expected with certainty, it does the next best thing. It shows that the explanandum phenomenon is at least to be expected with high probability, and in this way provides understanding. Stated more generally, the deductive nomological and inductive statistical models share the common idea that, as Salmon 1989 put it, the essence of scientific explanation can be described as gnomic expectability, that is, expectability on the basis of lawful connections. The second main motivation for the deductive nomological inductive statistical models has to do with the role of causal claims in scientific explanation. There is considerable disagreement among philosophers about whether all explanations in science and in ordinary life are causal, and also disagreement about what the distinction, if any, between causal and non-causal explanations consist in. Nevertheless, virtually everyone, including Hempel, agrees that many scientific explanations cite information about causes. However, Hempel, along with most other early advocates of the deductive nomological model, is unwilling to take the notion of causation as primitive in the theory of explanation. That is, he is unwilling to simply say that X figures in the explanation of y if and only if X causes y. Instead, adherents of the deductive nomological model have generally looked for an account of causation that satisfies the empiricist requirements. In particular, advocates of the deductive nomological model have generally accepted a broadly Humean or regularity theory of causation, according to which very roughly all causal claims imply the existence of some corresponding regularity, a law linking cause to effect. This is then taken to show that all causal explanations imply, perhaps only implicitly, that such a law regularity exists, and hence that laws are involved in all such explanations, just as the deductive nomological model claims. So-called singular causal explanation, advanced by Michael Scriven, 1962, is a counterexample to the claim that the deductive nomological model described necessary conditions for successful explanation. Hempel's response is that the occurrence of caused should not be left unanalyzed or taken as explanatory just as it stands. Instead, should be understood as implicitly or tacitly claiming there is a law or regularity. According to Hempel, it is the implicit claim that some such law holds that distinguishes from a mere sequential narrative, but without any claim of causal connection, a narrative that Hempel thinks would clearly not be explanatory. This linking law is the nomological premise in the deductive nomological argument that, according to Hempel, is implicitly inserted. The basic idea is thus that a proper explication of the role of causal claims in explanation leads via a Humean or regularity theory of causation to the conclusion that, at least ideally, explanations should satisfy the deductive nomological inductive statistical model. Let us call this line of argument the hidden structure argument in recognition of the role it assigns to a hidden or at least non-explicit deductive nomological structure that is claimed to be associated with. At this point, a comment is in order regarding a feature of this proposal that may seem puzzling. The boundaries of the category scientific explanation are far from clear, but well, arguably an explanation, it is not what one usually thinks of as science. Instead, it is a claim from ordinary life or common sense. This raises the question of why adherents of the deductive nomological Inductive statistical model don't simply respond to the alleged counterexample by denying that it is an instance of the category scientific explanation. That is, by claiming that the deductive nomological inductive statistical model is not an attempt to reconstruct the structure of explanations, but is rather only meant to apply to explanations that are properly regarded as scientific. The fact that this response is not often adopted by advocates of the deductive nomological model is an indication of the extent to which it is implicitly assumed in most discussions of scientific explanation that there are important similarities or continuities in structure between explanations and explanations that are more obviously scientific, and that these similarities that should be captured by some common account that applies to both. Indeed, it is a striking feature not just of Hempel, but of many other treatments of scientific explanation that much of the discussion in fact focuses on ordinary life, singular causal explanations similar. The tacit assumption being that conclusions about the structure of such explanations have fairly direct implications for understanding explanation in science. I've noted that the parts that I don't read is not highlighted are either examples or overly technical. So people could look at that on their own if they want to see the examples or the overly technical parts beyond uh, the scope of what I could do here. Explanatory understanding and nomic expectability, counterexamples to sufficiency. As explained above, potential counterexamples to the claim that the deductive nomological model provides necessary conditions for explanation. There are also a number of well-known counterexamples to the claim that the deductive nomological model provides sufficient conditions for successful scientific explanation. Here are two illustrations. Explanatory asymmetries. There are many cases in which a derivation of an explanandum from a law and initial conditions seems explanatory, but a backward derivation of initial conditions from the explanandum and the same law does not seem explanatory, even though the latter, like the former, appears to meet the criteria for successful deductive nomological explanation. Explanatory irrelevancies. A derivation can satisfy the deductive nomological criteria and yet be a defective explanation because it contains irrelevancies besides those associated with the directional features of explanation. The regularity account of causation favored by deductive nomological theorists is at best incomplete. The occurrence of causes and effects and the existence of some regularity or law linking them, or X having property P and X having property Q, and some law linking these, is not sufficient condition for the truth of the claim that the cause or X having property P is causally or explanatory relevant to X having property Q. It follows that the deductive nomological model fails to state sufficient conditions for explanation. Explaining outcome isn't just a matter of showing that it is nomically expectable. There are two possible reactions that one might have to this observation. One is that the idea that explanation is a matter of nomic expectability is correct as far as it goes, but that something more is required as well. According to the assessment, the deductive nomological inductive statistical model does state a necessary condition for successful explanation, and moreover, a condition that is non-redundant part of a set of conditions that are jointly sufficient for explanation. However, some other independent feature X, which will account for the directional features of explanation and ensure the kind of explanatory relevance that is apparently missing, must be added to the deductive nomological model to achieve a successful account of explanation. The idea is that nomic expectability plus X equals explanation. Something like this idea is endorsed by the unificationist models of explanation developed by Friedman 1974 and Kitcher in 1989. A second, more radical possible conclusion is the deductive nomological account of the goal of rationale of explanation is mistaken in some much more fundamental way than the deductive nomological model does not even state necessary conditions for successful explanation. As noted above, unless the hidden structure argument is accepted, this conclusion is strongly suggested by examples which appear to involve explanation without the explicit citing of a law or deductive structure. The statistical relevance model. The basic idea. Much of the subsequent literature on explanation has been motivated by attempts to capture the features of causal or explanatory relevance that appear to be left out of examples seen in the deductive nomological model, typically within the empiricist constraints described above. Wesley Salmon's statistical relevance model is a very influential attempt to capture these features in terms of the notion of statistical relevance or conditional dependence relationships. Given some class or a population A, an attribute C will be statistically relevant to another attribute B if and only if, that is, if and only if the probability of B conditional on A and C is different from the probability of B conditional on A alone. The intuition underlying the statistical relevance model is that statistically relevant properties or information about statistically relevant relations are explanatory and statistically irrelevant properties are not. In other words, the notion of a property making a difference for an explanandum is unpacked in terms of the statistical relevance relationship. To characterize the statistical relevance model more precisely, we need the notion of homogeneous partition. A homogeneous partition of A is a set of subclass or cell C of A that are mutually exclusive and exhaustive. The statistical relevance model and low probability events. The statistical relevance model has a number of distinctive features that have generated substantial discussion. First, note that according to the statistical relevance model, and in contrast to the deductive nomological inductive statistical model, an explanation is not an argument, either in the sense of deductively valid argument in which the explanandum follows as a conclusion from the explanums, or in the sense of a so-called inductive argument in which the explanandum follows with a high probability from the explanums, as in the case of the inductive statistical explanation. Instead, an explanation is an assembly of information that is statistically relevant to the explanandum. Salmon argues that the criteria that a good argument must satisfy, criteria that ensure deductive soundness or some inductive analog, are simply different from those a good explanation must satisfy. Among other things, as Salmon puts it, irrelevancies are harmless in arguments but fatal in explanations, as explained above. In associating successful explanation with the provision of information about statistical relevance relationships, the statistical relevance model attempts to accommodate this observation. A second closely related point is that the statistical relevance model departs from the inductive statistical model in abandoning the idea that statistical explanation of an outcome must provide information from which it follows that the outcome occurred with high probability. As the reader may check, the statement of the statistical relevance model above imposes no such high probability requirement. Instead, even very unlikely outcomes will be explained as long as the criteria for statistical relevance explanation are met. More generally, what matters on the statistical relevance model is not whether the value of the probability of the explanandum outcome is high or low, or even high or low in comparison with its prior probability, but rather whether the putative explanandum cites all the and only statistically relevant factors, and whether the probabilities it invokes are correct. One consequence of this, which Salmon endorses, while acknowledging that many will regard it as unintuitive, is that on the statistical relevance model, the same explanums may explain both an explanandum and explananda that are inconsistent. This judgment that, contrary to the inductive statistical model, the value that a candidate explanandum assigns to an explanandum outcome should not matter for the goodness of the explanation is motivated as follows. When an outcome is the result of a generally indeterministic process, we understand both high probability and low probability outcomes, the latter of which, of course, will sometimes occur equally well. In both cases, once a statistical relevance model has been constructed, there are no additional factors that distinguish the two outcomes. What do statistical theories explain? What sorts of examples are accounts of statistical explanation intended to capture? Stepping back from the issues such as the status of the high probability requirement that have dominated discussions of statistical explanation, there are several more general issues that deserve mention. One is that these models have been applied to a range of examples that seem prima facie to be quite different. The models themselves are very far from satisfying an objective homogeneity requirement. Indeed, taken literally, standard causal models assume the opposite. The assumed equations are deterministic with the stochastic elements supplied by an error term. This raises the question of whether it is sensible to look for a single model that captures all of these explanations. A second, more radical assessment focuses on the question of whether it is appropriate to think of the sorts of statistical theories and hypotheses of which Hempel and Salmon discuss as explaining individual events or outcomes at all. This raises the question of what additional work is accomplished by models of statistical explanation of either the inductive statistical or statistical relevance sort. Causation and statistical relevance relationships. Putting aside the issues raised in the previous section, the statistical relevance model embodies several generic assumptions of ongoing philosophical interest. In particular, the model assumes that explanations must cite causal relationships and that causal relationships are fully captured by statistical relevance or conditional dependence and independence relationships. Well, the first is a matter of current controversy, the second is clearly false, as a substantial body of work has made clear causal relationships are generally undetermined by statistical relevance. A relationship, even given additional assumptions. For example, the structure in which B is a common cause of the joint effects A and C implies assuming the causal Markov assumption, which is the appropriate generalization of Selman's assumptions connecting causation and probability, implies the same statistical relevance relations as a change structure in which A causes B, which causes C. The causal mechanical model, the basic idea. In more recent work, Salmon abandoned the attempt to characterize explanation or causal relationships in purely statistical terms. Instead, he developed a new account which he called the causal mechanical model of explanation, an account which is similar in both content and spirit to the so-called causal process theory of causation of the sort defended by philosophers like Philip Dow, 2000. We may think of the causal mechanical model as an attempt to capture the something more involved in causal and explanatory relationships over and above facts about statistical relevance. Again, while attempting to remain within a broadly Humean framework, the causal mechanical model employs several central ideas. A causal process is a physical process. This is characterized by the ability to transmit a mark in a continuous way. Continuous generally, although perhaps not always, means spatio-temporal continuous. Intuitively, a mark is some local modification to the structure of a process. A process is capable of transmitting a mark if once the mark is introduced at one spatial temporal location, it will persist to the other spatial temporal locations, even in the absence of any further interaction. Causal processes contrast with pseudo processes which lack the ability to transmit marks. An example is the shadow of a moving physical object. The intuitive idea is that if we try to mark the shadow by modifying its shape at one point, for example, by altering a light source or introducing a second occluding object, this modification will not persist unless we continually intervene to maintain it as the shadow occupies successive spatial temporal positions. In other words, the modification will not be transmitted by the structure of the shadow itself, as it would in the case of the genuine causal process. We should note for future reference that, as characterized by Salmon, the ability to transmit a mark is clearly a counterfactual notion in several senses. To begin with, a process may be a causal process even if it does not in fact transmit any mark, as long as it is true that if it were appropriately marked, it would transmit the mark. Moreover, the notion of marking itself involves a counterfactual contrast, a contrast between how a process behaves when marked and how it would behave if left unmarked. Although Salmon, like Hempel has always been suspicious of counterfactuals, his view at the time that he first introduced the causal mechanical model was that counterfactuals involved in the general characterization of marked transmission were relatively unproblematic, in part because they seemed experimentally testable in a fairly direct way. Nonetheless, the reliance of the causal mechanical model, as originally formulated on counterfactuals, shows that it does not completely satisfy the Humean strictures described above. In subsequent work, Salmon attempted to construct a version of the causal mechanical model that completely avoids reliance on counterfactuals. The other major element in Salmon's model is the notion of causal interaction. A causal interaction involves a spatial temporal intersection between two causal processes which modify the structure of both. Each process comes to have features it would not have had in the absence of the interaction. A collision between two cars that dents both is a paradigmatic causal interaction. According to the causal mechanical model, an explanation of some event will trace the causal processes and interactions leading up to the event. Salmon calls this the etiological aspect of the explanation, or at least some portion of these, as well as describing the processes and interactions that make up the event itself, the constitutive aspect of explanation. In this way, the explanation shows how the event fits into a causal nexus. The causal mechanical model and explanatory relevance. The causal mechanical model takes it as its paradigm of causal interactions in which there is action by contact and no spatial temporal gaps in the transmission of causal influence. There's little doubt that explanations in which there are no such gaps, no action at a distance, often strike us as particularly satisfying. However, as Christopher Hitchcock shows in an illuminating paper, even here the causal mechanical model leaves out something important. Part of the difficulty is that to express such relatively fine-grained judgments of explanatory relevance, we need to talk about relationships between properties or magnitudes, and it is not clear how to express such judgments purely in terms of facts about causal processes and interactions. A more general way of putting the problem revealed by these examples is that those features of a process in virtue of which it qualifies as a causal process, the ability to transmit a mark, may not be the features of a process that are causally or explanatory relevant to the outcome that we want to explain. The mark may be irrelevant to the event, with some other property being the property which is causally relevant to the event. So while mark transmission may well be a criterion that correctly distinguishes between causal processes and pseudo processes, it does not, as it stands, provide the resources for distinguishing those features or properties of a causal process that are causally or explanatory relevant to an outcome and those features that are irrelevant. The causal mechanical model and complex systems. A second set of worries has to do with the application of the causal mechanical model to systems which depart in various respects from simple physical paradigms, such as the collision described above. There are a number of examples of such systems. First, there are theories like Newtonian gravitational theory, which involve action at a distance in a physically interesting sense. Second, there are a number of examples from the literature on causation that did not involve physically interesting forms of action at a distance, but which arguably involve causal interactions without intervening spatial temporal continuous processes or transfer of energy and momentum from cause to effect. These include cases of causation by omission and causation by double prevention or disconnection. In all these cases, a literal application of the causal mechanical model seems to yield the judgment that no explanation has been provided, that Newtonian gravitational theory is unexplanatory, and so on. Many philosophers have been reluctant to accept this assessment. Yet another class of examples that raise problems for the causal mechanical model involves putative explanations of the behavior of complex or higher level systems. Explanations that do not explicitly cite spatial temporal continuous causal processes involve transfer of energy and momentum, even though we may think of such processes are at work at a more underlying level. Most explanations in disciplines like biology, psychology, and economics fall under this description, as do a number of straightforwardly physical explanations. Just what does the causal mechanical model require in the case of complex systems in which we cannot trace individual causal processes, at least at a fine-grained level? How exactly does the causal mechanical model avoid the disastrous conclusion that any successful explanation of the behavior of the gas must trace to the trajectories of individual molecules? Does the statistical mechanical explanation described above successfully trace causal processes and interactions, or specify a causal mechanism in the sense that demanded by the causal mechanical model? And if so, what exactly does tracing causal processes and interactions involve or amount to a connection with such a system? A fully adequate development of the causal mechanical model needs to address such questions. More recent developments. In more recent work, prompted in part by a desire to avoid certain counterexamples advanced by Philip Kitcher in 1989 to his characterization of mark transmission, Salmon attempted to fashion a theory of causal explanation that completely avoids any appeal to counterfactuals. In this new theory, which is influenced by the conserved process theory of causation by Dow's 2000, Salmon defined a causal process as a process that transmits a non-zero amount of conserved quantity at each moment in its history. Conserved quantities are quantities so characterized in physics, linear momentum, angular momentum, change, charge, and so on. A causal interaction is an intersection of world lines associated with causal processes involving exchange of conserved quantity. Finally, a process transmits a conserved quantity from A to B if it possesses that quantity at every stage without any interaction that involve an exchange of the quantity in the half-open interval. One may doubt that this new theory really avoids reliance on counterfactuals, but an even more fundamental difficulty is that it still does not adequately deal with the problem of causal or explanatory relevance described above. That is, we still face the problem to the feature that makes a process causal. Transmission of some conserved quantity or other may tell us little about which features of the process are causally or explanatorily relevant to the outcome we want to explain. In cases which there appears to be no conservation laws governing the explanatory relevant property, cases in which the explanatory relevant variables are not conserved quantities, this difficulty seems even more acute. In a more recent paper, Salmon conceded this point. He argued that the notion of causal processes cannot by itself capture a notion of causal and explanatory relevance. He suggested, however, that this notion can be adequately captured by appealing to the notion of causal processes and information about statistical relevance relationship, that is, information about conditional or unconditional independence relationships, with the latter capturing the element of causal or explanatory dependence that was missing from his previous account. I would now say that statistical relevance relations, in the absence of information about connecting causal processes, lack explanatory import, and that connecting causal processes, in the absence of statistical relevance relations, also lack explanatory import. This suggestion is not developed in any detail in Salmon's paper. It is not easy to see how it can be made to work. We noted above that statistical relevance relationships often greatly underdetermine the causal relationship among a set of variables. What reason is there to suppose that appealing to the notion of a causal process in Salmon's sense will always, or even usually, remove this indeterminacy? We also noted that the notion of a causal process cannot capture fine-grained notions of relevance between properties, that there can be causal relevance between properties instances in which, at least at the level of description at which they are characterized, are not linked by spatial temporality, continuous or transference of conserved quantities, and that properties can be so linked without being causally relevant, as long as it is possible, and why should it not be, for different causal claims to imply the same fact about statistical relevance relationships, and for these claims to differ in ways that cannot be fully cashed out in terms of Salmon's notion of causal processes and interactions. This new proposal will fail as well. Hello, Wayne, God bless. Last Australian, good to see you. A unificationist account of explanation. The basic idea. In unificationist accounts of explanation, developed by philosophers, scientific explanation is a matter of providing a unified account of a range of different phenomena. This idea is unquestionably intuitively appealing. Successful unification may exhibit connections or relationships between phenomena previously thought to be unrelated, and this seems to be something that we expect good explanations to do. Moreover, theory unification has clearly played an important role in science. Paradigmatic examples include Newton's unification of terrestrial and celestial theories of motion, and Maxwell's unification of electricity and magnetism. The key question, however, is whether in which intuitive notions of unification can be made more precise in a way that allows us to recover the features that we think that good explanations should possess. Michael Friedman, 1974, is an important early attempt to do this. Friedman's formulation of the unificationist idea was subsequently shown to suffer from various technical problems like Kitcher, 1976, and subsequent development of the unification treatment of explanation has been most closely associated with Philip Kitcher. Let us begin by introducing some of Kitcher's technical vocabulary. A schematic sentence is a sentence in which some of the non-logical vocabulary has been replaced by dummy letters. Filling instructions are directions that specify how to fill in the dummy letters in schematic sentences. Schematic arguments are sequences of schematic sentences. Classifications describe which sentences and schematic arguments are premises and conclusions, and what rules of inference are used. An argument pattern is an ordered triple consisting of a schematic argument, a set or sets of filling instructions, one for each term of the schematic argument, and a classification of the schematic argument. The more restrictions an argument pattern imposes on the argument that instantiate it, the more stringent it is said to be. Roughly speaking, Kitcher's guiding idea is that explanation is a matter of deriving descriptions of many different phenomena by using as few and as stringent argument patterns as possible. Over and over again, the fewer patterns used, the more stringent they are, and the greater the range of different conclusions derived, the more unified our explanation. Kitcher summarizes this view as follows. Science advances our understanding of nature by showing us how to derive descriptions of many phenomena using the same pattern of derivation again and again. And in demonstrating this, it teaches us how to reduce the number of facts we have to accept as ultimate. Kitcher does not propose a completely general theory of how the various considerations he describes, number of conclusions, number of patterns, and stringencies of patterns, are to be traded off against one another, but does suggest that it often will be clear enough what these considerations imply about the evaluation of particular candidate explanations. His basic strategy is to attempt to show that the derivations we regard as good or acceptable explanations are instances of patterns that, taken together, score better according to the criteria just described than the patterns instantiated by what we regard as defective explanations. Following Kitcher, let us define the explanatory store as the set of argument patterns that maximally unifies the set of beliefs accepted at a particular time in science. Showing that a particular derivation is a good or acceptable explanation is then a matter of showing that it belongs to this explanatory store. Illustrations of the unificationist model. As an illustration, consider Kitcher's treatment of the problem of explanatory asymmetries. Our present explanatory practices. Kitcher compares our present explanatory practices with alternative schematizations in which such derivations are regarded as explanatory. According to Kitcher, our present explanatory practices includes the use of a single origin and development pattern of explanation, according to which the dimensions of subject artifacts, mountain stars, organisms are traced to the conditions under which the object originated and the modifications it has subsequently undergone. Now consider the consequence of adding to our present explanatory practices an additional pattern which permits the derivation of the dimensions of objects from facts about their shadows, the shadow pattern. Since the origin and development pattern already permits the derivation of all facts about dimensions and objects, the addition of the shadow pattern to our present explanatory practices will increase the number of argument patterns in our present explanatory practices and will not allow us to derive any new conclusions. On the other hand, if we were to drop the origin and development from our present explanatory practices and replace it with the shadow pattern, we would have no net change in the number of patterns in our present explanatory practices, but would be able to derive far fewer conclusions than we would with our origins and development, since many objects do not have shadows or enough shadows from which to derive all their dimensions. Kitcher acknowledges that there is nothing in the unificationist account per se that requires that all explanations be deductive. There's no bar in principle that uses the non-deductive arguments in the systemization of our beliefs. Nonetheless, the task of comparing the unifying power of different systemizations look even more formidable if non-deductive arguments are considered. And apart from this reason, Kitcher endorses the view that in a certain sense, all explanation is deductive. What is the role of causation on this account? Kitcher claims that the because of causation is always derivative from the because of explanation. That is, our causal judgments simply reflect the explanatory relationship that fall out of our intellectual ancestors' attempt to construct unified theories of nature. There's no independent causal order over and above this which our explanations must capture. Like many other philosophers, Kitcher takes very seriously even if in the end he perhaps does not fully endorse standard empiricist or Humean worries about the epistemic accessibility and intelligibility of causal claims. Taking causal, counterfactual, or other notions belonging to the same family as primitive in the theory of explanation is problematic. Kitcher believes that it is a virtue of his theory that it does not do this. Instead, Kitcher proposes to begin with the notion of explanatory unification, characterized in terms of constraints or deductive systemizations, where these constraints can be specified in a quite general way that is independent of causal or counterfactual notions, and then show how the causal claims we accept derive from our efforts at unification. The illustrations criticized. As remarked at the beginning of the section, the idea that explanation is connected in some way to unification is intuitively appealing. Nonetheless, Kitcher's particular way of cashing out this connection has been subject to criticism. One possible response is to bite the bullet and argue that from the point of view of fundamental physics, there really is no difference in the explanatory import and the retrodictive and predictive derivations, and that it is a virtue, not a defect, of the unificationist approach that it reproduces this judgment. Whatever might be said in favor of this response, it is not Kitcher's. His claim is that our ordinary judgments about causal asymmetries cannot be derived from the unificationist account. The example just described casts doubt on this claim. More generally, casts doubt on Kitcher's contention that one can begin with the notion of explanatory unification, understood in a way that does not presuppose causal notions, and use it to derive the content of causal judgment. Pragmatic theories of explanation. Introduction. Despite the many differences, the accounts of Hempel, focusing now on just the deductive nomological rather than the inductive statistical model, Salmon, Kitcher, and others discussed above, largely share a common overall conception of what the project of constructing a theory of explanation should involve, and to a considerable extent, what criteria should a theory satisfy if it is to be successful. Pragmatic theories of explanation depart from the consensus in important respects. Let us say that a theory of explanation contains pragmatic elements if, according to a theory, those elements require irreducible references to facts about the interest, beliefs, or other features of the psychology of those providing or receiving the explanation, and or irreducible reference to the context in which the explanation occurs. Although the writers discussed above agree that pragmatic elements play some role in the activity of giving and receiving explanations, they assume that there is a non-pragmatic core to the notion of explanation, which is the central task of a theory of explanation to capture. That is, it is assumed that this core notion can be specified without reference to psychological features of explainers or their audiences, and with reference to non-contextual features that are sufficiently general, abstract, and structural in the sense they hold across a range of explanations with different contents and across a range of different contexts. Relations like deductive entailment or statistical relevance are examples of candidates for such structural relationships. In addition, these writers see a goal of a theory of explanation as capturing a notion of correct explanation, as opposed to the notion of explanations being considered explanatory by a particular audience or not, a matter which presumably depends on such considerations as whether the audience understands the terms in which the explanation is framed. In this sense, correctness requires at least that the explanums be true or well confirmed, and that the explanums stand in the right relationship to the explanandum. Finally, as noted in the introduction to this entry, writers in this tradition have not had the goal of capturing all the various ways in which the word explanation is used in ordinary English. They have instead focused on such more restricted class of examples in which what is of interest is something like explaining why some outcome or general phenomenon occurred, as opposed to explaining the meaning of a word or how to solve a differential equation. The motivation for the restriction is simply the judgment that an interesting or non-trivial theory is more likely to emerge if it is restricted in scope in this way. For ease of reference, let us call this the traditional conception of the task of a theory of explanation. Some or all of the assumptions and goals are rejected in pragmatic accounts of explanation. Early contributors to this approach include Michael Scriven, 1962, and Sylvan Bromberger, 1966, and more systematic statements due to Van Frass in 1980 and Achenstein in 1983, since it is not always clear just what the points of disagreement are between pragmatic and traditional accounts. Some oriented remarks about this will be useful before turning to detail. Defenders of pragmatic approaches to explanation typically stress the point that whether provision of a certain body of information to some audience produces understanding or is illuminating for that audience depends on the background knowledge of the audience members and on other factors having to do with the local context. Factors of the sort are grouped together as pragmatic, and their influence is taken to illustrate at least one way in which pragmatic considerations enter into the notion of explanation. Taken in itself, the observation just described seems completely uncontroversial and not in conflict with traditional approaches to explanation. Indeed, as remarked above, writers like Hempel and Selman explicitly agree with the explanation has a pragmatic dimension in the sense just described. In fact, Hempel invokes the role of pragmatic factors at a number of points to address prima facie counterexamples to the deductive nomological model. This suggests that, often at least, what is distinctive about pragmatic approaches to explanation is not just the bare idea that explanation has a pragmatic dimension, but rather that much stronger claim than the traditional project of constructing a model of explanation pursued by Hempel and others has so far been unsuccessful and perhaps is bound to be unsuccessful, and that this is so because pragmatic or contextual factors play a central and illimitable role in explanation in a way that resist incorporation into the models of the traditional sort. On this view, much of what is distinctive about pragmatic accounts is their opposition to traditional accounts and their diagnosis of why such accounts fail. They fail because they admit pragmatic or contextual elements. It will be important to keep this point in mind in what follows because there is a current certain tendency among advocates of pragmatic theories to argue as though the superiority of their approach is established simply by the observation that explanation has pragmatic dimensions. Instead, it seems more appropriate to think that the real issue is whether traditional approaches are inadequate in principle because of their neglect of the pragmatic dimension of explanation. The second issue concerns an important ambiguity in the notion of pragmatic. One natural understanding of this notion, a pragmatic consideration, is one that has to do with utility or usefulness in the service of some goal connected to human interest, where the interests are in some relevant sense practical. Call this notion pragmatic. On this construal, Hempel's deductive nomological model might be correctly characterized as pragmatic theory since it links explanatory information closely to the provision of information that is useful for purposes of prediction, and prediction certainly qualifies as a pragmatic goal. For similar reason, Woodward's 2003 theory of explanation might also be counted as a pragmatic theory since it connects explanation with the provision of information that is useful for manipulation and control, unquestionably useful goals. As these examples suggest, models of explanation that aspire to traditional goals can be pragmatic theories. In the context of theories of explanation, however, the label pragmatic is usually intended to suggest a somewhat different set of associations. In particular, as noted above, pragmatic is typically used to characterize considerations having to do with facts about the psychology, interest, beliefs of those involved in providing or receiving explanations, and to the characterized considerations involved the local context, often with the suggestion that both sets of considerations may vary in complex and idiosyncratic ways that resist incorporation into the sort of general theory sought by traditional models. Call this set of associations pragmatic too. Neither Hempel nor Woodward's theory is pragmatic too. In particular, as the example of the deductive nomological model illustrates, the fact that a theory is pragmatic one in this sense that it appeals to facts and goals generally shared by human beings, such as prediction, to help to motivate a model of explanation does not preclude attempting to construct a model of explanation satisfying traditional goals and does not require commitment to the idea that explanation must be understood as pragmatic to notion. We need to be careful to distinguish these two different ways of thinking about the pragmatic dimension of explanation. Finally, as emphasized above, a concern with the pragmatics of explanation naturally connects with an interest in the psychology of explanation, and this in turn suggests the relevance of empirical studies of sorts of information that various subjects, ordinary folks, scientists find explanatory, treat as providing understanding the distinctions subjects make along explanations and so on. Although there is a growing literature in this area, the most prominent philosophical advocates of pragmatic approaches to explanations have so far tended to not make use of it. In this connection, it is worth pointing out that the psychological literature goes well beyond the truisms found in philosophical discussion about different people finding different sorts of information explanatory depending on their interest. In particular, psychologists have been very interested in exploring general features of structural patterns present in information that various subjects find explanatory. For example, Lombrazzo, 2010, finds evidence that subjects prefer explanation that appeals to relationships that are relatively stable in the sense of continuing to hold across changing circumstances, and Lien and Chang 2000 present evidence that in cases in which the explanandum has a single candidate cause, subjects prefer levels of explanation causal descriptions that maximize. Notice that in both cases, these are relationships or patterns of the sort that traditional accounts of explanation attempt to capture. As these examples bring out, there's no necessarily incompatibility between the process of trying to formulate an account of explanation that satisfies traditional goals and an interest in the psychology of explanation. It may be that subjects find certain sorts of information explanatory or understanding producing because certain structural features of the sort of traditional accounts attempt to characterize are present in that information. Indeed, this is what the Lombrazzo and Cheng papers suggest. Thus, we should distinguish the project of investigating the empirical psychology of explanation, which can be pursued with a variety of different commitments about how to best theorize about explanation, from the more specific claim that the characterization of what it is for an explanatory relationship to hold between explanandums and explanandum must be given in psychologistic terms, in the sense that it requires irreducible reference to psychological facts about particular audiences, such as vagaries of when they happen to be what they happen to be interested in. Constructive empiricism and the pragmatic theory of explanation. One of the most influential recent pragmatic accounts of explanation is associated with constructive empiricism. This is the thesis defended by Bosman Frass in his 1980 book, The Scientific Image, that the aim of science, or at least pure science, is the construction of theories that are empirically adequate, that is, yield a true or correct description of observables, and not, as scientific realists suppose, theories that aim to tell literally true stories about unobservables. Relatedly, acceptance of a theory involves only the belief that it is empirically adequate. Van Frassen's account of explanation, which is laid out in several articles and most fully in Chapter 6 of his book, is meant to fit with this overall conception of science. It is a conception according to which explanation per se is not an epistemic aim of pure science. Empirical adequacy is the only such aim, but rather a pragmatic virtue having to do with the application of science. Note that the application of science is arguably a matter of pragmatics 1. However, the idea that explanation has to do with the application of science is used to motivate the adoption of a pragmatic 2 theory of explanation. We thus have an illusion of the two notions of pragmatic distinguished above. According to Van Frassen, because explanation is a merely pragmatic virtue, a concern with explanation is not something that can require scientists to move beyond belief in the empirical adequacy of their theories to belief in the literal truth of claims about unobservable entities. According to Van Frassen, explanations are answers to questions, and getting clear about the logic of questions is central to constructing a theory of explanation. Questions can take many direct forms, but when the question of interest is a why question, explanatory queries will typically take the following form: a query about why some explanation, rather than any one of the members of a contrast class, a set of probable alternatives to the explanandum obtained. In addition, some relevant relation is assumed by the question. An answer to this question will take the form of the explanandum in contrast to the rest of the contrast class, because the answer bears the relevant relation of the explanandum to the contrast class. The relevance relation similarly depends on the context and the information which the questionnaire is interested in obtaining. For example, the relevant relation might involve causal information, but it might have to do with information about a function. Thus, context enters into the explanation, both playing a role in specifying the contrast class and the relevance relation. Van Frassen describes various rules for the evaluation of answers. For example, the explanandum and answer must be true. The other members of the contrast class must not be true. The answer must favor, raise the condition of probability of the explanandum against alternatives. The answer must compare favorably with other answers to the same question, a condition which itself has several aspects, including, for example, whether the answer favors the topic more than these other answers and whether the answer is screened off by other answers. However, he also makes it clear that a variety of different relevance relations may be appropriate depending on the context, and that the evaluation of answers also depends on context. Moreover, he explicitly denies that there is anything distinctive about the category of scientific explanation that has to do with its structure or form. Instead, a scientific explanation is simply an explanation that makes use of information that is, or at least treated as, grounded in a scientific theory. Van Frassen sums up his view of explanation and gestures as grounds for rejecting traditional objectivist approaches as follows. The discussion of explanation went wrong at the very beginning when explanation was conceived of as a relation like description, a relation between theory and effect. Really, it is a three-term relationship between theory, fact, and context. No wonder that a single relation between theory and fact ever managed to fit more than a few examples. Being an explanation is essentially relative, for an explanation is an answer, is evaluated vis-a-vis a question, which is a request for information. But exactly what is requested differs from context to context. Van Frassen begins his chapter on explanation with a brief story that provides a good point of entry into how he intends his account to work. This is commonly taken to show that the deductive nomological model has left out some factor having to do with the directional or asymmetric features of explanation, perhaps asymmetry in the relation between cause and effect that ought to be incorporated into one's model of explanation. In Van Frassen's story, a straightforward causal explanation of this usual sort of S in terms of H is first offered. Presumably, the moral we to draw here is that the context and perhaps the relevance relation are varied. Both that H explains S and S explains H are acceptable, legitimate, appropriate explanations. Moreover, since these variations in context and relevance relation turn on variations in what is of interest to the explainer and his audience, we are further encouraged to conclude that explanatory asymmetries have their source in psychological facts about people's interest and background beliefs, rather than, say, some asymmetry that exists in nature independently of these. Pragmatists about explanation think that a similar conclusion holds for other features of the explanatory relevance relation that philosophers have tried to characterize in terms of traditional models of explanation. A much more general criticism has been advanced against Van Frassen's version of pragmatic theory by Kitcher and Salmon, 1987. Basically, their complaint is that the relevance relation in Van Frassen's account is completely unconstrained, with the, in their view, obviously unacceptable consequence that for any pair of true propositions, P and A, answer A is relevant to P via some relevance relationship and thus explains P. As noted above, on Van Frassen's view, background knowledge, and in the case of scientific explanation, current scientific knowledge helps to determine which are the acceptable relevance relations and acceptable answers to the questions posed in requests for explanation. More generally, it might be argued that available scientific knowledge will provide constraints on the relevance relations and answers that exclude the anything goes worries raised by Salmon and Kitcher, at least insofar as the context is one in which the scientific explanation is sought. While this response may seem plausible enough as far as it goes, it does bring out the extent to which much of the work of distinguishing the explanatory from the non-explanatory in Van Frassen's account comes from a very general appeal to what is accepted as legitimate background information in current science. But differently, this raises the worry that once one moves beyond Van Frassen's formal machinery concerning questions and answers, which Van Frassen himself acknowledges is relatively unconstraining, one is left with an account according to which scientific explanation is simply any explanation employing claims from current science and currently scientifically approved relevance to the relation. Even if otherwise unexceptionable this proposal is, if not exactly trivial, at least rather deflationary, it provides much less than may have hoped for from a theory of explanation, in particular in cases of which there are many examples in which there is an ongoing argument or dispute in some area of science, not about whether some proposed theory or model is true, but rather about whether it explains some phenomenon. It is not easy to see how this proposal even purports to provide guidance. On the other hand, the obvious rejoinder that might be made on Van Frassen's behalf is that no more ambitious treatment that would satisfy the expectations associated with more traditional accounts of explanation, including a demarcation of candidate explanations into those that are correct and incorrect, is possible. A theory like Van Frassen's is as good as it gets. If there is no defensible theory of explanation embodying a non-trivially constraining relevance relation, it cannot be a good criticism of Van Frassen's theory that he fails to provide this. A final point that is suggested by Van Frassen's theory is that in considering pragmatic theories, it matters a great deal exactly where the pragmatic elements are claimed to enter into the account of explanation. One point at which such considerations seem clearly to enter is the selection of characterization of what an audience wants to be explained. This is reflected in Van Frassen's theory in the choice of an explanandum and associated contrast class. Obviously, whether we are looking for an explanation of why. However, this particular sort of interest relativity and associated phenomenon having to do with the role of contrastive focus in the characterization of explananda, which really just serve to specify more exactly which particular explananda we want explained, seems something that can be readily acknowledged by traditional theories. After all, it is not a threat to the deductive, nomological, or other models with similar traditional aspirations that one audience may be interested in explanation of the photoelectric effect, but not to the deflection of starlight by a sun, and another audience may have the opposite interest. What would be a threat to the deductive, nomological in similar models would be an argument that once some explanation is fully specified, whether explanandums explain the explanandum, that is, whether there's an explanatory relationship between the explanandums and the explanandum, is itself interest relative. It is natural to interpret Van Frassen as making this latter claims both in connection with explanatory asymmetries and more generally. Conclusion. Conclusions open issues in further directions. What can we conclude from the recounting of some of the more prominent recent attempts to construct models of scientific explanation? What important issues remain open, and what are the most promising directions for future work? Of course, any effort at stock taking will reflect a particular point of view, but with this caveat in mind, several observations seem plausible, if not completely uncontroversial. The role of causation. One issue concerns the role of causal information in scientific explanation. All the traditional models considered above attempt to capture causal explanations, although some attempt to capture non-causal explanations as well. It is a natural thought endorsed by many that many of the difficulties faced by the models described above derive at least in part from their reliance on inadequate treatment of causation. The problems of explanatory asymmetries and explanatory irrelevance seems to show that holding of a law between cause and effect is not sufficient for cause to cause effect, hence not a sufficient condition for cause to figure an explanation of effect. If the argument is correct, a fundamental problem with the statistical relevance, structural relevance model is that statistical relevance information is insufficient to fully capture causal information in the sense that different causal structures can be consistent with the same information about statistical relevance relationships. Similarly, the causal mechanistic model faces a difficulty that information about causal processes interaction is also insufficient to fully capture causal relevance relations, and that there is a range of cases in which causal relationships hold between cause and effect, and hence in which cause figures in an explanation of effect, although there's no connecting causal processes between cause and effect. Finally, a fundamental problem with unificationist models is that the content of our causal judgments does not seem to fall out of our efforts at unification, at least when unification is understood along the lines advocated by Kitcher. For example, as discussed above, considerations having to do with unification do not by themselves explain why it is appropriate to explain effects in terms of their causes rather than vice versa. These observations suggest that insofar as we are interested in causal forms of scientific explanation, progress may require more attention to the notion of causation and more thoroughgoing integration of discussion of explanation with the burgeoning literature on causation, both within and without outside of philosophy. A number of steps in this direction have been taken. Does this mean that a focus on causation should entirely replace the project of development models of explanation? On the philosophers should stop talking about explanation and instead just talk about causation. Despite the apparent certainty of causation to many explanations, it is arguable that completely subsuming the latter into the former loses connection with some important issues. For one thing, causal claims themselves seem to vary greatly in the extent to which they are explanatorily deep or illuminating. Causal claims found in Newtonian mechanics seem deeper and more satisfying from the point of view of explanation than causal claims in the rock broke the window variety. It is usually supposed that such differences are connected to other features, for example, how general, stable, coherent with background knowledge a causal claim is. However, notions like generality are vague, and not all forms of generality seem to be connected to explanatory goodness. So even if one focuses on causal explanation, there remains the important project of trying to understand better what sorts of distinctions among causal claims matter for goodness in explanation. To the extent that this is so, the kinds of concerns that have animated traditional treatment of explanations don't seem to be entirely subsumable into standard accounts of causation, which have tended to focus largely on the project of distinguishing causal from non-causal relationships rather than the features that make causal relationships good for purposes of explanation. Another important question has to do with whether there are forms of why explanations that are non-causal. If so, how important are these are in science and what is their structure? Hempel seems to have thought of causal explanations simply as those deductive nomological explanations that appeal to causal laws, which he regarded as a proper subset of all laws. Thus, in his view, causal and non-causal explanations share a common structure. Kitcher's unificationist model was also intended to apply to both causal and non-causal explanations, such as unifying argument patterns in linguistics. More recently, there's been a great upsurge in interest in whether there are non-causal forms of explanation, with some claiming that they are ubiquitous in science. If there are such explanations, this raises the issue of what distinguishes them from causal explanations and whether there is some overarching theory that subsumes both causal and non-causal explanations. The single model of explanation. As noted above, one way in which the attempt to develop a single general model of explanation might fail is that we might conclude that there are causal and non-causal forms of explanation that have little in common. But even putting this possibility aside, another possibility is that explanation differs across different areas of science in a way that precludes the development of a single general model. It is, after all, uncontroversial that explanatory practice, what is accepted as an explanation, how explanatory goals interact with others, what sort of explanatory information is thought to be achievable, discoverable, testable, varies in significant ways across different disciplines. Nevertheless, all of the models of explanation surveyed above are universalist in aspiration. They claim that a single, one-size model of explanation fits all areas of inquiry insofar as these have a legitimate claim to explain. Although the extreme position that explanation in biology or history has nothing interesting in common with explanation in physics seems unappealing and in any case has attracted little support. It seems reasonable to expect that more effort will be devoted in the future to developing models of explanation that are more sensitive to disciplinary differences. Ideally, such models would reveal commonalities across disciplines, but they should also enable us to see why explanatory practice varies as it does across different disciplines and the significance of such variations. For example, as noted above, biologists, in contrast to physicists, often describe their explanatory goals as the discovery of mechanisms rather than the discovery of laws. Although it's conceivable that this difference is purely terminological, it is also worth exploring the possibility that there is a distinctive story to be told about what a mechanism is, and this notion is understood by biologists and how information about mechanisms contribute to explanation. A closely related point is that at least some of the models described above impose requirements on explanation that may be satisfiable in some domains of inquiry, but are either unachievable in any practically interesting sense in other domains, or to the extent that they may be achievable, bear no discernible relationship to generally accepted goals of inquiry in those domains. For example, we noted above that many scientists and philosophers hold that there are few, if any, laws to be discovered in biology and the social science and social and behavioral sciences. If so, models of explanation that assign a central role to laws may not be very illuminating regarding how explanation works in these disciplines. As another example, even if we suppose that the partition into objectivity homogeneous reference classes recommended by the statistical relevance model is an achievable goal in connection with certain quantum mechanical phenomenon, it may be that it is simply not a goal that can be achieved in a non-trivial way in economics and sociology, disciplines in which causal inference from statistics also figures prominently. In such disciplines, it may be that additional statistically relevant partitions of any population or subpopulation of interest will virtually always be possible, so that the activity of finding such partitions is limited only by the cost of gathering additional information. A similar assessment may hold for most applications of the causal mechanical model to the social sciences. Okay, so there we go. Okay, Lou, good to see you. Mr. Boston, thanks for being in the chat. So a lot of material there. To some extent, this part about scientific explanation is like the pinnacle crux of the philosophy of science and gets down to the importance of metaphysics, the relation of cause and effect, which is really part of metaphysics and not science. And so let's keep it going. All these things have more to get detail into, and further analysis of most of these models would be more in logical notation. And so there you have like, well, is explanation you like what I'm doing now using words as opposed to mechanisms or causal relationships that are expressed in purely logical formulations. So important details. And okay, so let's look now at mathematical explanation. And okay, so mathematical explanation. So we just looked at scientific explanation, and now we're going to look at mathematical explanation. What's the difference between scientific explanation and mathematical explanation? And is mathematical explanation actually more scientific than scientific explanation? We'll return to the indispensability argument that we discussed 2 weeks ago, the Quine-Putnam hypothesis, and go more into detail on that. Mathematical explanation. The philosophical analysis of mathematical explanation concerns itself with two different, although connected, areas of investigation. The first area addresses the problem of whether mathematics can play an explanatory role in the natural and social sciences. The second deals with the problem of whether mathematical explanation occurs within mathematics itself. Accordingly, this entry surveys the contributions to both areas. It shows their relevance to the history of philosophy, mathematics, and science. It articulates their connection and points to the philosophical payoffs to be expected by deepening our understanding of the topic. And all these topics that I'm covering will be going into much more detail from a philosophical perspective in my next series on metaphysics. Mathematical explanation in the empirical sciences. Nearly all of our most successful empirical sciences employ a great deal of mathematics. In addition, scientists often emphasize the value of explaining some phenomenon that they have discovered. It is natural to wonder then if mathematics is well suited to contribute to the explanation of natural phenomenon and what these contributions might be. In the philosophy of science, most accounts of explanation identify an explanation with appropriate description of a cause. Nearly everyone can admit that mathematical tools are an excellent means of tracking or representing causes. Much of the debate about mathematical explanation in the empirical sciences focused on more contentious cases. What role might mathematics play in non-causal explanations, if there are any, and how might these cases challenge this or that account of causal explanation? One kind of case that has been emphasized aims to explain the possibility or impossibility of some process. Neither mathematical fact is a cause of the feature of the process in question, so we seem to have non-causal explanation where mathematics is part of the explanation. The possibility or impossibility of other processes are explained by other areas of mathematics that investigate structures or formal features of natural systems. Another kind of non-causal mathematical explanation deals with a striking or surprising feature of a phenomenon where that feature can be identified through a mathematical analysis of the situation. The feature may be tied to a minimization process or be especially resilient or stable for what is arguably a mathematical reason. There's an extensive literature on how these optimality explanations might work in biology and economics. However, this explanatory contribution from mathematics can be found in other domains as well. The mathematics of the situation is central to the character that the law takes on. Other cases turn on a mathematical analysis of the stability or instability of some process. The rest of section 1 will consider some of the history and debates about non-causal mathematical explanations and their significance for various theories of scientific explanation. The section then turns to two other debates that are closely related to these features of these explanations, how mathematical models may explain despite their highly idealized character, and how these explanatory role of mathematics and science could support a Platonistic interpretation of pure mathematics. Some historical remarks. Does mathematics help explain the physical world, or does it actually hinder a grasp of the physical mechanisms that explain the how and why of a natural phenomenon? It is not possible here to treat this topic in its full complexity, but a few remarks will help the reader to appreciate the historical importance of the question. Aristotle describes his ideal of scientific knowledge in posterior analytics in terms of, among other things, knowledge of the cause. We suppose ourselves to possess unqualified scientific knowledge of a thing as opposed to knowing it in it the accidental way in which the sophist knows when we think that we know the cause on which the fact depends as the cause of the fact and of no other, and further that the fact could not be other than it is. The causes atia in question are the four Aristotelian causes: formal, material, efficient, and final. Nowadays, translators and commentators of Aristotle prefer to translate Asian as explanations so that the theory of the four causes becomes an account of the four types of explanations. For instance, here is Barnes' translation of the passage quoted earlier. We think we understand a thing simpliciter and not in the sophistic fashion accidentally, whenever we think we are both aware that the explanation because of which the object is its explanation, and that it is not possible for this to be otherwise. But how will we obtain scientific knowledge? Scientific knowledge is obtained through demonstration. However, not all logically cogent proofs provide us with a kind of demonstration that yields scientific knowledge. In a scientific demonstration, the premises must be true, primarily, immediately, better known, and prior to the conclusion, which is further related to them in as effects to causes. In Barnes' translation, if then understanding is as we posited, it is necessary for demonstrative understanding, in particular, to depend on things which are true and primitive and immediate and more familiar than and prior to an explanatory of the conclusion. Accordingly, in posterior analytics, Aristotle distinguishes between demonstrations of the fact and demonstrations of the reason fact. Although both are logically cogent, only the latter mirrors the causal structure of the phenomenon under investigation and thus provides us with knowledge. We can call them respectively non-explanatory and explanatory demonstrations. In Aristotle's system, physics was not mathematized, although causal reasonings were proper to it. However, Aristotle also discussed extensively the so-called mixed sciences, such as optics, harmonics, and mechanics, characterizing them as the more physical of the mathematical sciences. There is a relation of subordination between these mixed sciences and areas of pure mathematics. For instance, harmonics is subordinated to arithmetic and optics to geometry. Aristotle has no doubt that there are mathematical explanations of physical phenomena. For here, it is for the empirical scientist to know that fact and for the mathematical to know the reason why. For the latter, have the demonstrations of the explanations, and often they do not know the fact, just as those who consider the universal often do not know some of the particulars through lack of observation. However, the topic of whether mathematics could give explanations of natural phenomenon was one on which there was disagreement. As the domains to which mathematics could be applied grew, so did the resistance to it. One source of tension consisted in trying to reconcile the Aristotelian conception of pure mathematics and abstracting form, matter, and motion as abstracting form from matter and motion with the fact that both physics, natural philosophy, and the mixed sciences are all conversant about natural phenomenon and thus dependent on matter and motion. For instance, an important debate in the Renaissance known as the Quaestio de Certitudine Mathematicarum focused in a large part on whether mathematics could play the explanatory role assigned to it by Aristotle. Some argued that lacking causality, mathematics could not be explanatory link in the explanation of natural phenomena. By the time we reach the 17th century and the Newtonian revolution in physics, the problem reappears in the context of a change of criteria of explanation and intelligibility. This has been beautifully described in an article by uh, Gingras in 2001. Gingras argues that the use of mathematics in dynamics, as distinct from its use in kinematics, had the effect of transforming the very meaning of the term explanation as it was used by philosophers in the 17th century. What Gingras describes, among other things, is how the mathematical treatment of force espoused by Newton and his followers, a treatment that ignored the mechanics that could explain why and how the force operated, became an accepted standard for explanation during the 18th century. After referring to the 17th and 18th centuries discussions on the mechanical explanation of gravity, he remarks, the episode shows that the evaluation criteria for what was to count as an acceptable explanation of gravitation in this case were shifting towards mathematics and away from mechanical explanation. Confronted with a mathematical formulation of a phenomenon for which there was no mechanical explanation, more and more actors chose the former, even at the price of not finding the latter. There was something new for the whole of the 17th century and most of the 18th to explain a physical phenomenon meant to give a physical mechanism involved in its production. The publication of Newton's Principia marks the beginning of the shift where mathematical explanation came to be preferred to mechanical explanation when the latter did not conform to calculations. Among those who resisted this confusion between physical explanations and mathematical explanations was the Jesuit Louis Castel. He granted that the propositions connected mathematically the inverse square law to the ellipticity of the course of the planets. However, he objected that the one is not the cause, the reason of the other, and that Newton had not provided any physical explanation other than only a mathematical one. Indeed, physical reasons are necessary reasons of entailment or linkages of mechanisms. In Newton, there is none of this kind. Some contemporary discussions bear close proximity to these worries. Consider Morrison's book, Unifying Scientific Theories, in 2000. One of the major theses of this book is that unification and explanation often pull in different directions and come apart, contrary to what is claimed by unification theories of explanation. One of the examples discussed in her introduction reminds us of Castell's objections. Another example in the unification of terrestrial is the unification of terrestrial and celestial phenomena. In Newton's Principia, although influenced by Cartesian mechanics, one of the most striking features of the Principia is its move away from explanations of planetary motions in terms of mechanical causes. Instead, the mathematical form of the force is highlighted. The planetary ellipses discovered by Kepler are explained in terms of mathematical description of the force that produces these motions. Of course, the inverse square law of gravitational attraction explains why the planets move in the way that they do, but there's no explanation of how this gravitational force acts on bodies, how it is transported, nor is there any account of its causal properties. Using several case studies, Morrison argues that the mathematical structures involved in the unification often supplied little or no theoretical explanation of the physical dynamics of the unified theory. In short, the mathematical formalism facilitates unification but does not help us explain the how and why of physical phenomena. We have to close these historical remarks here, although it would be interesting to pursue these questions in a more systematic way in the 19th and 20th centuries. The aim of the above was to prepare the ground for showing how in contemporary discussions in philosophy of science, to which we now turn, we are still confronted with such issues. Theories of explanation. Two legacies of an Aristotelian tradition are that explanations require causes and that providing explanation requires giving an argument that turns on laws. Debates in the philosophy of science since the 1960s have shown how one can privilege one legacy over the other. Hempel's deductive nomological analysis of explanation requires that explanation be deductively valid arguments from true premises, where at least one premise is a scientific law. Hempel and other empiricists in this broad tradition are wary of making causes central to explanation. This is apparent even in some of Hempel's critics, such as Kitcher, who emphasizes the unifying power of explanations. For Kitcher, an explanation is an instance of deductive argument scheme, where the schemes to adapt are identified on the basis of global features of the claims we accept. By contrast, Selman's work has persuaded many philosophers of science that explanations need only provide causal information about the explanatory target. For Selman and others in this tradition, explanations do not require laws and need not even be arguments. One development of this approach preserves Selman's emphasis on causal mechanisms as a special sort of process. These so-called new mechanists endorse a broader notion of causal mechanisms than Selman allowed for, and identified an explanation of some target with the mechanism that produces it. Other approaches to causal explanation include David Lewis's counterfactual analysis of causation and Woodward's interventionist theory. Despite their differences, Lewis and Woodward allow for causal explanations in the absence of mechanisms. This makes their approaches to explanation easier to generalize to non-causal cases. Philosophical discussions of non-causal mathematical explanation can be classified based on how they are related to these debates about scientific explanation more generally. One position argues for the need to restore something like Hempel's emphasis on laws or Kitcher's claims about unification. Another position generalizes from an account of causal explanation so that it can include these mathematical cases. Yet a third position is pluralist about explanation and argues that explanations come in a variety of distinct sorts and that cannot be fit into one or the other of these two options. Lang's extensive discussion on non-causal explanation can be seen as a valiant attempt to preserve the law-based approach to scientific explanation that goes back to Hempel and Aristotle. Lang's work on laws emphasized how to identify claims with the right kind of modal strength to contribute to explanations. Lang's approach to mathematical explanation extends to this point so that mathematical claims can function in explanations in a distinctive way due to their special degree of necessity. This allows mathematics to contribute to what Lang calls explanations by constraint that show how some outcome is guaranteed to arise. This is how Lang treats the strawberry division case and also cases like the bridges of Koenigsberg. Other mathematical explanations turn the dimension of the quantities involved or the statistical features of some process. In each of these types of cases, the modal character of the mathematical claim allows it to explain just as the modal character of ordinary scientific laws allows them to explain. Unsurprisingly, many philosophers have challenged Lang's proposal in ways that are reminiscent to how Selman objected to Hempel's deductive nomological account. For example, Craver and Povich object that in the absence of causal constraint on explanation, Lang's proposals lack any suitable worldly basis and so count too many representations of some target as explanatory. As a mechanist about explanation quite generally, Craver seems inclined to dismiss the possibility of non-causal mathematical explanations. His co-author Povich has authored a more constructive proposal for these cases that allows for explanations with a variety of worldly ontic bases. Povich deploys a version of what amounts to a new consensus for handling non-causal explanations. If a proposed explanation relates to the right counterfactuals in the right way, then it is legitimate. However, there is as yet no agreement on what sorts of counterfactual tests are sufficient for explanation. One option is to treat a mathematical claim like a law that governs some situation and to credit the mathematics with explanatory power, whether it allows us to assess a range of counterfactual scenarios. This is Routlinger's proposal, which deliberately loosens the requirement that Woodward places on intervention. For example, in the bridges of Koenigsberg case, the mathematical claim indicates that a circuit of the bridges would be possible in the counterfactual scenario where some of the bridges were absent. Routlinger concludes that the mathematical claim thus explains what is going on in the actual world by indicating what makes the difference to the feature of interest. Another option is to treat the mathematical claim like a cause. Then the claim will be explanatory when a counter-mathematical that supposes that this claim is false winds up making a difference to the target in question. This sort of counter-mathematical involves impossible worlds where necessary truths come out false. This is the option that Povich takes. Another family of proposals along these lines has been developed by Barron in collaboration with Colleyven and Ripley. Barron draws on David Lewis's procedure for evaluating counterfactuals tied to causation. Consider the scenario that arises through a miraculous change that is just enough of a change to make the antecedent of the counterfactual true. In addition, Barron requires that the features of the natural world that are implicated in the shift in the mathematics be changed in a corresponding way. There are pressing questions for these proposals about the nature of impossible worlds and our epistemic access to them. Another sort of objection has been raised by Barron himself in work that develops another account of mathematical explanation. Barron, like Baker and Lang, aims to identify a special class of genuinely or distinctively mathematical explanations of natural phenomena. What is special about these cases is that the mathematics explains, but not only by representing or describing some non-mathematical explainers, such as causes on otherworldly difference makers. Barron's general worry is that simply using counter-mathematicals fails to distinguish explanations that employ mathematics from these generally mathematical explanations. Barron concludes that some additional requirements must be imposed beyond the truth of the relevant counter-mathematical. Here Barron reaches back to Kitcher's idea that explanations are instances of a special sort of argument scheme, where the schemes are found through a process of appropriately unifying the claims that we accept. Other recent work on non-causal mathematical explanations also seem to be returning to some of the original sources of these debates. For example, Lang argues that the best way to make sense of the explanatory power of pure mathematics in the empirical sciences is to adopt an Aristotelian interpretation of pure mathematics. Lyon proposes another way of relating mathematical explanation to causal explanations by adopting Jackson and Petit's notion of program explanation. A program explanation does not invoke a property that causes the outcome of interest. Instead, the explanation appeals to a property that guarantees the presence of some member of a family of properties where some such property causes the outcome of interest. As Lyon summarizes his proposal, an explanation of an empirical fact is mathematical. It is mathematics doing explanatory work. If the explanation is a program explanation that uses mathematics in a way that is indispensable to the program. One concern with this proposal is that it includes cases where the mathematics merely represents some causally relevant property. As with the stamps case noted above, programming is too indiscriminate a relation to avoid this worry. A sweeping way of dealing with the apparent tension between causes and mathematics has been pursued by some ontic structural realists. They identify the fundamental metaphysical structure of the world with the mathematical structure. If one adopted this kind of structural realism, then the explanatory power of mathematics in the empirical science would receive a satisfying analysis. In fundamental physics, scientists would be working with the fundamental mathematical structure directly, and so explanations there would be essentially mathematical. In non-fundamental domains such as biology or economics, scientists would be investigating features of the world that are ultimately grounded in some mathematical structure. So again, it would make sense for many of the explanations in non-fundamental sciences to be mathematical. Causal explanations would then turn out to be perfectly consistent with more fundamental mathematical explanations. Few philosophers are willing to adopt such a metaphysical position in order to resolve questions about mathematical explanation, although at least one physicist has defended this approach, Max Tegmark. Another less metaphysical solution to these difficulties is to retain an account of how causal explanations work to simply supplement it with a distinct account of how various kinds of non-causal explanations arise. This sort of explanatory pluralism is also reminiscent of one aspect of the Aristotelian tradition. One challenge for the explanatory pluralist is to make sense of the value that scientists ascribe to explanations. How can there be some special value in having an explanation if explanations come in different kinds that have nothing in common? One response to this challenge is that grasping an explanation produces scientific understanding, but the nature and value of the scientific understanding remains the subject of active debate. Another response is to defend restrictive form of explanatory monism. It may turn out that this monism about explanation is so restrictive that there are no mathematical explanations in science. This is reminiscent of one side of the Renaissance debate. Another sort of pluralism arises from supposing that causal explanations involve the mechanisms championed by the new mechanists, and then allowing for other sorts of explanations that work in different ways. One type of case that has received extensive discussion is so-called topological explanation. These explanations appeal to a structural or network-based features to explain an aspect of a system. One position is that topological explanations are non-causal, non-mechanical explanations that are based on different kinds of explanatory relevant features. For example, Kostic and Khalifa argue that non-ontic approach that privileges scientists' explanatory goals is needed to make sense of topological explanation. Another position is that an appropriately flexible notion of mechanism can count genuine topological explanations as mechanical explanations. As with the debates arising from Woodward's and Lewis' counterfactual approach to causal explanation, the main question is what counts as a mechanism and how non-mechanisms can be explanatory. More recently, some authors have tried to restore some kind of explanatory monism by arguing that all scientific explanations turn on non-representational expressive elements. If this was right, then there would be no difficulty making sense of mathematical explanations, so long as mathematics can be seen to perform whatever expressive function an author identifies. The viability of an expressive approach thus turns on questions about the interpretation of pure mathematics. Mathematical models and idealization. One assumption of the Aristotelian tradition is that is often on question is that whatever provides the explanation, the explanums must be true. Philosophical investigation of scientific models and how these models may explain have convinced many that the explanums need not be true. The argument for this conclusion is straightforward. Scientific models explain, and scientific models are not true, so truth is not required for explanation. A traditional response to this argument is that even though models are not true, a model can only explain if it generates some truths about the target of explanation. That is, a model explains only when it represents its target to be a certain way. The debate thus turns on the options for making sense of how models represent, especially when those models are mathematical, and if it represents aspects of models are sufficient to make sense of model-based explanation. One proposal is that a model explains when the model represents a target system to be a certain way and only represents something else that explains why the system is that way. For example, a causal model of outcome needs to represent in some cause and effect. However, there is no consensus of what it takes for a model to represent something. As a model, it is distinct from its target, and the model and target are often composed of different materials. It is natural to conclude that structural relations are central to what a model represents. However, it's hard to maintain that a model represents a target just in case there is a structural relation between the model and target. For example, a model is isomorphic to itself, and so it stands in a structural relation to itself, but we do not want to say that a model represents itself. There are also model-target relations that lack any clear structural characterization, so it seems that standing in a structural relation is neither necessary nor sufficient for a model to represent a target. One response to these problems is that a model represents a target when agents claim that a structural relation obtains between the model and the target, where the relation may be quite selective and involve reinterpretations of various elements of the model. Some authors associate the relations that agents establish between model and target with inferential principles. So according to these various proposals, the model explains a feature of a target when either some representational relation or inferential licenses from model to targets have been established by agents, and these connections generally explain the feature that they are causes of the feature. The different approaches to explanation surveyed can then be used to identify explanatory models and what they explain. A mechanist about explanation can allow that mathematical models explain by representing mechanisms, while difference-making views will require an explanatory model to represent difference-making, how changing factor will go along with a change in outcome. All of these proposals will argue that scientific models do not need to be true in order to explain. All that needs to occur is for the model to provide some truths by representing the right things about the target. So the presence of falsehoods that the model also provides about the target does not stand in the way of the model's explanatory power. This approach to explanatory models and idealization has been called into question by Batterman, One argument from Batterman is that there are explanatory models that do not explain in virtue of an element of the model representing some explanatory relevant factor, such as a cause or even exotic non-causal difference maker. Indeed, in such cases, while we have a genuine mathematical explanation of physical phenomenon, there is no appeal to the existence of mathematical entities or their properties. Instead, the appeal is to a mathematical idealization resulting from the limit operation that relates one model to another. The case that Batterman is discussing here involves an operation known as taking the thermodynamic limit and transforms a finite statistical mechanical model into a continuum thermodynamic model. This is central to the explanation of the universality of some features of the phase transition that includes liquid gas transitions and magnetization. The features are universal in the sense that they rise across systems with very different microphysical features and so seem especially puzzling. One point that Batterman is making here is that mathematical operations that connect models can be significant for mathematical explanation of an empirical phenomenon. The defenders of traditional approaches to model explanation often focus on cases where a single mathematical structure is used to explain. However, the basic idea of the traditional approach can be extended to deal with the explanatory significance of some mathematical operation. For example, one mathematical model may be transformed into another mathematical model through a mathematical operation. If this operation reflects something of explanatory significance, then the two models and the operation connecting them may be central to the explanation. Some idealizations are associated with these operations, as is the case where the ocean is treated as infinitely deep or a planet is modeled as a point particle. In such cases, the operations function by changing or removing the interpretation of the elements of the model. Batterman also develops another point that poses a more significant challenge to traditional approaches of model explanation. This is the mathematical idealization that results from this operation and that is tied to one of these models is essential to the whole explanation. In the ocean case, there's no temptation to say that the ocean being infinitely deep in one model is explanatorily relevant to the character of the waves on the surface of the actual ocean. All that this idealization turns on is the depth is the above some threshold. Other cases can be handled using similar Galilean idealizations that eliminate the falsehood from the genuine explanation. But in Batterman's cases, such as the phase transition cases, he is clear that it takes the idealization to be essential to the explanation. These non-traditional idealizations play essential explanatory roles involving operations or mathematical processes without representing the system in question. If this point is accepted, then these cases would undermine the scope of the traditional approach. In the philosophy of physics, there's been extensive discussion on how essential these idealizations are to the explanations in question. Some critics of Batterman have argued that these cases can be dealt with using explanations that avoid these idealizations or that treat these idealizations in the manner that we treated the infinitely deep ocean. But other critics of Batterman have argued that a more selective approach to what these models represent allows one to admit that the idealizations are essential to generating the explanation, but that they are not literally to be included in the explanation itself. For example, a counterfactual approach to these cases would identify the explanation with some counterfactuals that are generated by the model. Batterman and others in turn have responded that all these criticisms fail to do justice to the phenomenon in question or what scientists say about their explanations. Other alternatives to a traditional approach to mathematical modeling and explanation have been developed using other sorts of cases as the primary motivations. One theme of this work is a generalization of Batterman's point of that scientific explanations often involve many models whose representational relation to the explanatory target is more involved than what is usually allowed. For example, Kazazada considers a case in which with two mathematical models with different spatial scales of a process of skin color pattern formation. Biologists ask for an explanation of how the two processes related to one another. Kazazada argues that this explanation required additional bridge mathematics over and above the mathematics found in the original two models. The additional mathematics contributed to the explanation by characterizing how the microscopic processes give rise to the unexpected macroscopic structures. McKenna goes on further to argue for the importance of cases where models cannot be stitched together in purely mathematical terms. In McKenna's main case, various models of sea ice permeability are developed for the purposes of large-scale climate modeling. No single mathematical model of sea ice proved to be adequate to supply the right parameter to the large-scale model. Instead, different models of sea ice were used in conjunction with the high-resolution empirical data about samples of sea ice formation. The significance of these cases for the explanations that arise from these modeling techniques is likely to be a subject of ongoing debate. Explanatory indispensability arguments. Many philosophers are interested in non-causal mathematical explanations in science because they seem to support an explanatory indispensability argument for a Platonist interpretation of pure mathematics. Calivan and Baker have been the most ardent defenders of such an argument. In his 2001 book, Calivan presented a general indispensability argument for the existence of mathematical entities like the natural numbers. We ought to have ontological commitment to all and only those entities that are indispensable to our best scientific theories. Mathematical entities are indispensable to our best scientific theories. Therefore, we ought to have ontological commitment to mathematical entities. The notion of ontological commitment was first articulated by Quine and Putnam. These commitments are reflective what one should believe in. Premise 1 is tied to a naturalistic approach to these beliefs that claims that should be determined by the character of our best scientific theories, where Quine, one's ontological commitments are settled by the best regimentation of one's scientific theories into first-order logic, where one makes a regimentation. The best is determined by ordinary scientific criteria like the consistency and simplicity. Some of Calivan's cases in his book invoke the explanatory contribution that mathematical entities make to our best theories. If we suppose that one aim of science is to explain, then a regimentation may be the best, in part because it affords explanation of various scientific phenomena. An explanatory version of this indispensability argument became more prominent after Melia's exchange with Calivan. Melia argued that indispensability quantification over mathematical entities was not sufficient for ontological commitment. Any such commitments could be canceled by a Weaseling maneuver that added, but I do not accept the existence of any mathematical entities. For example, one could use numbers to count how many apples and pears one has and conclude that there are more apples than pears, but Melia would then add that he has rejected the existence of natural numbers, thereby canceling the commitment. Calivan replied that such an addition was incoherent when the mathematical entities were explaining something, and Melia agreed, where there are clear examples where the postulation of mathematical objects resulted in an increase in the same kind of utility as that provided by the postulation of theoretical entities, then it would seem that the same kind of considerations that supported the existence of atoms, electrons, and spacetime equally supports the existence of numbers, function, and sets. The debate about indispensability in Platonism then largely turned to the evaluation of cases. Baker took up Melia's challenge by reformulating the argument so that the explanatory question became central. Baker also introduced new cases like the Circada case, where the parallel between atoms and numbers was meant to be clear. In Baker's formulation, the argument is, 1, we ought rationally to believe in the existence of any entity that plays an indispensable explanatory role in our best scientific theory. 2, mathematical objects play an indispensable explanatory role in science. 3, hence we ought rationally to believe in the existence of mathematical objects. The emphasis on explanation in premise 1 is, of course, consistent with Quine's process of regimentation. All premise 1 maintains, then, is that one should endorse whatever these ontological commitments turns out to be. Hence, the second way to support premise 1 is available. One could appeal to the inference to the best explanation, and it's used to support scientific realism about unobservable entities like electron. Baker sometimes ties the appeal of his indispensability argument to scientific realism. A crucial plank of scientific realism position involves inference to the best explanation to justify the postulation in particular cases of unobservable theoretical terms. The indispensability debate only gets off the ground if both sides of the inference to the best explanation take inference to the best explanation seriously, which suggests that explanation is of key importance in the debate. The appeal of inference to the best explanation avoids the Quinean process of regimentation by directing our attention to some explanatory target. If we are scientific realists, then we accept the use of inference to the best explanation in support of our claims about the existence of various entities. So if we find that the best explanation also includes abstract objects like prime numbers, then we should also accept their existence. Three worries about this explanatory indispensability argument can be fruitfully distinguished. The first worry is that the argument is somehow circular, begs the question, or else fails to correctly identify the basis for knowledge of the existence of mathematical entities. The point was forcefully represented by Steiner in 1978. Steiner argues for the existence of mathematical explanation and also claims to know of the existence of abstract mathematical entities. However, no explanatory argument can establish the existence of mathematical entities. The reason for this is attributed to Morgan Besser. We cannot say what the world would be like without numbers because describing any thinkable experience except for utter emptiness presupposes their existence. The point seems to be that what we must be able to compare mathematical and non-mathematical explanations of some target in order to get an explanatory argument going. But if that target always presupposes the existence of some mathematical entities, then this comparison is not possible. Bangu has developed this point by noting how many of the cases discussed have targets that are mathematical in character. So the worry continues. Mathematical explanations are only indispensable in science if we have used mathematical entities to characterize the target phenomenon. Pincock has a somewhat similar concern. If the targets are characterized in weak mathematical terms, then only weak mathematical theories will be needed to explain these targets. And these theories can be easily supplied with a nominalistic interpretation that preserves these theories' explanatory power. Another worry accepts that there are some sense mathematical explanations in science. However, premise 2 is rejected because these explanations fail to involve the existence of any mathematical objects. Satsi has developed this criticism by claiming that mathematics only explains by representing some non-mathematical features of the physical world. On this reading, premise 2 requires the existence of some distinctively or generally mathematical explanations, but there are no such explanations. As Satsi put the worry, what really matters for the indispensability argument, all that matters is whether or not mathematics plays the kind of explanatory role that we should take as ontologically committing. Until the defenders of the argument clarify what distinctively mathematical explanations are and how they involve mathematical objects, it seems that premise 2 is in trouble. The third kind of worry is that about premise 2 is developed by mathematical fictionalists like Yablo and Lang. Fictionalists accept the existence of distinctively mathematical explanations and yet argue that these explanations do not presuppose the existence of any mathematical objects. For example, Lang argues that we can generate mathematical explanations of physical phenomena that do not appeal to any abstract mathematical objects, but instead only require modal truths about what follows logically from our mathematical assumptions, together with the recognition that the assumptions of our mathematical theories are true when interpreted as about the physical system under examination. Lang can thus endorse the very same unified derivation of the features of Baker's cicadas, and yet refrain from accepting the existence of mathematical objects, while Satsi takes the physical features of the system to be genuine explainers. Lang uses the same features to interpret the mathematical theories that are doing the explanatory work. Either way, premise 2 of the indispensability argument comes out false. Collivin and Baker's strategy for supporting premise 2 has largely involved cases where it appears that mathematical objects play a role in the explanation that is analogous to what unobservable entities like electrons play in other explanations. This strategy would be most effective against representational approaches to mathematical explanation. The basic idea is that scientists value these explanations, and so any reinterpretation of them in non-mathematical terms risk privileging an unmotivated philosophical theory over some legitimate scientific practices. Baker and Collivin put the point in a reply directed at Daly and Langford in 2009. Commitments to philosophical theories such as nominalism, a causal theory of explanation, or the indexing view of mathematical applications are not good reasons for rejecting well-supported scientific and mathematical claims. The second strategy that Collivin has pursued is to challenge critics to recast these explanations in non-mathematical terms. The refusal to do this involves an easy road to nominalism that Collivin thinks is untenable. While some pieces of language is delivering an explanation, either that piece of language must be interpreted literally or the non-literal reading of the language in question stands proxy for the real explanation. This strategy is most effective against fictionalists. It involves the conception of scientific explanation that requires every genuine explanation to be presentable in literal, non-metaphorical language. To say why something is the case, we must literally say what is responsible for what, and so it must be in principle possible to avoid fictional or metaphorical tools. If fictionists are right about pure mathematics, then mathematics is simply such a tool, and so they should be able to sketch non-mathematical version of the explanations at issue. The fictionist response is to deny the conception of explanation. Yet another kind of criticism of premise 2 accepts both the existence of mathematical explanations and that these explanations involve mathematical objects, but maintains that these explanations are dispensable from our best science. That is, either the best regimentation of our scientific theories will avoid quantification over mathematical objects, or no appeal to inference to the best explanation will actually support adopting such an explanation. This sort of criticism can be traced back to Field's pioneering Science Without Numbers, 1980. There, Field contrasts intrinsic explanation with extrinsic explanations. He claims that all mathematical explanations are extrinsic, and that for every extrinsic explanation of some target, there's a superior intrinsic explanation of the very target. The explanation championed by Feyerabend, Baker, and others suggests that it's not clear that a mathematical explanation is always extrinsic, or that a non-mathematical explanation that is intrinsic is superior in all respects. Consider again the non-causal explanation of the impossibility of traversing the bridges of Königsberg. While some non-mathematical derivation of these targets is surely available, this does not settle whether or not these derivations should count as explanations or what their explanatory virtue might be. Perhaps the most promising defense of premise 2 would be to provide a positive account of distinctively mathematical explanations that would clarify how endorsing such explanation commits one to the existence of some mathematical objects. The recent literature on this issue again seems to lead to a kind of standoff. Consider, for example, Baron's Pythagorean proposal to these explanations. Baron defines a Pythagorean to be someone who has not only believes in mathematical objects as abstract entities, but who claims that some of the intrinsic properties of these abstract entities are also possessed by concrete entities. This is possible because the salient intrinsic properties of the mathematical entities are structural properties that are found in the concrete world, whenever the concrete entities are arranged in the right structure. These shared structural properties and their necessary mathematical relations thus enable mathematical truths to explain features of physical systems such as bridges or cicadas. In addition, Baron is clear that structural properties, on my account, make indispensable reference to abstract objects, so one defense of premise 2 involves adopting Baron's Pythagoreanism. Other accounts of distinctively mathematical explanations support the rejection of premise 2. For example, Lang's modal interpretation of distinctively mathematical explanations lead him to endorse what he calls an Aristotelian realist interpretation of pure mathematics in terms of a special kind of abstract property without the recourse to any abstract objects. According to Lang, the best way to make sense of the explanatory power of mathematical truths is to suppose that mathematics concerns mathematical properties possessed by physical systems. As with Baron, these mathematical properties can help to explain why these physical systems have some other properties. For Lang, the main benefit of such an Aristotelian interpretation is that the salient modal features of the physical system arise from the presence of the mathematical properties. This helps to clarify in what sense the mathematical truth and the properties it invokes may be explanatorily prior to some target property. Crucially, though, for Lang, this interpretation of pure mathematics eliminates the need to invoke abstract objects. If Lang is right, then premise 2 of the explanatory indispensability argument is false. One diagnosis of the problems with indispensability arguments is that the conclusions of the argument concern the interpretation of pure mathematics, while the premises of the argument consider how mathematics is used in science. Perhaps then a Platonist would be better served by focusing on explanatory considerations that arise within the practice of pure mathematics. Mathematical explanation in mathematics. Much mathematical activity is driven by factors other than establishing that a certain theorem is true. In many cases, mathematics are unsatisfied by merely knowing that mathematical facts hold and reprove it, while also claiming explanatory benefits for the new proof. This type of explanatory activity appears within mathematics itself and thus one often speaks of internal or intro-mathematical explanation. The expression internal mathematical explanation covers a wide range of different phenomena. An internal mathematical explanation could amount to the recasting of an entire area of mathematics, or it might aim at providing explanatory proofs for specific theorems. Amongst these different explanatory activities, most of the attention has been focused on the proofs which not only prove that a theorem is true, but also show why it is true. While there might not be agreement on specific instances, many mathematicians often claim that certain proofs have an explanatory power and that others do not. These claims are found throughout the history of mathematics and the philosophy of mathematics. In the words of Bulligand, most theorems can be given different demonstrations. The most instructive are, of course, those that let one understand the deep reasons of the results that one is establishing. In the real algebraic geometer Gregory Brumfield draws a stark contrast between two different types of proof to be found in real algebraic geometry, what he calls transcendental proofs, proofs based on transfer theorems that infer the truth of a statement for all real closed fields from its truth on a specific real closed field, say the real numbers, versus the type of proof that holds uniformly for all real closed fields. The first type of proof is rejected by Brumfield as non-explanatory, and by contrast, the latter provide explanatory benefits in his words. In this book, we absolutely and unequivocally refuse to give proofs of this type. Transcendental proofs, every result is proved uniformly for all real closed ground fields. Our philosophical objection to transcendental proofs is that they might logically prove a result, but they do not explain it except for a special case of real numbers. As the previous examples show, explanatory proofs could be of several types and explained in different manners. A recent debate has focused on the issue of whether proofs by induction are explanatory. On the one hand, Lang, 2010, argues that proofs by induction are not explanatory. Baker rejects Lang's argument by arguing against the explanatory equivalence between proofs by ordinary mathematical induction and proofs by upward and downward induction. Holtje rejects what they see as unacknowledged assumption in Lang's argument, namely that a universal sentence explains its instances. Daugherty, in 2017, line of attack is based on Lang's need to presuppose a problematic notion of identity on proofs, which he questions using an alternative criterion of identity spelled out using two equivalent characterizations, the first appealing to the language of homotopy type theory and the second using algebraic representatives to proof. Both Baldwin and Leahitt defend the explanatory value of induction in mathematics, while Baldwin offers positive considerations as to why inductive arguments are explanatory. Leahitt dwells on inductive definitions, which he argues might be cases of explanations in mathematics. The distinction between explanatory and non-explanatory proof has also been applied to other types of proof. For instance, proofs that explain by using diagrams or proofs that explain by drawing on analogies. Significant philosophical activity is focused on the proofs that explain by revealing the reasons or the grounds why a theorem is true. As stressed by Lang, in the context, the word ground should not be understood as a connection to recent literature on metaphysical grounding. We should rather think of the notion of conceptual grounding as developed by Smithson in 2020. This notion of ground has an illustrious pedigree in philosophers in mathematics such as Bolzano and Corno, and recent contributions have stressed its value in the mathematical realm. Indeed, just as the scientific literature is widely accepted that causal explanations track a causal relation in the world and explain by revealing the causes of why certain facts hold, it seems reasonable to accept that at least certain mathematical explanatory proofs track a grounding relation of the mathematical realm and thus explained by mentioning the grounds of reasons why a theorem is true. Some historical remarks. Since contributions in the analytical philosophy to the study of mathematical explanations date back only to Steiner, 1978, one might suspect that the topic was a byproduct of the Quinian conception of scientific theories. Once mathematics and natural science were placed on the same footing, it became possible to apply a unified methodology to both areas. Thus, it made sense to look for explanations in mathematics, just as in natural science. However, the historical reconstruction would be mistaken. Mathematical explanations of mathematical facts have been part of philosophical reflection since Aristotle. We have already seen the distinction Aristotle drew between demonstrations of the fact and demonstrations of the reason fact. Both are logically rigorous, but only the latter provide explanations for their result. Aristotle had also claimed that demonstrations of the reason fact occur in mathematics. Only these demonstrations can be called explanatory demonstrations, and some of the demonstrations will be mathematical proofs. Aristotle's position on explanatory proofs in mathematics was already challenged in ancient time. Proclus, in his commentary in the first book of Euclid's Elements, informs us of his point. He reports many persons have thought that geometry does not investigate the cause, that is, does not ask the question why. Proclus himself singles out certain propositions in Euclid's Elements as not being demonstrations of the reason fact. Euclid states that the sum of the internal angles of a triangle is equal to two right angles. If the demonstration were given by a scientific syllogism in the Aristotelian sense, the middle of the syllogism would have to provide the cause of the fact. But Proclus argues that Euclid's proof does not satisfy these Aristotelian constraints, for the appeal to the auxiliary lines and exterior angles is not causal. What is called proof, we shall find, sometimes has the properties of a demonstration in being able to establish what is sought by means of definitions as middle terms. And this is the perfect form of demonstration, but sometimes in attempts to prove by means of science, this point should not be overlooked. Although geometric propositions always derive their necessity from the matter under investigation, they do not always reach their results through demonstrative methods. For example, when from the fact that the exterior area of a triangle is equal to two opposite interior angles, it is shown that the sum of the interior angles of a triangle is equal to the two right angles. How can this be called a demonstration based on the cause? Is not the middle term used here only a sign? For even though there be no exterior angle, the interior angles are equal to two right angles, for it is a triangle even if the side is not extended. In addition, Proclus has also held that proofs by contradiction were not demonstrations of the reason fact. The rediscovery of Proclus in the Renaissance was to spark a far-reaching debate on the causality of mathematical demonstrations, referred to above as the Quesito de Certitudine Mathematicarum. The first shot was fired by Alessandro Piccolomini in 1547. Piccolomini's aim was to disarm the traditional claim that the effect that mathematics derives its certainty on account of its use of scientific demonstrations. In the Aristotelian sense, such proofs were known as potestime in the Renaissance. Since potestime demonstrations had to be causal, Piccolomini attacked the argument by arguing that mathematical demonstrations are not causal. This led to one of the most interesting epistemological debates of the Renaissance and the 17th century. Those denying the causality of mathematical demonstration argued by providing some specific examples of demonstrations from mathematical practice, usually from Euclid's Element, which they claimed could not be reconstructed as causal reasonings in the Aristotelian sense. By contrast, those hoping to restore causality to mathematics aimed at showing that the alleged counterexamples could easily be accommodated within the realm of causal demonstrations. Interesting, both positions in the debate assumed that mathematical proofs could be syllogized. What is more important here is to appreciate that the basic intuition, the contraposition between explanatory and non-explanatory demonstrations, had a long and successful history that has influenced both mathematical and philosophical developments well beyond the 17th century. For instance, Mancuso, 1999, shows that Bolzano and Corno, two major philosophers of mathematics in the 19th century, construe the central problem of philosophy of mathematics as that of accounting for the distinction between explanatory and non-explanatory demonstrations. In the case of Bolzano, this takes the form of a theory of Grund and Folge, ground and consequence. Kitcher, 1975, was the first to read Bolzano as propounding a theory of mathematical explanations. In the case of Corno, this is spelled out in terms of the opposition between order logic and order rationale. In Bolzano's case, the aim of providing a reconstruction of parts of analysis in geometry so that the exposition would use only explanatory proofs also led to major mathematical results, such as his purely analytical proof of the intermediate value theorem. In conclusion to the section, we should also point out that there is another tradition of thinking of explanation in mathematics that includes Mill, Lakatos, Russell, and Gödel. These authors are motivated by a conception of mathematics and or its foundations as hypothetical deductive in nature, and this leads them to construe mathematical activity in analogy with how explanatory hypotheses occur in science. Models of mathematical explanation. From the above, it should be obvious that Both philosophers and mathematicians have appealed to the notion of explanation within mathematics, and that amongst the different contexts in which such explanatory activity appears, proofs play a special role. But what distinguishes a proof that explains from one that doesn't? How should one proceed in providing an account of explanatory proof? It is here that two possibilities emerge. On the one hand, one can follow a top-down approach where one starts with a general model of explanatory proof and then tries to see how well it counts for the practice. On the other hand, one can embrace a bottom-up approach where one begins by avoiding as much as possible any commitment to a particular theoretical framework. Only afterward one attempts to provide a taxonomy of recurrent types of mathematical explanatory proofs and tries to see whether these patterns are heterogeneous or can be subsumed under a general account. Supporters of the bottom-up approach include Hafner and Mancuso, 2005, and Lang, 2008. Probably the main characteristics of their investigation is the extremely rich and varied set of examples considered precisely in virtue of this variety. Lang argues that there is no general pattern characterizing explanatory proofs. At most, one can claim that there are different classes of explanatory proofs. Lang proposes several salient features of mathematical theorems, which in different contexts are responsible in those contexts for the distinction between explanatory and non-explanatory proofs. Among them, he discusses extensively symmetry and simplicity. As for simplicity, it amounts to the requiem for a proof of a simple result, exploits some similar simple feature of the setup. As for symmetry, it is a property that arises when dealing with mathematical results that displays some striking symmetry for the proof to count as explanatory. It needs to show how such symmetry follows from a similar symmetry in the setup of the problem. Lang defends these properties by using case studies drawn from probability, real analysis, number theory, complex numbers, and geometry, among other areas of mathematics. One of the most representative is the proof of d'Albert's theorem to the effect that a polynomial equation of the nth degree in the variable x and having only real coefficients, the non-real roots always come in pairs. Any non-real root and its complex conjugate will both satisfy the equation. What explains the symmetry? A non-explanatory proof can be given by algebraic manipulations, but this does not reveal the reason for the result, which, according to Lang, is the fact that the axioms of the complex arithmetic are invariant under substitutions for I and negative I. Bueno and Vavenko, 2019, point out that it's unclear why Lang isolates as the symmetric feature of the proof, which makes it explanatory, is a symmetry at all. They suggest that this proof turns on an appropriate feature of the relevant structure. Top-down approaches take their start from a general theory of mathematical explanation and then explore how well the practice fits the model. A typical example of a top-down approach in mathematical explanation is Kitcher's unificationist theory, but one can also apply this description to overarching views of the nature of explanation. While there are several examples one could mention, here we present an influential proposal that finds its origin in Kim, 1994. In order to classify the different accounts of scientific explanation, Kim uses the contraposition between explanatory internalism and explanatory externalism, whereas for explanatory internalism, explanations are activities internal to the epistemic corpus, a theory or set of beliefs, and explanatory externalists will look for some systematic pattern or of objective dependence relations which explanations track or can be identified with. We divide the present section into two subsections that follow this division. One will be dedicated to the presentation of the externalist or ontic accounts of explanatory mathematical proofs, while the other to the internalist or epistemic ones. Among the externalist accounts, we will discuss Steiner's theory, several counterfactual theories of mathematical explanation, and some other proposals. Among the internalist accounts, we will discuss Kitcher's theory, together with two novel ones proposed by Franz in 2021 and English and Mejia Ramos, 2019. Externalist models of mathematical explanation. Among the several existing contemporary externalist models of explanatory proofs, the oldest and probably most well-known is Steiner's account. Steiner aims at finding criteria that could characterize explanatory proofs after having discussed several possible criteria such as abstractness, generality, and visuality. Steiner rejects them all in favor of the idea to explain the behavior of an entity. One deduces the behavior from the essence of or nature of the entity. Although such an idea could seem prima facie intuitive and interesting, it turns out to be quite problematic. First, it leads to the notorious difficulties linked to the concepts of essence or essential property. Moreover, such concepts risk having little traction in a mathematical context, since all mathematical truths are regarded as necessary. Hence, instead of talking of essence, Steiner speaks of characterizing properties, by which he means a property unique to a given entity or structure within a family or domain of such entities or structures, where he takes the notion of a family as undefined. In other words, for Steiner, the difference between explanatory and non-explanatory proofs lie in the characterizing properties, which are found only in the former, but not by the latter. However, this is not all. An explanatory proof needs to be generalizable as well, varying the relevant features, and hence a certain characterizing property in such a proof needs to give rise to an array of corresponding theorems, which are proved and explained by an array of deformations of the original proof. There have been two extensive critical discussions of Steiner's account. The first was provided by Resnick and Kushner in 1987, who argued that the distinction between explanatory and non-explanatory proof is context dependent. The second, which also offers a counterexample to the theory based on the case of explanation from real analysis recognized as such in mathematical practice, has been developed by Hafner and Mancuso, 2005. There have also been attempts to improve Steiner's model. The work developed by Weber and Verhoeven, 2002, can, for example, be seen as an attempt to improve Steiner's notion of deformation. Indeed, while Steiner suggests that explanation concerns an array of related proofs and theorems, although maintaining that each proof is an explanation of the individual theorem, Weber and Verhoeven start with what makes pairs of proofs P1 and P2 count as explanatory. In particular, they focus on explaining why, while a certain class of object X has a property Q, proof 1, another class of objects Y enjoys property Q prime. Proof 2, here P1 and P2 use the same axioms and the same logical rules, while both P1 uses a characterizing property of X, but not of Y. P2 uses a characterizing property of Y, but not of X. Final attempt to enrich Steiner's account is proposed by Salverda, 2017, who tries to adapt this approach to an internalist perspective on explanations. In the field of causal explanations, a dominant perspective has been formulated in counterfactual terms, although there has long been resistance to the use of counterfactuals to account for explanations in mathematics. Many authors adopt this approach, perhaps due to the attractiveness of a unified theory of explanation that promises to hold in both causal and non-causal contexts. Once the counterfactuals are specified, the theory for counterfactuals needs to make clear what truth conditional account of counterfactuals is adopted. Here, at least two options naturally emerge. On the one hand, one can evaluate a counterfactual using possible world semantics. For example, Lewis's closedness-based semantics, which trivializes for mathematical counterfactuals, has recently been extended to avoid these trivialities. Both Rittlinger, 2022, and Barron, 2020, support a counterfactual theory of explanation that is mainly discussed in the possible world semantics framework. More precisely, while Rittlinger defends the value of a monist theory of explanation, Barron exemplifies the counterfactual approach to mathematical explanation with the real case of explanatory proof. Gispers, 2017, develops a counterfactual account of explanatory proofs, which relies on the structural equation framework, but where the notion of intervention, although Woodward, cannot be employed in the mathematical context, as Woodward emphasizes intervention is a causal change to the value of a variable. Instead, Gispers introduces the idea of a quasi-interventionist theory of mathematical explanation. In this theory, quasi-interventions reveal asymmetries, which are inherent not in the mathematical proofs, but in the mathematical practice. In other words, asymmetries are no longer accounted for in objective, but rather in a more subjective way that is tied to the features of the practice in question. In a sense, Gispers' model is complementary to the one proposed by Franz and Weber, 2014. Indeed, while Gispers' account for the explanatory power of proofs is in counterfactual terms without using a notion of intervention, Franz and Weber account for the explanatory power of proofs with mechanistic model of explanation that directly generalizes on Woodward's notion of an intervention. The use of counterfactuals to model mathematical explanations has been criticized by Kazurazada, 2021, and Lang, 2022, while Kazurazada questions whether the explanums of an explanatory proof can be meaningfully varied in a mathematical context, as the counterfactual accounts would require. Lang argues instead that counterfactual account is rather threatened by the existence of too many non-trivially true counter-mathematicals. Both Kazurazada and Lang emphasize that the capacity to answer what if things had been different questions does not correlate with explanatory power in mathematics. Finally, note is that Jansen 2018, one might find criticisms of the use of the structural equations framework to model dependence relations other than causation, and thus arguably also dependence relations in mathematical contexts. Not all externalist models for mathematical explanations are modifications of Steiner's theory or conveyed in counterfactual terms. Pincock, for example, proposes to classify a proof as explanatory when it invokes more abstract kinds of entities than the topic of the theorem it proves. Wilhelm and Puglisi 2021 contain different proposals for the analysis of explanatory proofs that are similar in perspective to Pincock's approach. In their cases, that the determination of the explanatory power of different proofs requires a formalization of the proofs in logical systems. While for Wilhelm, the explanatory power of proof comes from the balance between the simplicity and the depth of the formalized proof. Puglisi distinguishes an explanatory proof from a non-explanatory one in that only in the formalized version of the former, one can witness an increase of conceptual complexity from the assumptions to the theorem the proof aims to establish. Internalist models of mathematical explanation. In a paper of 1974, Friedman posed a challenge for any coherent account of scientific and thus presumably also mathematical explanation. He argued that any such account needed to show how explanation generates understanding. I don't see how the philosophy of science can afford to ignore such concepts as understanding and intelligibility when giving a theory of the explanation relation. Well, externalist or ontic accounts do not directly concern themselves with Friedman's challenge. They do not deny the link between explanation and understanding. However, they simply do not pose understanding as a defining characteristic of explanation. By contrast, internalist or epistemic accounts are those which directly address this challenge. In the philosophy of science, one of the main conceptions of scientific understanding is the unificationist model, which argues that explanations provide understanding by unifying different phenomena. Although the idea is undoubtedly intuitively appealing, the key question is whether the notion of unification can be made more precise so that we can distinguish between what an explanation is and what is not. Friedman, 1974, is an early attempt to do this, although his formulation was quickly shown to suffer from several technical problems. Kitcher is, on the other hand, the main supporter of the unificationist approach. His proposal consists in looking at unification as the reduction of the number of argument patterns used in providing explanations while being as comprehensive as possible in the number of phenomena explained. Understanding the phenomenon is not simply a matter of reducing the fundamental incomprehensibilities, but of seeing connections, common patterns in what initially appeared to be different situations. Here, the switch in conception from premise conclusion pairs to derivations proves vital. Science advances our understanding of nature by showing us how to derive descriptions of many phenomena using the same pattern of derivation again and again. And in demonstrating this, it teaches us how to reduce the number of types of facts that we have to accept as ultimate or brute, so that the criterion of unification I shall try to articulate will be based on the idea that a set of derivations that makes the best trade-off between minimizing the number of patterns of derivation employed and maximizing the number of conclusions generated. Let us make this a little bit more formal. Let us start with a set K of beliefs assumed to be consistent and deductively closed. Informally, one can think of this as a set of statements endorsed by an ideal scientific community at a specific moment in time. A systemization of K is any set of arguments that derive from some sentences in K from other sentences of K. The explanatory store over K, E of K, is the best systemization of K. Kitcher here makes an idealization by claiming that the explanatory store is unique. Corresponding to a different systemization, we have different degrees of unification. The highest degree of unification is given by the explanatory store, but according to what criterion can a systemization be judged to be the best? There are three factors: the number of patterns, the stringency of the pattern, and the set of consequences derivable from the unification. Two remarks are in order when it comes to Kitcher's proposal. First, his account of theoretical unification is mainly thought for the general question of scientific explanation, although he sees it as one of the virtues of his viewpoint to be extendable to mathematics as well. Secondly, Kircher's model is not meant to address local questions of what distinguishes an explanatory proof from one that does not explain, as all other accounts do. It rather provides a novel perspective on the global question of how to systematize a whole body of knowledge that has explanatory value. The application of Kircher's model to explanatory proofs has been explored in two opposite directions. On the one hand, Hafner and Mancuso 2008 tested Kircher's model with three different methods to prove theorems about real closed fields. The authors showed that the model makes predictions about the explanatory powers of these methods, which contradicts judgments coming out from the mathematical practice. On the one hand, Franz 2021 not only reassesses the value of unificatory understanding, which is a type of explanatory understanding for mathematics. Additionally, he shows through a plethora of different examples ranging from Pythagoras' theorem to the theorem that states that the sum of the first n integers equals n times n plus 1 divided by 2, that proofs can contribute to unificatory understandings. A novel internalist account has been proposed by Inglis and Major-Romas 2019, who apply Wilkenfeld's functional model of understanding to the mathematical case. Wilkenfeld's approach consists in reversing Friedman's perspective. While Friedman demanded that philosophers clarify how explanations suitably defined generate understanding, Wilkenfeld defines explanations as those things that generate understanding. By doing so, Wilkenfeld moves the burden of clarification from the notion of explanation to that of understanding and how it is generated. This move, he argues, has recently become tenable as philosophical accounts of understanding have become more and more sophisticated. In Inglis and Major-Romas 2019, the conception of understanding adopted is that of Kelp in 2016, along with a modal model of the generation of understanding. With these two elements at hand, Inglis and Major-Romas identified three properties that any mathematical explanatory proof is likely to have. An explanatory proof would direct the reader's attention to its conceptually important section. It would reorganize the new existing information into a coherent new schema. It would reduce the chance of working memory capacity to be exceeded. Some connections to other debates. A number of fruitful studies have recently appeared connecting mathematical explanation to mathematical beauty, purity of methods, understanding of mathematics, mathematical style, and mathematical depth. We simply refer to one or two such background studies and encourage the reader to explore the bibliography of the studies referred to. The most extensive studies connecting mathematical beauty and explanation are Giaquinto 2016 and Lang. The notion of purity as method has long been an interest to mathematics and philosophers. The issues that have shaped the debates about mathematical explanation also arise in ongoing debates in the philosophy of mind and moral theory. For the philosophy of mind, one puzzle is how appealing to mental properties can explain human actions, even though human is a physical entity. If non-mental physical properties are apt to explain any physical event or pattern of physical events, then it seems that mental properties are disposable as epiphenomenal. For moral theory, a series of questions arise as how moral properties relate to presumably non-moral features of the physical world. In terms of explanation, it seems like there is no explanatory work for moral properties to do, at least with respect to physical events. However, ordinary practices frequently appeal to these properties as imputative explanation. So, as with the philosophy of mind, it seems that we must either revise our explanatory practice or else find a place for these properties in a more comprehensive conception of reality. Kim's exclusion argument is a prominent driver of these debates. In the philosophy of mind, Kim argues that the existence of mental properties requires that these properties provide some genuine contribution to the explanation of physical events. However, Kim maintains that mental properties are excluded from this contribution by the causal closure of the physical. Every physical event has a purely physical explanation. Our response to Kim is that the right conception of causal explanation makes space for mental properties to explain. The explanatory autonomy of the mental can thus be obtained in a way that parallels similar generalizations of causal explanation to allow for genuine mathematical explanations of physical phenomena. Pluralists about mathematical explanation can develop a different response to exclusion arguments. If explanations come in different kinds, then an explanation of one kind does not stand in the way of explanation of another kind. Baker 2022 has pursued a different kind of response that compares Dennett's intentional stance with the mathematical stance that enables mathematical explanations of physical phenomena. Herman and Street have advanced explanatory challenges to moral properties that can be fruitfully compared to criticisms of the explanatory indispensability argument for mathematical Platonism. Will Harman focuses on the explanation of moral observations. Street emphasizes a broader concern with explaining other phenomena such as the prevalence of some moral judgment. For both, the challenge is that the best explanation does not involve moral properties. That is, moral properties are explanatorily dispensable for the targets in question. As Sinclair and Leibowitz emphasize, this argument and the responses to it parallel debates about the explanatory dispensability of mathematical objects. One innovation of the debate about moral properties is Enoch's argument that it is sufficient for moral properties to be indispensable to practical deliberation. If this non-Quinean condition for ontological commitment is granted, then it may be feasible to identify new forms of explanatory indispensability for mathematical objects. Okay, so there you have it. So, yeah, thanks, Mr. Boston and Luke, for being active in the chat. So a lot of information there, and a lot of stuff to get through. You know, a lot of stuff to return to. The role of mathematics is definitely going to be a big part in the future of the research and logic. When we get into the metaphysics, but good introduction to some of these basic mathematical theories and the relationship of mathematical explanation to scientific explanation. Mr. Boston, when we get into the metaphysics, we'll talk extensively about Platonism and other aspects. Okay, so let me take a 2-minute break. I'm just going to get another drink, use the restroom, say Kriya Shema. Okay, so let's keep it going. And now we're going to look at scientific objectivity. So we're really covering all of the bases here. So like after today, we'll have covered almost all of the main aspects of the philosophy of science. So we just looked at explanation. Now let's talk about objectivity. Scientific objectivity. Scientific objectivity is a property of various aspects of science. It expresses the idea that scientific claims, methods, results, and scientists themselves are not or should not be influenced by particular perspectives, value judgments, community bias, or personal interest, to name a few relevant factors. Objectivity is often considered to be an ideal for scientific inquiry, a good reason for valuing scientific knowledge, and the basis of the authority of science in society. Many central debates in the philosophy of science have, in one way or another, to do with objectivity: confirmation in the problem of induction, theory choice and scientific change, realism, scientific explanation, experimentation, measurement and quantification, statistical evidence, reproducibility, evidence-based science, feminism, and values in science. Understanding the role of objectivity in science is therefore integral to a full appreciation of these debates. As this article testifies, the reverse is true too. It is impossible to fully appreciate the notion of scientific objectivity without touching upon many of these debates. The idea of objectivity has been criticized repeatedly in the philosophy of science, questioning both its desirability and its attainability. This article focuses on the question of how scientific objectivity should be defined, whether the ideal of objectivity is desirable, and to what extent scientists can achieve it. Introduction. Objectivity is a value. To call something objective implies that it has certain importance to us and that we approve of it. Objectivity comes in degrees. Claims, methods, results, and scientists can be more or less subjective, and other things being equal, the more objective, the better. Using the term objective to describe something often carries a special rhetorical force with it. The admiration of science among the general public and the authority science enjoys in public life stems to a large extent from the view that science is objective, or at least more objective than other modes of inquiry. Understanding scientific objectivity is therefore central to understanding the nature of science and the role it plays in society. If what is so great about science is its objectivity, then objectivity should be worth defending. The close examinations of scientific practice that philosophers of science have undertaken in the past 50 years have shown, however, that several conceptions of the ideal of objectivity is either questionable or unattainable. The prospects for science providing a non-perspectival view from nowhere, or for proceeding in a way uninformed by human goals and values, is fairly slim. This article discusses several proposals to characterize the idea and ideal of objectivity in such a way that it is both strong enough to be valuable and weak enough to be obtainable and workable in practice. We begin with a natural conception of objectivity, faithfulness to facts. We motivate the intuitive appeal to this conception, discuss its relationship to scientific method, and discuss arguments challenging both its attainability as well as its desirability. We then move on to a second conception of objectivity as absence of normative commitments and value freedom. And once more, we contrast arguments in favor of such a conception with the challenges it faces. A third conception of objectivity, which we discuss at length, is the idea of absence of personal bias. Finally, there's the idea that objectivity is anchored in scientific communities and their practices. After discussing 3 case studies from economics, social sciences, and medicine, we address the conceptual unity of scientific objectivity. Do the various conceptions have a common valid core, such as promoting trust in science or minimizing relevant epistemic risk? Or are they rivaling in only loosely related accounts? Finally, we present some conjectures about what aspects of objectivity remain defensible and desirable in the light of the difficulties we have encountered. Objectivity as faithfulness to facts. The basic idea of the first conception of objectivity is that scientific claims are objective insofar as they faithfully describe facts about the world. The philosophical rationale underlying this conception of objectivity is the view that there are facts out there in the world and that it is the task of scientists to discover, analyze, and systematize these facts. Objective then becomes a success word. If a claim is objective, it correctly describes some aspect of the world. In this view, science is objective to the degree that it succeeds in discovering and generalizing facts, abstracting from the perspective of the individual scientist. Although few philosophers have fully endorsed such a conception of scientific objectivity, the idea figures recurrently in the work of prominent 20th century philosophers of science such as Carnap, Hempel, Popper, and Reichenbach. The view from nowhere. Humans experience the world from a perspective. The contents of an individual's experience vary greatly with his perspective, which is affected by his personal situation and the details of his perceptual apparatus, language, and culture. While the experiences vary, there seems to be something that remains constant. Examples motivate a distinction between qualities that vary with one's perspective and qualities that remain constant through changes of perspective. The latter are the objective qualities. Thomas Nagel explains that we arrive at the idea of objective quantities in three steps. The first step is to realize or postulate that our perceptions are caused by the actions of things around us through their effects on our bodies. The second step is to realize or postulate that since the same qualities that cause perceptions in us also have effects on other things and can exist without causing any perceptions at all. Their true nature must be detachable from their perspectival appearances and need not resemble it. The final step is to form a conception that the true nature independently of any perspective. Nagel called that conception the view from nowhere. Bernard Williams, the absolute conception. It represents the world as it is, unmediated by human minds and other distortions. That this absolute conception lies at the basis of scientific realism, and it is attractive insofar as it provides a basis for arbitrating between conflicting viewpoints, two different observations. Moreover, the absolute conception provides a simple, ununified account of the world. To the extent that the science aims to provide explanations for natural phenomena, casting them in terms of the absolute conception would help to realize this aim. As Williams puts it, the absolute conception non-vacuously explains how it itself and the various perspectival views of the world are possible. The third reason to find the view from nowhere attractive is that if the world came in structures as characterized by it and we did have access to it, we could use our knowledge of it to ground predictions, which to the extent that our theories do track the absolute structures will be borne out. A fourth and related reason is that attempts to manipulate and control phenomenon can similarly be grounded in our knowledge of these structures to attain any of the four purposes: settling disagreements, explaining the world, predicting phenomenon, and manipulation and control. The absolute conception is at best sufficient but not necessary. We can explain the world and our image of it by means of theories that do not represent absolute structures and properties, and there is no need to get things absolutely right in order to predict successfully. Nevertheless, there is something appealing in the idea that factual disagreements can be settled by the very facts themselves, that explanations and predictions grounded in what's really there rather than in a distorted image of it. No matter how desirable our ability to use scientific claims to represent facts about the world depends on whether these claims can unambiguously be established on the basis of evidence and of evidence alone. Alas, the relation between evidence and scientific hypothesis is not straightforward. We'll look at two challenges of the idea that even the best scientific method will yield claims that describe an aperspectival view from nowhere, and we'll deal with socially motivated criticisms of this view from nowhere. Theory-latedness and incommensurability. According to the popular picture, all scientific theories are false and imperfect. Yet, as we add true and eliminate false beliefs, our best scientific theories become more truth-like. If this picture is correct, then scientific knowledge grows by gradually approaching the truth, and it will become more objective over time. That is, more faithful to facts. However, scientific theories often change, and sometimes several theories compete for the place of the best scientific account of the world. It is inherent in the above picture of scientific objectivity that observation can, at least in principle, decide between competing theories. If they did not, the conception of objectivity as faithfulness would be pointless to have, as we would not be in a position to verify it. This position has been adapted by Karl Popper and Rudolf Carnap and other leading figures in broadly empiricist philosophy of science. Many philosophers have argued that the relationship between observation and theory is way more complex and that influences can actually run both ways. The most lasting criticism, however, was delivered by Thomas Kuhn in his book, The Structure of Scientific Revolution. Kuhn's analysis is built on the assumption that scientists always view research problems through a lens of a paradigm defined by a set of relevant problems, axioms, methodological presuppositions, techniques, and so forth. Kuhn provided several historical examples in favor of the claim scientific progress and the practice of normal everyday science happens within a paradigm that guides the individual scientist's puzzle-solving work and that sets the community standards. Can observations undermine such a paradigm and speak for a different one? Here, Kuhn famously stresses that observations are theory-laden. They depend on a body of theoretical assumptions through which they are perceived and conceptualized. This hypothesis has two important aspects. First, the meaning of observational concepts is influenced by theoretical assumptions and presuppositions. In other words, Kuhn denies that there is theory-independent observation language. The faithfulness to reality of an observation report is always mediated by a theoretical Überbau, disabling the role of observation reports as an impartial, merely fact-dependent arbiter between different theories. Second, not only the observational concepts, but also the perception of a scientist depend on the paradigm he is working in. Practicing in different roles, the two groups of scientists who work in different paradigms see different things when they look from the same point in the same direction. That is, their own sense data are shaped and structured by a theoretical framework and may be fundamentally distinct from the sense of data of scientists working in another one. If this picture is correct, then it is hard to assess which theory or paradigm is more faithful to the facts, that is more objective. The thesis of theory-ladenness of observation has also been extended to the incommensurability of different paradigms of scientific theories problematized independently by Thomas Kuhn and Paul Feyerabend in 1962. Literally, this concept means having no measure in common, and it figures prominently in arguments against linear and standpoint independent pictures of scientific progress. The picture is undetermined, however, by two central aspects of incommensurability. First, not only do observational concepts in both theories differ, but in principles for specifying their meaning may be inconsistent with each other. Second, scientific research methods and standards of evaluation change with the theories or paradigms. Not all puzzles that could be tackled in the old paradigm will be solved by the new one. This is the phenomenon of Kuhn loss. A meaningful use of objectivity presupposes, according to Feyerabend, to perceive and to describe the world from a specific perspective when we try to verify the referential claims of a scientific theory. Only within a particular scientific worldview, the concept of objectivity may be applied meaningfully. That is, a scientific method cannot free itself from the particular scientific theory to which it is applied. The door to standpoint independence is locked, as Feyerabend puts it. Our epistemic activities may have a decisive influence even upon the most solid piece of cosmological furniture. They make gods disappear and replace them by heaps of atoms in empty space. Kuhn and Feyerabend's thesis about theory-latedness of observation and their implications for the objectivity of scientific inquiry have been much debated afterwards and have often been misunderstood in a social constructivist sense. Therefore, Kuhn later returned to the topic of scientific objectivity, of which he gives his own characterization in terms of the shared cognitive values of a scientific community. Underdetermination, values, and the experimenters regress. Scientific theories are tested by comparing their implications with the results of observation and experiments. Unfortunately, neither positive results when the theory's predictions are born out of data, nor negative results when they are not allow unambiguous inferences about the theory. A positive result can obtain even though the theory is false due to some alternative that makes the same prediction. A negative result might be due not to the falsehood of the theory under test, but due to the failing of one of the more auxiliary assumptions needed to derive the prediction from the theory. As any of these may be false, explaining an inconsistency, the locus classica for the observation is Pierre Duhem's The Aim and Structure of Physical Theory. Duhem concluded that there was no crucial experiment, an experiment that conclusively decides between two alternative theories in physics, and the physicists had to employ their expert judgment, or what Duhem called good sense, to determine what an experimental result means for the truth or falsehood of a theory. In other words, there is a gap between evidence and the theory supported by it. It is important to note that the alleged gap is more profound than the gap between the premises of any inductive argument and its conclusion. The latter gap could be bridged by an agreed-upon rule of inductive reasoning. Alas, all attempts to find an analogous rule for theory choice have failed. Various philosophers, historians, and sociologists of science have responded that theory appraisal is a complex form of value judgment. Below, we will discuss the nature of value judgments in more detail. For now, the important lesson is that if these philosophers, historians, and sociologists are correct, the faithfulness to facts ideal is unattainable, as the scientific image of the world is a joint product of the facts and scientists' value judgment. That image cannot be said to be aperspectival. Science does not eschew the human perspective. There are, of course, ways to escape his conclusion. If, as John Norton has argued, it is material facts that power and justify inductive inferences and not value judgments, we can avoid the negative conclusion regarding the view from nowhere. Unsurprisingly, Norton is also critical of the idea that evidence generally undetermines theory. However, there are good reasons to mistrust Norton's optimism regarding the eliminability of values and other non-factual elements in inductive inference. There is another closely related concern. Most of the early critics of objective verification or falsification focused on the relationship between evidence and scientific theories. There is a sense in which the claim that this relationship is problematic is not so surprising. Scientific theories contain highly abstract claims that describe states of affairs far removed from the immediacy of sense experience. This is for good reason. Sense experience is necessarily perspectival. So to the extent to which scientific theories are to track the absolute conception, they must describe a world different from that of sense experience. But surely one might think the evidence itself is objective. So even if we do have reasons to doubt that abstract theories faithfully represent the world, we should stand on firmer grounds when it comes to the evidence against which we test abstract theories. Theories are seldom tested against brute observations. However, simple generalizations are directly learned from observation, but they do not represent the view from nowhere. Genuine scientific theories are tested against experimental facts or phenomenon, which are themselves unobservable to the unaided senses. Experimental facts or phenomenon are instead established using intricate procedures of measurement and experimentation. We therefore need to ask whether the results of scientific measurement and experiments can be perspectival. An important debate from the 1980s and 90s. Some commentators answered the question with a resounding no, which was then rebutted by others. The debate concerns the so-called experimenter's regress. Collins, a prominent sociologist of science, claims that in order to know whether an experimental result is correct, one first needs to know whether the apparatus producing the result is reliable. But one does not know whether the apparatus is reliable unless knows that it produces correct results in the first place, and so on ad infinitum. Collins argues that the circle is eventually broken not by the facts themselves, but rather by factors having to do with the scientist's career, the social and cognitive interest of his community, and the expected faithfulness for future work. It is important to note that in Collins' view, these factors do not necessarily make scientific results arbitrary, but what he does argue is that experimental results do not represent the world according to the absolute conception. Rather, they are produced jointly by the world scientific apparatus and the psychological and sociological factors mentioned above. The facts and phenomena of science are therefore necessarily perspectival. In a series of contributions, Alan Frankel, physicist turned philosopher of science, has tried to show that while there are indeed no algorithmic procedures for establishing experimental facts, disagreements can nevertheless be settled by reason's judgment on the basis of bona fide epistemological criteria, such as experimental checks and calibrations, elimination of possible sources of error, using apparatuses based on well-collaborated theory, and so on. Collins responds that reasonableness is a social category that is not drawn from physics. The main issue for us in this debate is whether there are any reasons to believe that experimental results provide an aperspectival view on the world. According to Collins, experimental results are co-determined by the facts as well as social and psychological factors. According to Franklin, whatever else influences experimental results other than facts is not arbitrary, but instead based on reasoned judgment. What he has not shown is that reasoned judgment guarantees that experimental results reflects the facts alone and are therefore aperspectival in any interesting sense. Another important challenge for the aperspectival account comes from the feminist epistemology and other accounts that stress the importance of the construction of scientific knowledge through epistemic communities. Yeah, thanks a lot, Mr. Boston. God bless. And thanks for joining Discord. Objectivity as absence of normative commitments and the value-free ideal. In the previous section, we have presented arguments against the view of objectivity as faithfulness to the facts and an impersonal view from nowhere. An alternative view is that science is objective to the extent that it is value-free. Why would we identify objectivity with value freedom or regard the latter as a prerequisite for the former? Part of the answer is empiricism. If science is the business of producing empirical knowledge, and if differences about value judgments cannot be settled by empirical means, value should have no place in science. In the following, we will try to make this intuition more precise. Epistemic and contextual values. Before addressing what we will call the value-free ideal, it will be helpful to distinguish four stages at which values may affect science. They are the choice of scientific research problem, the gathering of evidence in relationship to the problem, the acceptance of a scientific hypothesis or theory as an adequate answer to the problem on the basis of evidence, and the proliferation and application of the scientific research results. Most philosophers of science would agree that the role of values in science is contentious only with respect to the second and third dimension, the gathering of evidence, the acceptance of scientific theories. It is almost universally accepted that the choice of research problem is often influenced by interest of individual scientists, funding parties, and society as a whole. The influence may make science more shallow and slow down its long-run progress. But it has benefits too. Scientists will focus on providing solutions to those intellectual problems that are considered urgent by society and that may actually improve people's lives. Similarly, the proliferation and application of scientific research results is evidently affected by the personal values of journal editors and end users, and little can be done about this. The real debate is about whether or not the core of scientific reasoning, the gathering of evidence, and the assessment and acceptance scientific theories is and should be value-free. We have introduced the problem of the underdetermination of theory by evidence above. The problem does not stop, however, at values being required for filling the gap between theory and evidence. A further complication is that these values can conflict with each other. Consider the classical problem of fitting a mathematical function to a data set. The researcher often has the choice between using a complex function, which makes the relationship between the variable less simple but fits the data more accurately, or postulating a simple relationship that is less accurate. Simplicity and accuracy are both important cognitive values, and trading them off requires careful value judgment. However, philosophers of science tend to regard value-latedness in this sense as benign. Cognitive values, sometimes also called epistemic or constitutive values, such as predictive accuracy, scope, unification, explanatory power, simplicity, and the coherence with other accepted theories, are taken to be indicative of the truth of the theory and therefore provide reasons for preferring one theory over another. Kuhn, 1977, even claimed that cognitive values define the shared commitments of science, that is, the standards of theory assessment that characterize the scientific approach as a whole. Note that not every philosopher entertains the same list of cognitive values. Subjective differences in ranking and applying cognitive values do not vanish, a point Kuhn made empathetically. In most views, the objectivity of and authority of science is not threatened by cognitive values, but only by non-cognitive and contextual values. Contextual values are moral, personal, social, political, and cultural values that are pleasure, justice, and equality, conservation of the natural environment, and diversity. The most notorious cases of improper uses of such values involve travesties of scientific reasoning, where the intrusion of contextual values led to an intolerant and oppressive scientific agenda with devastating epistemic and social consequences. This preference bias, defined by Will Holt in 2009 as the infringement of conventional standards of the research community within the aim of arriving at a particular result, is clearly epistemically harmful. It seems desirable that research scientists assess theories without being influenced by such consideration. This is the core idea of the value-free ideal. Scientists should strive to minimize the influence of the contextual values on scientific reasoning in gathering evidence and assessing accepting scientific theories. According to the value-free ideal, scientific objectivity is characterized by absence of the contextual values and by exclusive commitment to the contingent values in stages 2 and 3 of the scientific process. For value freedom to be a reasonable ideal, it must not be the goal beyond reach and be attainable at least to some degree. This claim is expressed by the value neutrality thesis. Scientists can, at least in principle, gather evidence and accept theories without making contextual value judgments. Unlike the value-free ideal, the value neutrality thesis is not normative. It is the subject is whether the judgments that scientists make are or could possibly be free of contextual values. Similarly, Hugh Lacey, 1999, distinguishes three principal components or aspects of value-free science: impartiality, neutrality, and autonomy. Impartiality means that theories are solely accepted or appraised in virtue of their contribution to the cognitive values of science, such as truth, accuracy, or explanatory power. This excludes the influence of contextual values as stated above. Neutrality means that scientific theories make no value statements about the world. They are concerned with what there is, not with what there should be. Finally, scientific autonomy means that the scientific agenda is shaped by the desire to increase scientific knowledge and that contextual values have no place in the scientific method. These three interpretations of value-free science can be combined with each other or used individually. All of them, however, are subject to criticisms that we examine below. Denying the value neutrality thesis or the attainability of Lacey's three criteria for value-free science poses a challenge for scientific objectivity. One can either conclude that the ideal or objectivity should be rejected or develop a conception of objectivity that differs from the value-free ideal. Acceptability of scientific hypotheses and value neutrality. Lacey's characterization of the value-free science and the value neutrality thesis were once mainstream positions in the philosophy of science. Their widespread acceptance was closely connected to Reichenbach's famous distinction between context of discovery and context of justification. Reichenbach first made this distinction with respect to the epistemology of mathematics, the objective relation from the given entities to the solution, and the subjective way of finding it are clearly separated for problems of a deductive character. We must learn to make the same distinction for the problem of the inductive relation from facts to theories. The standard interpretation of the statement marks contextual values which may have contributed to a discovery of a theory as irrelevant for justifying the acceptance of a theory and for assessing how evidence bears on theory. The relation that is crucial for the objectivity of science, contextual values, are restricted to a matter of individual psychology that may influence the discovery, development, and proliferation of a scientific theory, but is not epistemic status. The distinction played a crucial role in post-World War II philosophy of science. It presupposes, however, a clear-cut distinction between cognitive values on the one hand and contextual values on the other. While this may be prima facie plausible for disciplines such as physics, there is an abundance of contextual values in the social science. More general, the three major lines of criticism can be identified. First, Helen Lagino, 1996, has argued that traditional cognitive values such as consistency, simplicity, breadth of scope, and fruitfulness are not purely cognitive or epistemic after all, and that their use imports political and social values into context of scientific judgments. According to her, the use of cognitive values in scientific judgment is not always, not even normally, politically neutral. She proposes to juxtapose the values with feminist values such as novelty, ontological heterogeneity, mutuality of an interaction, applicability to human needs, and diffusion of power, and argues the use of traditional value instead of its alternative, simplicity instead of ontological heterogeneity, can lead to biases and adverse research results. Longino's argument here is different from the one earlier discussed. It casts the very distinction between cognitive and contextual values into doubt. The second argument against the possibility of value-free science is semantic and attacks the neutrality of scientific theories. Fact and value are frequently entangled because the use of so-called thick ethical concepts in science, ethical concepts that have mixed descriptive and normative content. For example, a descriptive such as dangerous technology involves a value judgment about technology and the risk it implies, but it also has a descriptive content. It is uncertain and hard to predict whether using that technology will really trigger those risks. If the other use of such terms, where facts and values are inextricably entangled, it is inevitable in scientific reasoning. It is impossible to describe hypotheses and results in a value-free manner, undermining the value neutrality thesis. Indeed, Jean Dupree has argued that thick ethical terms are ineliminable from science, at least certain parts of it. Dupree points is essentially that scientific hypotheses and results concern us because they are relevant to human interest, and thus they will necessarily be couched in language that uses thick ethical terms. While it will often be possible to translate ethically thick descriptions into neutral ones, the translation could not be made without losses, and those losses obtain precisely because human interests are involved. According to Dupree, then many scientific statements are value-free only because their truth or falsity does not matter to us. The only human interests they touch, and these they may indeed touch deeply, are cognitive ones, and so the only values that they implicate are cognitive values. The third challenge to the value neutrality thesis, and perhaps the most influential one, was raised by Richard Rudner in his influential article, The Scientist Qua-Scientist Make Value Judgment, 1953. Rudner disputes the core of the value neutrality thesis and the context of discovery justification distinction, the idea that the acceptance of a scientific theory can in principle be value-free. First, Rudner argues no analysis of what constitutes the method of science would be satisfactory unless it comprised some assertion to the effect that the scientist as scientist accepts or rejects hypotheses. This assumption stems from the industrial quality control and other application-oriented research. In such contexts, it is often necessary to accept or reject a hypothesis in order to make effective decisions. Second, he notes that no scientific hypothesis is ever confirmed beyond reasonable doubt. Some probability of error always remains. When we accept or reject a hypothesis, there is always a chance that our decision is mistaken. Hence, our decision is always a function of the importance in the typically ethical sense of making a mistake in accepting or rejecting a hypothesis. We are balancing the seriousness of two possible errors, erroneous acceptance, rejection of the hypothesis, against each other. This is corresponding to type 1 and type 2 errors in statistical inference. The decision to accept or reject a hypothesis involves value judgment, or at least implicitly, because scientists have to judge which of the consequences of an erroneous decision they deem more palatable. Some individuals die of the side effects of a drug erroneously judged to be safe, or other individuals die of a condition because they did not have access to a treatment that was erroneously judged to be unsafe. Hence, ethical judgments and contextual values necessarily enter the scientist's core activity of accepting and rejecting hypotheses. And the value neutrality thesis stands refuted. Closely related arguments can be found in Churchman, 1948, and Braithwaite, 1953, and Hempel, 1965, gives a modified account of Rudner's argument by distinguishing between judgments of confirmation, which are free of contextual values, and judgments of acceptance. Since even strongly confirming evidence cannot fully prove a universal scientific law, we have to live with a residual inductive risk in inferring that law. Contextual values influence scientific methods by determining the acceptable amount of inductive risk. But how general are Rudner's objection? Apparently, his results hold true of applied sciences, but not necessarily fundamental research. For the latter domain, two major lines of rebuttals have been proposed. First, Richard Jeffrey, 1956, notes that law-like hypotheses in theoretical science are characterized by their general scope and not confined to particular application. Obviously, a scientist cannot fine-tune his decision to their possible consequences in a wide variety of different contexts, so he should just refrain from the essentially pragmatic decision to accept or reject hypothesis by restricting scientific reasoning to gathering and interpreting evidence, possibly supplemented by assessing the probability of hypothesis. Jeffrey tries to save the value neutrality thesis in a fundamental scientific research and the objectivity of scientific reason. Second, Isaac Levy, 1960, observes that scientists commit themselves to a certain standard of inference when they become a member of a profession. This may, for example, lead to the statistical rejection of hypothesis when the observed significance level is smaller than 5%. These community standards may eliminate any room for a contextual ethical judgment on behalf of the scientist. They determine when he should accept a hypothesis as established. Value judgments may be implicit in how a scientific community sets standards of inference, but not the daily work of an individual scientist. Both defenses of the value neutrality thesis focus on the impact of values in theory choice, either by denying that scientists actually choose their theories, or by referring to community standards and restricting the value neutrality thesis to individual scientists. Douglas points out, however, that the acceptance of scientific theories is only one of several places for values to enter scientific reasoning, albeit an especially prominent and explicit one. Many decisions in the process of scientific inquiry may conceal implicit value judgments: the design of an experiment, the methodology for conducting it, the characterization of the data, the choice of the statistical method for processing and analyzing the data, the interpretational process findings None of the methodological decisions could be made without consideration of the possible consequences that could occur. The choice of a conservative classification or model had to be weighted against the adverse consequences for society that could result from underestimating the risk. These diagnoses cast a gloomy light on attempts to divide scientific labor between gathering evidence and determining the degree of confirmation value-free on the one hand and accepting scientific theories value-laden on the other. The entire process of conceptualizing, gathering, and interpreting evidence is so entangled with contextual values that no neat division, as Jeffries envisions, will work outside the narrow realm of statistical inference, and even there doubts may be raised. Philip Kitcher gives an alternative argument based on his idea of significant truths. There are simply too many truths that are of no interest whatsoever. Science then doesn't aim at truth simpliciter, but rather at something more narrow, truth worth pursuing from the point of view of our cognitive, practical, and social goals. Any truth that is worth pursuing in this sense is what he calls a significant truth. Clearly, it is a value judgment that helps us decide whether or not any given truth is significant. Kitcher goes on observing that the process of scientific investigation cannot neatly be divided into a stage in which the research question is chosen, one in which the evidence is gathered, and one in which a judgment about the question is made on the basis of evidence. Rather, the sequence is multiply iterated, and at each stage, the researcher has to decide whether previous results warrant pursuit of the current line of research or whether he should switch to another avenue. Such choices are laden within contextual values. Values in science also interact, according to Kitcher, in a non-trivial way. Assume we endorse predictive accuracy as an important goal of science. However, there may not be convincing strategy to reach this goal in some domain of science. For instance, because the domain is characterized by strong nonlinear dependencies. In this case, predictive accuracy might have to yield to achieving other values, such as consistencies, with theories in neighboring domains. Conversely, changing social goals lead to reevaluations of scientific knowledge and research methods. Science then cannot be value-free because no scientist ever works exclusively in the supposed value-free zone of assessing and accepting hypotheses. Evidence is gathered and hypotheses are assessed and accepted in the light of their potential for application in fruitful research avenues. Both cognitive and contextual value judgment guide these choices and are themselves influenced by their results. Science policy and the value-free ideal. The discussion so far is focused on the value neutrality thesis, the practical attainability of the value-free ideal, but little has been said about a value-free science, whether a value-free science is desirable in the first place. This subsection discusses the topic with special attention to informing and advising public policy from a scientific perspective. While the value-free ideal and many arguments for and against it can be applied to science as a whole, the interface of science and public policy is the place where the intrusion of values into science is especially salient and where it's surrounded by the greatest controversy. Indeed, many debates at the interface of science and public policy are characterized by disagreements on propositions that combine the factual basis with specific goals and values. The critical question in such debate is whether there are theses that such that one side of the debate endorses, the other side rejects it, the evidence is shared, and both sides have good reasons for their respective positions. According to the value-free ideal, scientists should uncover an epistemic value-free basis for resolving such disagreements and restrict the dissent to the realm of value judgments. Even if the value neutrality thesis should turn out to be unattainable and a strict separation should be impossible, the value-free ideal may have an important function in guiding scientific research and minimizing the impact of values on objective science. In the philosophy of science, one camp of scholars defends the value-free ideal as a necessary antidote to individual and institutional interests, such as Hugh Lacey, Ernest McMullen, and Sandra Mitchell, while another adapts a critical attitude such as Helen Longino, Philip Kitcher, and Heather Douglas. These criticisms we discussed mainly refer to the desirability or the conceptual unclarity of the value-free ideal. First, it is argued that the value-free ideal is not desirable at all. Feminist philosophers have argued that science often carries a heavy androcentric values, for instance, in biological theories about sex, gender, and rape. The change against these values is not so much that they are contextual rather than cognitive, but they are unjustified. Moreover, if scientists did follow the value-free ideal rigidly, policymakers would pay even less attention to them, with the detrimental effect of the decisions they take. Given these shortcomings, the value-free ideal has to be rethought if it is supposed to play a successful role for guiding scientific research and leading a better policy decision. Elaborate on this line of criticism is the context of scientific community practices and a science in the service of society. Second, the autonomy of science often fails in practice due to the presence of external stakeholders, such as funding agencies and industry lobbies. To save the epistemic authority of science, Douglas proposed to detach it from its autonomy by reformulating the value-free ideal and distinguishing between direct and indirect roles of values in science. Contextual values may legitimately affect the assessment of evidence by indicating the appropriate standard of evidence and representation of complex processes, the severity of consequences of a decision, the interpretation of noisy data sets, and so on. This concerns, above all, policy-related disciplines such as climate science or economics that routinely perform scientific risk analysis for real-world problems. Values should, however, not be reasons in themselves, that is, evidence or defeaters for evidence, direct role illegitimate, and as helping to decide what should count as sufficient reason for a choice. Indirect role legitimate, the prohibition for values to replace or dismiss scientific evidence is called detached objectivity by Douglas, but it is complemented by various other aspects that relate to a reflected balancing of various perspectives and the procedural social aspects of science. That said, Douglas's proposal is not very concrete when it comes to implementation regarding the way diverse values should be balanced. Comprising in the middle cannot be the solution. Compromising in the middle cannot be the solution. First, no standpoint is just in virtue of being in the middle, evidently supported vis-a-vis more extreme positions. Similarly, the middle positions are also, from a practical point of view, the least functional when it comes to advising policymakers. Moreover, the distinction between direct and indirect roles of values in science may not be sufficiently clear-cut to police the legitimate use of values in science and to draw the necessary borderlines. Assume that a scientist considers, for whatever reason, the consequences of erroneously accepting hypothesis undesirable, therefore uses a statistical model whose results are likely to favor not the hypothesis over the hypothesis in a matter of reasonable conservativeness? Or does it amount to reasoning to a foregone conclusion and treating value as evidence? The most recent literature on values and evidence in science presents us with a broad spectrum of opinions. Steele and Winsberg, 2012, argue that probabilistic assessments of uncertainty involve contextual value judgments, while Steele defends this point by analyzing the role of scientists as policy advisors. Winsberg points to the influence of contextual values in the selection and representation of physical processes and climate modeling. Betts, 2013, argues by contrast that scientists can largely avoid making contextual value judgments if they carefully express the uncertainty involved in their evidential judgments by using scale ranging from purely qualitative evidence, such as expert judgment, to precise probabilistic assessment. The issues of value judgments at earlier stages of inquiry is not addressed by this proposal. However, disentangling evidential judgment and judgments involving contextual values at the stage of theory assessment may be a good thing in itself. Thus, should we or should we not be worried about values in scientific reasoning? While the interplay of values and evidential considerations need not be pernicious, it is unclear why it adds to the success or the authority of science. How are we going to ensure that the permissive attitude towards values in setting evidential standards is not abused in the absence of a general theory about which contextual values are beneficial and which are pernicious? The value-free ideal might as well be a first-order approximation to a sound, transparent, and objective science. Oh yeah, thanks, Mr. Boston. Objectivity is freedom from personal biases. This section deals with scientific objectivity as a form of intersubjectivity, as freedom from personal biases. According to this view, science is objective to the extent that personal biases are absent from scientific reasoning, or that they can be eliminated in a social process. Perhaps all science is necessarily perspectival. Perhaps we cannot sensibly draw scientific inferences without a host of background assumptions, which may include assumptions about values. Perhaps all scientists are biased in some way, but objective scientific results do not, or so the argument goes, depend on researchers' personal preferences or experiences. They are the result of a process that where individual biases are gradually filtered out and replaced by agreed upon evidence. That, among other things, is what distinguishes science from the arts and other human activities, and scientific knowledge from fact-independent social construction. paradigmatic ways to achieve objectivity in this sense are measurement and quantification. What has been measured and quantified has been verified relative to a standard. The truth is independent of the person making the measurement. We will begin with a discussion of objectivity, so conceived in measurement, discuss the ideal of mechanical objectivity, and then investigate to what extent freedom from personal biases can be implemented in statistical evidence and inductive inference, arguably the core of scientific reasoning, especially in quantitatively oriented sciences. Finally, we will discuss Feyerabend's radical criticism of a rational scientific method that can be mechanistically applied and his defense of the epistemic and social benefits of personal bias and idiosyncrasy. Measurement and quantification. Measurement is often thought to epitomize scientific objectivity, most famously captured in Lord Kelvin's dictum, where you cannot when you cannot express in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be. Measurement can certainly achieve some independence of perspective. Clearly, however, measurement does not result in a review from nowhere, nor are typical measurement results free from presuppositions. Measurement instruments interact with the environment, and so results will always be a product of both properties of the environment we aim to measure as well as the properties of the instrument. Instruments thus provide a perspectival view on the world. Moreover, making sense of measurements results require interpretation. According to Sak Cheng's account of the early thermometry, the problem was eventually solved by using a principle of minimalist overdetermination, the goal of which was to find a reliable thermometer while making as few substantial assumptions as possible. Minimal doesn't mean zero, however, indeed this procedure makes an important presupposition in the case of a metaphysical assumption about the one-valuedness of a physical quantity. Moreover, the procedure yielded at best a reliable instrument, not necessarily one that was best at tracking the uniquely real temperature. What Cheng argues about the early thermometry is true of measurements more generally. They are always made against a backdrop of metaphysical presuppositions, theoretical expectation, and other kinds of belief. Whether or not any given procedure is regarded as adequate depends to a large extent on the purposes pursued by the individual scientist or group of scientists making the measurement. Especially in the social sciences, this often means the measurement procedures are laden with normative assumptions, values. Julian Rees has argued that economic indicators are value-laden in the sense. While not free of assumptions and values, the goal of many measurement procedures remains to reduce the influence of personal biases and idiosyncrasies. Lorraine Datson and Peter Gallison refer to this as mechanical objectivity. They write, finally, we come to the full-fledged establishment of mechanical objectivity as the ideal of scientific representation. What we find is that the image or standard bearer of its objectivity is tied to a relentless search to replace individual volition and discretion in depiction by the invariable routines of mechanical reproduction. Mechanical objectivity reduces the importance of human contributions to scientific results to a minimum and therefore enables science to proceed on a large scale where bonds of trust between individuals can no longer hold. Trust in mechanical procedures thus replaces trust in individual scientists. In his book, Trust in Numbers, Theodore Porter pursues this line of thought in great detail, in particular on the basis of case studies involving British actuaries in the mid-19th century, of French state engineers throughout the century, and of the U.S. Army Corps of Engineers from 1920 to 1960. He argues for two causal claims. First, measurement instruments and quantitative procedures originate in commercial and administrative needs and affect the ways in which natural and social sciences are practiced, not the other way around. In the mushroom of instruments such as chemical balances, barometers, chronometers, was largely a result of social pressures and demands of democratic societies. Administering large territories or controlling diverse peoples and processes is not always possible on the basis of a personal trust, and thus objective procedures which do not require trust in persons took the place of subjective judgments which do. Second, he argues that quantification is a technology of distrust and weakness and not of strength. It is weak administrators who do not have the social status, political support, or professional solidarity to defend their expert judgments. They therefore subject decisions to public scrutiny, which means they must be made in a publicly accessible form. This is a situation in which scientists who work in areas where the science policy boundary is fluid find themselves. The National Academy of Sciences has accepted the principle that scientists should declare their conflicts of interest and financial holdings before offering policy advice or even information to the government. And while police inspections of notebooks remains exceptional, the personal financial interests of scientists and engineers are often considered material, especially in legal and regulatory contexts. Strategies of impersonality must be understood partly as defenses against such suspicions. Objectivity means knowledge that does not depend too much on the particular individual who authored it. Measurement and quantification help to reduce the influence of personal biases and idiosyncrasies that they reduce the need to trust the scientist or government official, but often at a cost. Standardizing scientific procedures becomes difficult when their subject matters are not homogeneous, and few domains outside fundamental physics are. Attempts to quantify procedures for treatment and policy decisions that we find in evidence-based practices are currently transferred to a variety of sciences such as medicine, nursing, psychology, education, and social policy. However, they often lack a certain degree of responsiveness to the peculiarities of their subject and the local condition to which they are applied. Moreover, the measurement and quantification of characteristics of scientific interest is only half the story. We also want to describe relations between the quantities and make inferences using statistical analysis. Statistics thus helps to quantify further aspects of scientific work. We will now examine whether or not statistical analysis can proceed in a way free from personal biases and idiosyncrasies. Sandra, God bless. Statistical evidence. The appraisal of scientific evidence is traditionally regarded as a domain of scientific reasoning, where the ideal of scientific objectivity has strong normative force, and where it is also well entrenched in scientific practice. Episodes such as Galileo's observation of Jupiter's moon, Lavoisier's calcinization experiment, and Eddington's observation of the 1999 eclipse are all found in philosophy of science textbooks because they exemplify how evidence can be persuasive and compelling to scientists with different backgrounds. The crucial question is, therefore, can we identify an objective concept of scientific evidence that is independent of the personal biases of the experimenter and interpreter? Inferential statistics. In the field that investigates the validity of inferences from data to theory, tries to answer this question, is extremely influential in modern science, pervading experimental research as well as the assessment and acceptance of our most fundamental theories. For instance, a statistical argument helped to establish the recent discovery of the Higgs boson. We now compare the main theories of statistical evidence with respect to the objectivity of the claims they produce. They mainly differ with respect to the role of an explicitly subjective interpretation of probability. Bayesian inference. Bayesian inference quantifies scientific evidence by means of probabilities that are interpreted as a scientist's subjective degrees of belief. The Bayesian thus leaves behind Carnap's idea that the probability is determined by a logical relation between sentences. For example, the prior degree of belief in hypothesis H, written P of H, can in principle take any value in the interval 0 to 1. Simultaneously held degrees of belief in different hypotheses are, however, constrained by the laws of probability. After learning evidence E, the degree of belief in the hypothesis is changed from its prior probability, P of H, to the conditional degree of belief, P of HE, commonly called the posterior probability of the hypothesis. Both quantities can be related to each other by means of Bayes' theorem. These days, the Bayesian approach is extremely influential in philosophy and rapidly gaining ground across all scientific disciplines. For quantifying evidence for a hypothesis, Bayesian statisticians almost uniformly use the Bayes factor, that is the ratio of the prior to the posterior odds in favor of hypothesis, the Bayes factor in favor of hypothesis against its negation in light of evidence. Or in other words, as the likelihood ratio between the hypothesis and not the hypothesis. The Bayes factor reduces to the likelihoodist conception of evidence for the case of two competing point hypotheses. Unsurprisingly, the idea to measure scientific evidence in terms of subjective probability has met resistance. For example, statistician Ronald Fisher has argued that measuring psychological tendencies cannot be relevant for scientific inquiry and sustained claims to objectivity. Indeed, how should scientific objectivity square with subjective degree of belief? Bayesians have responded to this challenge in various ways. Hausen 2000 and Urbach in 2006 consider the objection misplaced in the same way that deductive logic does not judge the correctness of the premises, but just advises you what to infer from them. Bayesian inductive logic provides rational rules for representing uncertainty and making inductive inferences. Choosing the premises, the prior distributions objectively falls outside of the scope of Bayesian analysis. Converging or merging of opinion theorems guarantee that under certain circumstances, agents with very different initial attitudes who observe the same evidence will obtain similar posterior degrees of belief in the long run. However, they are asymptotic results without direct implications for inference with real-life data sets. In such cases, the choice of the prior matters, and it may be beset with idiosyncrasy, bias, and manifest social values. Adopting a more modest stance, Springer, 2018, accepts that Bayesian inference does not achieve the goal of objectivity in the sense of intersubjective agreement, concordant objectivity, or being free from personal values, biased and subjective judgment. However, he argues that competing schools of inference, such as frequentist inference, face this problem to the same degree, perhaps even worse. Moreover, some features of Bayesian inference, the transparency about prior assumptions, fit recent socially oriented conceptions of objectivity. A radical Bayesian solution to the problem of personal bias is to adopt a principle that radically constrains an agent's rational degrees of belief, such as the principle of maximum entropy. According to the principle of maximum entropy, degrees of belief must be probabilistic and in sync with empirical constraints, but conditional on these constraints, they must be equivocal, that is, as middling as possible. This latter constraint accounts to maximizing the entropy of the probability distribution in question. The principle of maximum entropy approach eliminates various sources of subjective bias at the expense of narrowing down the range of rational degrees of belief. An alternative objective Bayesian solution consists in so-called objective prior probabilities that do not represent an agent's factual attitudes, but are determined by principles of asymmetry, mathematical convenience, or maximizing the influence of the data on the posterior. Thus, Bayesian inference, which analyzes statistical evidence from the vantage point of rational belief, provides only a partial answer to securing scientific objectivity from personal idiosyncrasy. Frequentist inference. The frequentist conception of evidence is based on the idea of statistical test of a hypothesis. Under the influence of the statistician Jerzy Neiman and Ergon Pearson, tests were often regarded as rational decision procedures that minimize the relative frequency of wrong decisions in a hypothetical series of repetitions of a test, hence the name frequentism. Rudner's argument has pointed out the limits of this conception of hypothesis test, the choice of thresholds for acceptance and rejection, the acceptable type 1 and 2 error rates, may reflect contextual value judgments and personal biases. Moreover, the losses associated with erroneously accepting or rejecting that hypothesis depend on the context of application, which may be unbeknownst to the experimenter. Alternatively, scientists can restrict themselves to a purely evidential interpretation of hypothesis tests and leave decisions to policymakers and regulatory agencies. The statistician and biologist Fisher proposed what later became the orthodox quantification of evidence in frequentist statistics. Suppose a null or default hypothesis denotes that an intervention has zero effect if the observed data are extreme under the default hypothesis. If it was highly likely to observe a result that agrees better with the default hypothesis, the data provide evidence against the null hypothesis and for the efficacy of the intervention. The epistemological rationale is connected to the idea of severe testing. If the intervention were ineffective, we would in all likelihood have found data that agree better with the null hypothesis. The strength of evidence against the null hypothesis is equal to the p-value. The lower it is, the stronger the evidence speaks against the null hypothesis. Unlike Bayes' factor, the concept of statistical evidence does not depend on personal degrees of belief. However, this does not necessarily mean that p-values are more objective. First, p-values are usually classified as non-significant, significant, highly significant, and so on. Not only do these thresholds and labels are largely arbitrary, they also promote publication bias. Non-significant findings are often classified as failed studies. The efficacy of the intervention could not be shown, rarely published, and end up in proverbial file drawer. Much valuable research is suppressed. Conversely, significant findings may often occur when the null hypothesis is actually true, especially when researchers have been hunting for significance. In fact, researchers have an incentive to keep their p-values low. The stronger the evidence, the more convincing the narrative. the greater the impact and the higher the chance for good publication and career relevant rewards. Moving the goalpost by p-hacking outcomes, for example, by eliminating outliers, selective reporting, or restricting the analysis to a subgroup, evidently biases the research results and compromises the objectivity of experimental research. In particular, such questionable research practices increase the type 1 error rate, which measures the rate at which false hypotheses are accepted substantially over its nominal 5% level and contribute to publication bias. Ioannidis 2005 concludes that most published research findings are false, that they are combined result of low base rate of effective causal interventions, the file drawer effect, and the widespread presence of questionable research practices. The frequentist logic of hypothesis testing aggravates the problem because it provides a framework where all these biases can easily enter. These radical conclusions are also confirmed by empirical findings, and many disciplined research failed to replicate findings by other scientific teams. Summing it up, our findings: neither of the two major frameworks of statistical inference manages to eliminate all the sources of personal bias and idiosyncrasies. The Bayesian considers subjective assumptions to be an irreducible part of scientific reasoning and sees no harm in making them explicit. The frequentist conception of evidence based on p-values avoids these explicitly subjective elements, but at the price of misleading impressions of objectivity and frequent abuse in practice. The defense of a frequentist interference should, in our opinion, stress that the relatively rigid rules for interpreting statistical evidence facilitate communication and assessment of research results in the scientific community, something that is harder to achieve for a Bayesian. We now turn from specific methods for stating and interpreting evidence to a radical criticism of the idea that there is a rational scientific method. Feyerabend, the tyranny of the rational method. In his writings of the 1970s, Paul Feyerabend launched a profound attack on the rationality and objectivity of scientific method. His position is exceptional in the philosophical literature, since traditionally the threat for objective and successful science is located in contextual rather than epistemic values. Feyerabend turns this view upside down. It is the tyranny of rational method and the emphasis on epistemic rather than contextual factors that prevents us from having a science in the service of society. Moreover, he welcomes the diversity of different personal, also idiosyncratic perspectives, thus denying the idea that freedom from personal bias is epistemically or socially beneficial. The starting point of Feyerabend's criticism of rational method is his thesis that strict epistemic rules, such as those expressed in the value-free ideal, only suppresses an open exchange of ideals, extinguish scientific creativity, and prevents a free and truly democratic science. In his classic Against Method, 1975, Feyerabend elaborates on his criticism by examining a famous episode in the history of science. When the Catholic Church objected to Galilean mechanics, it had the better arguments by the standards of the 17th century science. Their conservatism in the position was scientifically backed. Galileo's telescopes were unreliable for celestial observations, and many well-established phenomena, no fixed star parallax, invariance of laws of motion, could not yet be explained in the heliocentric system. With hindsight, Galileo managed to achieve groundbreaking scientific progress just because he deliberately violated rules of scientific reasoning. Hence, Feyerabend's dictum, anything goes, no methodology whatsoever is able to capture the creative and often irrational way by which science deepens our understanding of the world. Good scientific reasoning cannot be captured by rational method, as Carnap, Hempel, and Popper postulated. The drawbacks of an objective, value-free, and method-bound view on science and scientific method are not only epistemic. Such a view narrows down our perspectives and makes us less free, open-minded, creative, and ultimately less human in our thinking. It is therefore neither possible nor desirable to have an objective, value-free science. As a consequence, Feyerabend sees traditional forms of inquiry about the world on par with their Western competitors. He denounces appeals to objective standards as rhetorical tools for bolstering the epistemic authority of a small intellectual elite, Western scientists, and as fairly disguised statements of preference for one's own worldview. There is hardly any difference between the members of a primitive tribe who defend their laws because they're the laws of the gods and a rationalist who appeals to objective standards, except that the former knows what they are doing while the latter does not. In particular, when discussing other traditions, we often project our own worldview and value judgments into them instead of making an impartial comparison. There's no purely rational justification for dismissing other perspectives in favor of the Western scientific worldview. The Galilee example also illustrates that personal perspective and idiosyncratic bias need not be bad for science. Feyerabend argues further that scientific research is accountable to society and should be kept in check by democratic institutions and laymen in particular. Their particular perspectives can help to determine the funding agenda and set ethical standards for scientific inquiry, but also be useful for traditionally value-free tasks such as choosing an appropriate research method and assessing scientific evidence. Feyerabend's writings on this issue were much influenced by witnessing the civil rights movement in the United States and increasing emancipation of minorities. All this is not meant to say that truth loses its function as a normative concept, nor that all scientific claims are equally acceptable. Rather, Feyerabend advocates for epistemic pluralism that accepts diverse approaches to acquiring knowledge rather than defending a narrow and misleading ideal of objectivity. Science should respect the diversity of values and traditions that drive our inquiries about the world. This would put science back into the role ahead during the scientific revolution of the Enlightenment as a liberating force that fought intellectual and political oppression by the sovereign, the nobility, or the clergy. Objectivity is a feature of scientific communities and the practices. This section addresses various accounts that regard scientific objectivity essentially as a function of social practices in science and social organizations of the scientific community. All these accounts reject the characterizations of scientific objectivity as a function of correspondence between theories and the world, as a feature of individual reasoning practices, or as pertaining to individual studies and experiments. Instead, they evaluate the objectivity as a collective of studies as well as the methods and community practices that structure and guide scientific research. More precisely, they adopt a meta-analytical perspective for assessing the reliability of scientific results, and they construct objectivity from a feminist perspective as an open interchange of mutual criticism, or as being anchored in the situatedness of our scientific practices and the knowledge we gain. Reproducibility in the meta-analytic perspective. The collectivist perspective is especially useful when an entire discipline enters a stage of crisis. Its members become convinced that a significant portion of the findings are not trustworthy. A contemporary example of such a situation is the replication crisis, which was briefly mentioned in the previous section and concerns the reproducibility of scientific knowledge claims in a variety of different fields, most prominently psychology, biology, and medicine. Large-scale replication projects have noticed that many findings which we considered as an integral part of scientific knowledge failed to replicate in settings that were designed to mimic the original experiments as closely as possible. Successful attempts at replicating an experimental result have long been argued to provide evidence of freedom from particular kinds of artifacts and thus the trustworthiness of the result. Likewise, failure to replicate indicates that either the original finding, the result, or of the replication, or both, are biased. Though see John Norton's argument that the evidential value of failed replication crucially depends on researchers' material background assumptions. When replication failures in a discipline are particularly significant, one may conclude that the published literature lacks objectivity. At a minimum, the discipline fails to inspire trust that its findings are more than artifacts of the researcher's efforts. Conversely, when observed effects can be replicated in follow-up experiments, a kind of objectivity in research that goes beyond the ideas of freedom from personal bias, mechanical objectivity, and subject-independent measurement. Friesen Peterson, 2018, called this idea statistical objectivity. It grounds the view that even the most scrupulous and diligent researchers cannot achieve full objectivity all by themselves. The term objectivity instead applies to a collection of populations of studies with meta-analysis, a formal method of aggregating the results from ranges of studies, as the apex of objectivity. In particular, aggregating studies from different researchers may provide evidence of a systematic bias in questionable research practices. In the published literature, the diagnostic function of meta-analysis for detecting violations of objectivity is enhanced by the statistical techniques such as the funnel plot and the P-curve. Apart from this epistemic dimension, research on statistical objectivity has an activist dimension. Methodologists urge researchers to make publicly available essential parts of their research before the data analyst starts and to make their methods and data source more transparent. For example, it is conjectured that the replicability and thus objectivity of science will be increased by making all data available online, by pre-registering experiments, and by using the registered reports model for journal articles. The journal decides on publication before data collection on the basis of the significance of the proposed research as well as the experimental design. The idea is that transparency about the data set and the experimental design will make it easier to stage a replication of an experiment to assess its methodological quality. Moreover, publicly committing to a data analysis plan beforehand will lower the rate of questionable research practices and of attempts to accommodate data to hypothesize rather than making proper predictions. All in all, statistical objectivity moves the discussion of objectivity to the level of population of studies. There it takes up and modifies several conceptions of objectivity that we have seen before, most prominently freedom of subjective bias, which is replaced with collective bias and pernicious conventions, and the subject independent measurement of a physical quantity, which is replaced by reproducibility of effects. Feminist and standpoint epistemology. Traditional notions of objectivity as faithfulness to facts of freedom of contextual values have also been challenged from a feminist perspective. These critiques can be grouped into three major research programs: feminist epistemology, feminist standpoint theory, and feminist postmodernism. The program of feminist epistemology explores the impact of sex and gender on the production of scientific knowledge. More precisely, feminist epistemology highlights the epistemic risk resulting from the systematic exclusion of women from the ranks of scientists and neglect of women as objects of study. Often, but not always, feminist epistemologists go beyond pointing out what they regard as androcentric bias and reject the value-free ideal altogether, with an eye on the social and moral responsibility of scientific inquiry. They try to show that value-laden science can also meet important criteria for being epistemically reliable and objective. A classical representative of such efforts is Longino's 1990 contextual empiricism. She reinforces Popper's insistence that the objectivity of scientific statements lies in the fact that they can be intersubjectively tested. But unlike Popper, she conceives scientific knowledge essentially as a social product. Thus, our conception of scientific objectivity must directly engage with the social process that generates knowledge. Longino assigns a crucial function to social systems of criticism in securing the epistemic success of science. Specifically, she develops an epistemology which regards a method of inquiry as objective to the degree that it permits a transformative criticism. From an epistemic community, to achieve transformative criticism, there must be avenues for criticism. Criticism is an essential part of scientific institutions like peer review. Shared standards. The community must share a set of cognitive values for assessing theories. Uptake of criticism. Criticism must be able to transform scientific practice in the long run. Equality of intellectual authority. Intellectual authority must be shared equally among qualified practitioners. Longino's contextual empiricism can be understood as the development of John Stuart Mill's view that beliefs should never be suppressed independently of whether they are true or false. Even the most implausible beliefs might be true, and even if they are false, they might contain a grain of truth which is worth preserving or helps to better articulate true beliefs. The underlying intuition is supported by recent empirical research on the epistemic benefits of a diversity of opinions and perspectives. By stressing the social nature of scientific knowledge and the importance of criticism, Longino's account fits into the broader project of feminist epistemology. Standpoint theory undertakes a more radical attack on traditional scientific objectivity. This view develops Marxist ideas to the effect that epistemic position is related to and a product of social position. Feminist standpoint theory builds on these ideas but focuses on gender, racial, and other social relations. Feminist standpoint theorists and proponents of situated knowledge such as Donna Haraway, 1998, Sandra Harding, and Alison Wiley, 2003, deny the internal coherence of a view from nowhere. All human knowledge is at base human knowledge and therefore necessarily perspectival. But they argue more than that. Not only is it perspectively the human condition, it is also a good thing to have. That is because perspectives, especially the perspectives of underprivileged classes and groups in society, come along with epistemic benefits. These ideas are controversial, but they draw attention to the possibility that attempts to rid science of the perspectives might not only be futile, but also costly. They prevent scientists from having the epistemic benefits certain standpoints afford and from developing knowledge for marginalized groups in society. The perspectival stance can also explain why criteria for objectivity often vary with context. The relative importance of epistemic virtue is a matter of goals and interest, in other words, standpoint. By endorsing a perspectival stance, feminist standpoint theory rejects classical elements of scientific objectivity, such as neutrality and impartiality. This is a notable difference to feminist epistemology, which is in principle, though not always in practice, compatible with traditional views of objectivity. Feminist standpoint theory is also a political project For example, Harding demands that scientists, their communities, and their practices, in other words, the ways through which knowledge is gained, be investigated as rigorously as the object of knowledge itself. The idea she refers to as strong objectivity replaces the weak conception of objectivity in the empiricist tradition. Value freedom, impartiality, rigorous adherence to methods of testing, and inference, like Feyerabend. Harding integrates a transformation of epistemic standards in science into a broader political project of rendering science more democratic and inclusive. On the other hand, she is exposed to similar objections. Isn't it grossly exaggerated to identify class, race, and gender as important factors in the construction of physical theories? Doesn't the feminist approach, like social constructivist approaches, lose sight of the particular epistemic qualities of science? Should not scientists really have as much authority as trained scientists? To whom does the condition of equally shared intellectual authority apply? Nor is it clear, especially at the time of fake news and filter bubbles, whether it is always a good idea to subject scientific results to democratic approval. There is no guarantee. Arguably, there are few good reasons to believe that democratized or standpoint-based science leads to more reliable theories or better decisions for society as a whole. Issues in the special sciences. So far, everything we discussed was meant to apply across all, or at least most of the scientists. In this section, we will look at a number of specific issues that arise in the social sciences, in economics, and in evidence-based medicine. Max Weber and objectivity in the social sciences. There's a long tradition in the philosophy of social science maintaining that there is a gulf in terms of both goals as well as methods between the natural and social sciences. This tradition associated with thinkers such as the Neo-Kantians, Heinrich Rickert and Wilhelm Winterbildt, the hermeneuticist William Dilthey, and the sociologist economics Max Weber, and the 20th century hermeneuticist Hans Gregor Gadamer and Michael Oakeshott hold that, unlike the natural sciences, whose aim is to establish natural laws to which proceed by experimentation and causal analysis, the social sciences seek understanding of social phenomenon, the interpretive examination of the meaning individuals attribute to their actions. Understood in this way, social sciences lack objectivity in more than one sense. One of the more important debates concerning objectivity in the social sciences concern the role value judgment play, and importantly, whether value-laden research entails claims about the desirability of actions. Max Weber held that the social sciences are necessary value-laden. However, they can achieve some degree of objectivity by keeping out the social researchers' views about whether agents' goals are commendable. In a similar vein, contemporary economics can be said to be value-laden because it predicts and explains social phenomena on the basis of agents' preferences. Nevertheless, economists are adamant that economists are not in the business of telling people what they ought to value. Modern economics is thus said to be objective in a Weberian sense of absence of researchers' values, a conception. It is widely cited essay, Objectivity in the Social Sciences and Social Policy. Weber argued that the idea of a perspectival social science was meaningless. There's no absolutely objective scientific analysis of social phenomenon, independent of special and one-sided viewpoints according to which expressively or tacitly, consciously or unconsciously, they are selected, analyzed, and organized for expository purposes. All knowledge of cultural reality, as it may be seen, is always knowledge from a particular point of view. The reason for this is twofold. First, social reality is too complex to admit to a full description and explanation, so we have to select, but perhaps in contraposition to natural sciences, we cannot just select those aspects of the phenomenon that fall under universal natural laws and treat everything else as unintegrated residuals. This is because, second, in the social sciences, we want to understand social phenomenon in their individuality, that is, in their unique configurations that have significance for us. Values solve a selection problem. They tell us what research questions we ought to address because they inform us about the cultural importance of social phenomena. Only a small portion of existing concrete reality is colored by our value coordination interest, our value condition interest, and it alone is significant to us. It is significant because it reveals relationships which are important to use due to their connection with our values. It is important to note that Weber did not think that social and natural science were different in kind, as Dilthey and others did. Social science too examines the causes of phenomenon of Interest in natural science too often seeks to explain natural phenomenon in their individual constellations. The role of causal laws is different in the two fields, however, whereas establishing a causal law is often an end in itself in the natural sciences. In the social sciences, laws play an attenuated and accompanying role as mere means to explain cultural phenomena in their uniqueness. Nevertheless, for Weber, social science remains objective in at least two ways. First, one research question of interest has been settled. Answers about the causes of culturally significant phenomena do not depend on the idiosyncrasies of an individual researcher, but obviously does not follow from this that research in the cultural sciences can only have results which are subjective in the sense that they are valid for one person and not for others. For scientific truth is precisely what is valid for all who seek the truth. The claim of social sciences can therefore be objective in our third sense. Moreover, by determining that a given phenomenon is culturally significant, a researcher reflects on whether or not a practice is meaningful or important, and not whether or not it is commendable. An important implication of this view came to the fore in the so-called quarrel concerning value judgments in the early 1900s. In this debate, Weber maintained against the socialists of the lectern around Gustav Mahler the position that social scientists qua scientists should not be directly involved in policy debates because it was not the aim of science to examine the appropriateness of ends. Given a policy goal, a social scientist could make recommendations about effective strategies to reach the goal, but social science was to be value-free in the sense of not taking a stance on the desirability of the goals themselves. This leads us to our conception of objectivity as freedom from value judgments. Contemporary rational choice theory. Contemporary mainstream economists hold the view concerning objectivity that mirrors Max Weber's. On the other hand, it is clear that value judgments are at the heart of economic theorizing. Preferences are a key concept of rational choice theory, the main theory in contemporary mainstream economics. Preferences are evaluation. If an individual prefers A to B, he values A higher than B. Thus, to the extent that economists predict and explain market behavior in terms of rational choice theory, they predict and explain market value behavior in a way laden with value judgments. However, economists are not themselves supposed to take a stance on whether whatever individual's value is objectively good in a stronger sense. That an agent is rational from rational choice theory point of view does not mean that the course of action he will choose is objectively optimal. Desires do not have to align with an objective measure of goodness. I may want to risk swimming in a crocodile-infested lake. I may desire to smoke or drink, even though I know it harms me. Optimality is determined by the agent's desire, not the converse. In a similar vein, Gould and Pessendorfer write, however, standard economics has no therapeutic ambition. It does not try to evaluate or improve the individual's objectives. Economics cannot distinguish between choices that maximize happiness, choices that reflect a sense of duty, or choices that are the response to some impulse. Moreover, standard economics takes no position on the question of which of these objectives the agent should pursue. According to the standard view, all that rational choice theory demands is that people's performances are internally consistent. It has no business in telling people what they ought to prefer, whether their preferences are consistent with external norms or values. Economics is thus value laden, but laden with values of the agents whose behavior it seeks to predict and explain, and not with the values of those who seek to predict and explain this behavior. Whether or not social science and economics in particular can be objective in this Weber's and the contemporary economic sense is controversial. On the one hand, there are some reasons to believe in the rational choice theory, which is at work not only in economics but also in political science and other social sciences, cannot be applied to empirical phenomena without referring to external norms or values. On the other hand, it is not clear that economists and other social scientists, qua social scientists, shouldn't participate in a debate about social goals. For one thing, trying to do welfare analysis is this in the standard Weberian way tends to obscure rather than eliminate normative commitments. Obscuring value judgments can be detrimental to social scientists as policy advisors because it will hamper rather than promote trust in social science. For another, economists are in a prime position to contribute to ethical debates for a variety of reasons and should therefore take this responsibility seriously. Evidence-based medicine and social policy. The same demands calling for mechanical objectivity in the natural sciences and objectification in the social policy and policy sciences in the 19th century and the mid 20th century are responsible for a recent movement in biomedical research, which even more recently have swept to contemporary social science and policy. Early proponents of the so-called evidence-based medicine made their pursuit of a downplay of the human element in medicine plain. Evidence-based medicine de-emphasizes intuition on systematic clinical experience and pathophysiological rationale as sufficient grounds for clinical decision-making and stresses the examination of evidence from clinical research. To call the new movement evidence-based is a misnomer, strictly speaking, as intuition, clinical experience, and pathophysiological rationale can certainly constitute evidence. But proponents of evidence-based practices have much narrower concept of evidence in mind. Analysis of the result of randomized control trials. This movement is now very strong in biomedical research, development economics, and a number of areas of social science, especially psychology, education, and social policy, and especially in the English-speaking world. The goal is to replace subjective, biased, error-prone, idiosyncratic judgments by mechanically objective methods, but in the other areas, attempting to mechanize inquiry can lead to reduced accuracy and utility of the results. Causal mechanisms in the social and biomedical science hold on account of highly complex arrangements of factors and conditions. Whether, for instance, a substance is toxic depends on details of the metabolic system of the population ingesting it, and whether an educational policy is effective on the constellation of factors that affects the student's learning progress. If a randomized control trial was conducted successfully, the conclusion about the effectiveness of the treatment under test is certain for the particular arrangement of factors and conditions of the trial, but unlike randomized control trials itself, many of whose aspects can be relatively mechanically implemented, applying the result to a new setting always involves subjective judgment of the kind proponents of evidence-based practices seek to avoid, such as judgments about the similarity of the test to the target or policy population. On the other hand, randomized control trials can be regarded as a debiasing procedure because they prevent researchers from allocating treatments to patients according to their personal interests, so that the healthiest or smartest subjects get the researcher's favorite therapy. While unbalanced allocations can certainly happen by chance, randomization still provides some warrant that the allocation was not done on purpose with a view to promoting somebody's interest. A priori, the experimental procedure is thus more impartial with respect to the interest at stake. It has thus been argued that randomized control trials in medicine, while no guarantor of the best outcomes, were adopted by the U.S. Food and Drug Administration to different degrees during the 1960s and 70s in order to regain public trust in its decisions about treatments, which it had lost due to the thalidomide and other scandals. It is important to notice, however, that randomization is at best effective with respect to one kind of bias, selection bias. Important other epistemic concerns are not addressed by the procedure, but should not be ignored. The unity and disunity of scientific objectivity. In sections 2 to 5, we have encountered various concepts of scientific objectivity and their limitations. This prompts the question of how unified or disunified scientific objectivity is as a concept. Is there something substantive shared by all of these analyses, or is objectivity, as Heather Douglas in 2004 puts it, an irreducibly complex concept? Douglas defines pluralism about scientific objectivity and distinguishes 3 areas of application of the concept: interaction of humans with the world, individual reasoning process, social processes, and science. Within each area, there are various distinct senses which are, again, irreducible to each other and do not have a common core meaning. This does not mean that the senses are unrelated. They share a complex web of relationships and can also support each other. For example, eliminating values from reasoning may help to achieve procedural objectivity. For Douglas, reducing objectivity to a single core meaning would be a simplification without benefits. Instead of a complex web of relations between different senses of objectivity, we would obtain an improvised concept out of touch with scientific practice. It has been argued, however, that pluralist approaches give up too quickly on the idea that the different senses of objectivity share one or several important common elements. Scientific objectivity and trust in science are closely connected. Scientific objectivity is desirable because, to the extent that science is objective, we have reasons to trust scientists. The results are recommendations Thus, perhaps what is unifying among the different senses of objectivity is that each sense describes a feature of scientific practice that is able to inspire trust in science. Building on this idea, Inkara Koshkinen has recently argued that is in fact not trust but reliance that we are after. Trust is something that can be betrayed, but only individuals can betray, whereas objectivity pertains to institutions, practices, and results. We can call scientific institutions, practices, results objective to the extent that we have reasons to rely on them. The analysis does not stop here, however. There is a distinctive view about objectivity that is behind Datsun and Gallison's historical epistemology of the concept and has been defended by Ian Hacking, that objectivity is not a positive virtue, but rather the absence of this or that vice. Speaking of objectivity in imaging, for instance, Datsun and Gallison write that their goal is let the specimen appear without that distortion characteristic of the observer's personal taste, commitments, and or ambitions. Koshkinen picks up this idea of objectivity as absence of vice and argues that it is specifically the aversion to epistemic risk for which the term is reserved. Epistemic risk comprises any risk of epistemic error that arises anywhere during knowledge practices, such as the risk of having mistaken beliefs, the risk of errors in reasoning, and the risk related to operationalization, concept formation, and model choice. Koskinen argues that only those epistemic risks that relate to failings of scientists as human beings are relevant to objectivity. For instance, when the results of an experiment are incorrect because of malfunctioning equipment, we do not worry about objectivity. We just say that the results should not be taken into account. So it is only when the epistemic risk is related to our own failings and is hard to avert that we start talking about objectivity. Illusion, subjectivity, idiosyncrasies, and collective biases are important epistemic risks arising from our imperfections as epistemic agents. Koskinen understands her account as a response to Hacking's criticism that we should stop talking about objectivity altogether. According to Hacking, objectivity is an elevator or second level word similar to true or real. He recommends to stick to ground level questions and worry about whether specific sources of error have been controlled. A similar elimination request with respect to the labels objective and subjective in statistical inference has been advanced by Gelman and Henning in focusing on averting specific epistemic risk. Koskinen's account does precisely that. Koskinen argues that a unified account of objectivity as averting epistemic risk takes into account Hacking's negative stance and explains at the same time important features of the concept. For example, why objectivity does not imply certainty and why it varies with context. The strong point of this account is that none of the threats to a peculiar analysis puts scientific objectivity at risk. We can, in fact, we do rely on scientific practices that represent the world from a perspective and where non-epistemic values affect outcomes and decisions. What is left open by Koskinen's account is the normative question of what a scientist who cares about her experiments and inferences being objective should actually do. That is the philosophical ideas we have reviewed in this section stay mainly on the descriptive level and do not give an actual guideline for working scientists. Connecting the abstract philosophical analysis to the day-to-day work in science remains an open problem. Conclusions. So is scientific objectivity desirable? Is it attainable? That, as we have seen, depends crucially on how the term is understood. We have looked in detail at 4 different conceptions of scientific objectivity: faithfulness to facts, value freedom, freedom from personal biases, and features of community practices. In each case, there are at least some reasons to believe that either science cannot deliver full objectivity in this sense, or that it would not be a good thing to try to do so, or both. Does this mean we should give up on the idea of objectivity in science? We have shown that it's hard to define scientific objectivity in terms of a view from nowhere, value freedom, or freedom from personal bias. It is a lot harder to say anything positive about the matter. Perhaps it is related to a thorough critical attitude concerning claims and findings of popular thought. Perhaps it is the fact that many voices are heard, especially respected and subjected to accepted standards as Longino defines. Perhaps it is something else altogether, or a combination of several factors discussed in this article. However, one should not as yet throw out the baby with the bathwater, like those who defend a particular explication of scientific objectivity. The critics struggle to explain what makes science objective, trustworthy, and special. For instance, our discussion of the value-free ideal revealed that alternatives to the value-free ideal are at least as problematic as the value-free ideal itself, and that the value-free ideal may, with all its inadequacies, still be a useful heuristic for fostering scientific integrity and objectivity. Similarly, although entirely unbiased scientific procedures may be impossible, there are many mechanisms scientists can adopt for protecting their reasoning against undesirable forms of bias, choosing an appropriate method of statistical inference, being transparent about different stages of the research process, and avoiding certain questionable research practices. Whatever it is, it should come as no surprise that finding a positive characterization of what makes science objective is hard. If we knew an answer, we would have done it no less than solve the problem of induction, because we would know what procedures or forms of organization are responsible for the success of science. Work on this problem is an ongoing project, and so is the quest for understanding scientific objectivity. Okay, I'd meant to do 5, and that includes computer simulations, although I think I'm only going to do 4 because it's already been 4.5 hours, and this one's probably going to take me a whole nother hour. Hey, Skyworks, good to see you. So I'm going to have to put off computer simulations till next week, but we will do the incommensurability of scientific theories. Yes, Skyworks, good to see you. Just refill my drink. And don't forget, this Saturday night, 7 p.m. ET, will be a year in review with Church of Entropy. It'll be more interactive with the chat, and hopefully have some guests if you want to pop on. So don't forget, year in review with Church of Entropy Saturday night. Okay, so the incommensurability of scientific theories. The term incommensurable means to have no common measure. The idea has its origin in ancient Greek mathematics, where it meant no common measure between magnitudes. Today, such incommensurable relations are represented by irrational numbers. The metaphorical application of this mathematical notion, specifically to the relationship between successive scientific theories, became controversial in 1962 after it was popularized by 2 influential philosophers of science, Thomas Kuhn and Paul Feyerabend. They appear to be challenging the rationality of natural science and were often considered to be among the worst enemies of science. Since 1962, the incommensurability of scientific theories has been a widely discussed, controversial idea that was instrumental in the historical turn in the philosophy of science and the establishment of the sociology of science as a professional discipline. Introduction. In the influential The Structure of Scientific Revolution, 1962, Kuhn made the famous dramatic claim that the history of science reveals proponents of competing paradigms failing to make complete contact with each other's view, so that they are always talking at least slightly at cross purposes. Kuhn characterized the collective reason for these limits to communicate as the incommensurability of pre- and post-revolutionary scientific traditions, claiming that the Newtonian paradigm is incommensurable with the Cartesian and Aristotelian predecessors in the history of physics, just as the Lavoisier's paradigm is incommensurable with that of Priestley's in chemistry. These competing paradigms lack a common measure because they use different concepts and methods to address different problems, limiting communication across the revolutionary divide. Kuhn initially used incommensurability predominantly to challenge cumulative characteristics of scientific advances, according to which scientific progress is an improving approximation to the truth, and to challenge the idea that there are unchanging neutral methodological standards for comparing theories throughout the development of the natural sciences. Like in evolution, the process does not change towards some fixed goal according to some fixed rules, method, or standards, but rather it changes away from the pressures exerted by anomalies of the reigning theory. The process of scientific change is eliminative and permissive rather than instructive. In the process of confronting anomalies, certain alternatives are excluded, but nature does not guide us to some uniquely correct theory. Kuhn developed and refined his initial idea over the following decades, repeatedly emphasizing that incommensurability neither means nor implies incomparability, nor does it make science irrational. He focused increasingly on conceptual incompatibility as manifest in the structural differences used to classify the kinds whose relations are stated in laws and theories. He used incommensurability to attack the idea, prominent among logical positivists and logical empiricists, that comparing theories, translating their consequences into neutral observational language. In the late 1990s, he explicated incommensurability in terms of ineffability, emphasizing that it became possible for scientists to make and understand certain new statements only after a particular theory had been introduced, and the older vocabulary of the new sentences are nonsensical, just as it only becomes possible for historians to understand certain older statements by setting aside current conceptions that otherwise cause distortions. Such taxonomical incommensurability results in translation failure between local subsets and interdefined terms due to the cross-classification of objects into mutually exclusive taxonomies. This can be distinguished from methodological incommensurability, according to which there is no common measure between successive scientific theories, in the sense that the theory comparison is sometimes a matter of weighing historically developing values, not following fixed definitive rules. This makes room for rational disagreement in theory comparison, as scientists may apply different values such as scope, simplicity, fruitfulness, accuracy in evaluating and comparing particular theories, so that theory choice is not unequivocally determined throughout the scientific community. Paul Feyerabend first used this term incommensurable in the 1962 in Explanation, Reduction, and Empiricism to describe the lack of logical relations between the concepts of fundamental theories in his critique of logical empiricist models of explanation and reduction. He argued that in the course of scientific advance, when fundamental theories change, meanings change, which can result in new conceptions of the nature of reality. By calling two fundamental theories incommensurable, Feyerabend meant that they were conceptually incompatible. The main concepts of one could neither be defined on the basis of the primitive descriptive terms of the other, nor related to them via a correct empirical statement. Feyerabend repeatedly used the idea of incommensurability to challenge a wide range of forms of conceptual conservatism, arguing that they unjustifiably favor successful entrenched concepts over potential improvements and overlook the possibility of developing incommensurable alternatives. The entries organized around the 1962 popularizations of the concept of incommensurability by Kuhn and Feyerabend, and the basic ideas that influenced their developments of this concept. First, Kuhn's notion of incommensurability, as it was initially developed, is characterized as its cause and its purported consequence. That is followed by an examination of Kuhn's route to the idea and then his subsequent development after 1962. The section on Feyerabend's notion of incommensurability mirrored the same basic structure. They are followed by a brief comparison of Kuhn and Feyerabend's view on incommensurability, especially its relationship to theory comparison. Revolutionary paradigms. Thomas Kuhn on incommensurability. Kuhn's notion of incommensurability in the structure of scientific revolutions misleadingly appeared to imply that science was somehow irrational, and consequently it faced many challenges and caused many confusions. This led to many clarifications and eventually to substantial redevelopment of a more precise and restricted version of it over the following decades. Kuhn initially used the term holistically to capture methodological, observational, and conceptual disparities between successive scientific paradigms that he had encountered in his historical investigations into the development of the natural sciences. Later, he refined the idea, arguing that incommensurability is due to differences in the taxonomical structures of successive scientific theories and neighboring contemporaneous subdisciplines. Kuhn's developing notion of incommensurability has received much attention, and it continues to provoke plenty of controversy. Pardon me. The structure of scientific revolutions. In The Structure of Scientific Revolutions, 1962, Thomas Kuhn used the term incommensurable to characterize the holistic nature of the changes that take place in scientific revolution. His investigations of the history of science revealed a phenomenon often now called Kuhn loss, problems whose solution was vitally important to the older tradition may temporarily disappear become obsolete or even unscientific. On the other hand, problems that had not have even existed or whose solution had been considered trivial may gain extraordinary significance in the new tradition. Kuhn concluded that proponents of incommensurable theories have different conceptions of their discipline and different views about what counts as good science, and that these differences arise because of changes in the list of problems that a theory must resolve and a corresponding change in the standards for the admissibility of proposed solutions. According to Kuhn, he concluded that scientific revolutions altered the very definitions of science itself. Changes in problems and standards come with corresponding conceptual changes, so that after a revolution, many, though not all, of the older concepts are still used, but in a slightly modified way. Such conceptual changes have both intentional and extensional aspects, which is to say that the same terms take on different meanings and are used to refer to different things when used by proponents of competing incommensurable theories. The changes in the intentional aspects of concepts result because the terms used to express a theory are interdefined and their meanings depend on the theories to which they belong. Conceptual changes also result in the exclusion of some old elements of the extension of a concept, while new elements come to be subsumed by it, so that the same term comes to refer to a different things. Incommensurable theories use some of the same terms, but with different meanings to refer to different sets of things. Two scientists who perceive the same situation differently, but nevertheless use the same vocabulary to describe it, speak from incommensurable viewpoints. One of the most controversial claims to emerge from Kuhn's assertion about the incommensurability of scientific theories is that proponents of different paradigms work in different roles. Drawing on experiments in the psychology of perception, Kuhn argued that the rigorous training required for admittance to a paradigm conditions scientists' reaction, expectations, and beliefs, so that learning how to apply the concepts of a theory to solve exemplary problems determine scientist experiences. Kuhn and Feyerabend use an analogy of a Gestalt switch to illustrate this point. In this way, one main source of the notion of incommensurability of scientific theories has been the development of Gestalt psychology. According to Kuhn, these three interrelated aspects of incommensurability, changes in problems and standards that define a discipline, changes in the concepts used to state and solve the problems, and role changes jointly constrain the interpretation of scientific advances as cumulative. Scientific progress, Kuhn argued, is not simply the continual discovery of new facts duly explained. Instead, revolutions change what counts as the facts in the first place. When reigning theories are replaced by incommensurable challengers, the purported facts are redescribed according to new and incompatible theoretical principles. The main goal of Kuhn's structure was to challenge the idea of scientific progress as cumulative, according to which what is corrected or discarded in the course of scientific advance is that which was never really scientific in the first place. And Kuhn used incommensurability as the basis of his challenge. Instead of understanding scientific progress as a process of change towards some fixed truth, Kuhn compared his suggestion to that of Darwin's scientific progress is like evolution, in that its development should be understood without reference to a fixed permanent goal. Kuhn's route to incommensurability. Kuhn's discovery of incommensurability. According to Kuhn, he discovered incommensurability as a graduate student in the mid to late 1940s while struggling with what appeared to be nonsensical passages in Aristotelian physics. He could not believe that someone as extraordinary as Aristotle could have written them. Eventually, patterns in the disconcerting passages began to emerge, and then all at once the text made sense to him, a Gestalt switch that resulted when he changed the meaning of some of the central terms. He saw this process of meaning changes as a method of historical recovery. He realized that in his earlier encounters, he had been projecting contemporary meanings back into their historical sources, Whiggish history, and that he would need to peel them away in order to remove the distortion and understand the Aristotelian system in its own right, hermeneutic history. For instance, when he encountered the word motion in Aristotle, the standard translation of the Greek kinesis, he was thinking in terms of the change of position of objects in space as we do today. But to get more closely at Aristotle's original uses, he had to expand the meaning of motion to cover a much broader range of phenomena that included various other sorts of change, such as growth and diminution, alteration, and degeneration and corruption, making an object's motion in space displacement or locomotion, just a special case of motion. Kuhn realized that these sorts of conceptual differences indicated breaks between different modes of thought, and he suspected that such breaks might be significant both to the nature of knowledge and for the sense in which the development of knowledge can be said to make progress. Having made this discovery, Kuhn changed his career plans, leaving theoretical physics to pursue this strange phenomenon. Some 15 years later, the term incommensurable first appeared in his classic The Structure of Scientific Revolutions of 1962. Conceptual replacement and theory-latedness of observation, Ludwig Fleck. Of all the sources influencing Kuhn on incommensurability, at least one deserves special attention. In the foreword to The Structure of Scientific Revolutions, Kuhn acknowledges a deep debt to Ludwig Fleck, a bacteriologist who developed the first explicit sociology of natural science and anticipated many contemporary views about the social construction of knowledge. Around 1950, Kuhn was enticed by the potential relevance to his experience of incommensurability by Fleck's paradoxical title, Genesis and the Development of Scientific Fact, 1935. There, in another earlier works, Fleck had already used incommensurable in German to describe different styles of thinking within natural sciences, as well as discuss the ramifications of radical conceptions of change in the history of science. For example, Fleck used the term incommensurable to describe the differences between medical thinking and scientific thinking. The former addresses irregular, temporally dynamic phenomena such as illness, while the later addresses uniform phenomena. Fleck also used the term incommensurable to describe conceptual replacements in theoretical transition with what he considered the most vital of the natural sciences, the medical sciences. For example, he claimed that old concept disease became incommensurable with the newer concept that was not completely adequately substituted for it. While Fleck's program of comparative epistemology anticipated Kuhn's idea in many significant respects, it is also strikingly different. The most pervasive differences concerning incommensurability are that Fleck treats meaning and meaning change as a function of how concepts are received and developed by the collective, while for Kuhn, it is individuals who develop and apply the concepts that advance science. Moreover, for Fleck, meaning change is a continuous feature of scientific development, whereas Kuhn distinguishes normal scientific development that does not change meaning from revolutionary development that do. Even so, Fleck emphasizes all three of the interrelated aspects of the shifts that Kuhn called revolutions and tried to capture by calling theories incommensurable changes in problems and standards, conceptual change, and world change. Fleck argued that science does not approach the truth because successive thought style raise new problems and discard older forms of knowledge. Fleck emphasized that scientific terms acquire their meanings through their application within a particular theoretical context, and that these meanings change when theories change in the course of advance, even offering the example of chemical elements and compounds repeated by Kuhn. Fleck emphasizes the theory-latedness of observation with explicit references to Gestalt switches, stressing that a thought style determines not only the meanings of the concepts at issues, but also the perception of phenomena to be explained, developing examples from the history of anatomical representation. Fleck, like Kuhn, Feyerabend, and Wittgenstein, acknowledges Wolfgang Kohler's work in psychology of perception in this regard. Fleck concluded that scientific advance is not cumulative, that conceptual differences between members of different scientific communities cause communication difficulties between them. And later, for historians trying to understand older ideas, Fleck even emphasizes the meaning change in the course of scientific advances causes translation failure between theories, anticipating a central aspect of Kuhn's later notion of taxonomic incommensurability, Gestalt psychology, and organized perception. Another major source of Kuhn's idea of the incommensurability of scientific theories is Gestalt psychology. Wolfgang Kohler, for example, had emphasized the active role of an organization in perception, and he argued that in psychology, one begins with Gestalten, organized segregated wholes, such as objects of human perception or identifiable human behaviors, and then proceeds to discover their natural parts and not vice versa. In the opening sentences of the condensed English version of Kohler's investigation of the relationship between the mental concepts of psychology and that of material concepts of the physics, Kohler wrote, in order to orient itself in the company of natural sciences, psychology must discover connections wherever it can between its own phenomenon and those of other disciplines. If this research fails, then psychology must recognize that its categories and those of natural science are incommensurable. The image of art and the image of science. In a preliminary draft, The Structure of Scientific Revolutions, Chapter 1, What are Scientific Revolutions? Of the first chapter of his projected book, Kuhn initially used the idea of incommensurability to characterize stages of development in the arts, in contrast to traditional images of scientific progress as cumulative that he set out to challenge, although this draft chapter was entirely rewritten as the introduction of in 1962 and was explicitly intended only to provoke explanatory discussion and not for publication. It strongly suggests, though, at the time Kuhn began to develop the idea of incommensurability in science in reaction to the traditional contrast between development in the arts and cumulative progress in science. In this draft, Kuhn announced his project is intent to reshape the image of science so as to make it closer to the image of art. He wanted to challenge the cumulative conception of scientific progress promoted by the old historiography of science, according to which science appears to advance by accretion, and science is an ever-growing edifice to which each scientist strives to add few stones or a bit of mortar, in contrast to the image of art, according to which the transition between one stage of artistic development and the next is a transition between incommensurables. A few pages later, Kuhn proceeds to apply the idea of incommensurability to the science for the very first time, again while comparing scientific revolutions to the non-cumulative nature of progress in the arts. Often a decision to embrace new theory turns out to involve an implicit redefinition of the corresponding science. Old problems may be relegated to another science or may be declared entirely unscientific. Problems that on the old theory were not existent or trivial may, with a new theory, become very archetypes or of significant scientific achievement. And as the problem change, so too does the standard that distinguishes a real scientific solution from a mere metaphysical speculation, word game, or mathematical play. It follows that to a significant extent, the science that emerges from a scientific revolution is not only incompatible, but often actually incommensurable with that which has gone before. Only as this is realized can we grasp the full sense in which scientific revolutions are like those in the arts. Kuhn concludes that if we are to preserve any part of the metaphor which makes inventions and discovery new bricks for the scientific edifice, and if we are to simultaneously to give resistance to the and controversy an essential place in the development of science, then we may have to recognize that the addition of new bricks demands at least a partial demolition of the existing structure, and that the new edifice erected to include the new bricks is not just the old ones plus, but a new building. We may, that is, be forced to recognize that new discoveries and new theories do not simply add to the stock of pre-existing scientific knowledge, they change it. Kuhn's subsequent development of incommensurability. Kuhn continued to struggle with, develop, and then redefined his understanding of incommensurability until his death in 1996, although his development of incommensurability went through several stages. He claimed to have made a series of significant breakthroughs beginning in.
Okay, I found this on the web for
He claimed to have made a series of significant breakthroughs beginning in 1987. They are described in a number of essays and published lectures that were collected in 2000, and a last as yet unpublished book by Kuhn on incommensurability is still pending. The nature of these developments is controversial. Some commentators claim that Kuhn's incommensurability thesis underwent a major transformation, while others see only a more specific characterization of the original core insight. Kuhn's original holistic characterization of incommensurability has been distinguished into two separate theories. Taxonomical incommensurability involves a conceptual change, in contrast to methodological incommensurability, which involves the epistemic values used to evaluate theories. Taxonomical incommensurability. Kuhn continued to emphasize the difference between normal cumulative growth that does not change existing concepts such as the discovery of Boyle's law, which left the concepts of gas pressure and volume and the instruments used to measure them unchanged, from revolutionary changes that could not have been made on the basis of antecedently available concepts such as the discovery of Newton's theory. Such developments require replacing existing concepts with new concepts that are incompatible with the older ideas. To help explain the nature of this conceptual incompatibility, Kuhn adopted a notion of lexical taxonomy or lexicon from linguistics. A lexical taxonomy stores the structures the vocabulary used to state laws and theories, or more specifically, the kinds of things that they describe. It is the mental module in which members of speech communities store the kinds of terms prerequisite to generalization and description. To communicate the terms that speakers use do not have to have the same meaning, nor do speakers need to use the same criteria for identifying something as a member of a particular kind. Speakers need only share homologous lexical structure, that is, vocabularies incorporating the same system of taxonomic classification. This suffices to ensure that they refer to the same object with the same kind. If two theories do not share the same taxonomical lexical structure, then they are incommensurable. To help explain incommensurability in terms of taxonomic classification, Kuhn developed the no-overlap principle. The no-overlap principle precludes cross-classification of objects into different kinds within a theory taxonomy. According to the no-overlap principle, no two kind terms may overlap in their reference unless they're related as species to genus. Such kind terms are used to state laws and theories and must be learned together through experience. There are two possibilities. Most kinds of terms must be learned as members of one or another contrast set. Other types of kind terms are not learned through contrast sets, but together with closely related terms through their joint application to situations that exemplify natural law. According to Kuhn, scientific revolutions change the structural relationship between pre-existing kind terms, breaking the no-overlap principle. This is to say that theories separated by revolution cross-classified the same things into mutually exclusive sets of kinds. The kinds from one taxonomy is mutually exclusive with another if it cannot simply be introduced into it because the objects to which it refers would be subject to a different set of natural laws. This would result in conflicting expectations about the same objects, loss of logical relations between statements made with those concepts, and ultimately incoherence and miscommunication. Furthermore, Kuhn, in a move towards Feyerabend's view, now claims that the same types of difficulties in communications that arise due to incommensurability between members of a different scientific community separated by the passage of time also occurs between members of different contemporaneous subdisciplines that result from scientific revolutions. This represents a significant change to his original phase model of scientific advance and a corresponding shift in his application of the notion of incommensurability. Kuhn no longer represents scientific advance as a linear progression from pre-normal science to normal science through crisis to revolution that results in a new phase of normal science. Instead, scientific revolutions are compared to the process of speciation in biology in that they result in branching into subdisciplines that resemble a phylogenetic tree. The application of the relation of incommensurability is no longer restricted to diachronic episodes of scientific advances in which two theories are separated by revolution. The contemporaneous subdisciplines that result from scientific revolutions can also be incommensurable with each other. The incommensurability derives from a different training required to master the incompatible kind terms used to state their laws and theories. These shared kind terms cross-classify the same set of objects into different sets of kinds, resulting in mutually exclusive lexical taxonomies that break the no-overlap principle. Moreover, now not only are both processes, scientific progress and biological evolution, similar in that they are not fixed in advance of some set goal, like truth, but driven from behind, away from anomalies that play an analogous role to selection pressures, but also the incommensurability of scientific theories is presented as analogous to the isolating mechanisms required for speciation. Kuhn compared the function of such lexical taxonomies to Kant's a priori when taken in a relativized sense. Each lexicon makes a corresponding form of life possible within which the truth or falsity of propositions may be both claimed and rationally justified. For example, with the Aristotelian lexicon, one can speak of the truth or falsity of Aristotelian assertions, but these truth values have no bearing on the truth of apparently similar assertions made with the Newton lexicon. A lexicon is thus constitutively of the objects of knowledge, and consequently Kuhn rejected characterizations of scientific progress according to which science zeroes in on the truth. No shared metric is available to compare our assertions, and thus to provide a basis for a claim that our, or for this matter, his, are closer to the truth. Instead, the logical status of a lexical structure like that of word meanings in general, is that of convention, and the justification of lexical or lexical change can only be pragmatic. Kuhn thus reaffirmed his earlier claim that the notion of a match or correspondence between the ontology of a theory and its real counterpart in nature is elusive in principle. The implication that the incommensurability has for scientific realism have been widely discussed and continue to be controversial. A lexicon is not only a prerequisite to making meaningful statements, it also sets limits on what can be meaningfully said within the community of speakers that it shares. There is, for example, no way, even in enriched Newtonian vocabulary, to convey the Aristotelian propositions regularly misconstrued as asserting the proportionality of force and motion of the impossibility of a void. Using the conceptual lexicon, these Aristotelian propositions cannot be expressed. They are simply ineffable, and we are barred by the no overlap principle from access to these concepts required to express them. In this way, Kuhn's later notion of the incommensurability of scientific theories is based on effability. The structure of the lexicon shared by a particular community determines how the world can be described by its members, as well as how they will misunderstand the history of their own discipline. That is, unless they learn to understand other terms according to the structure of the older lexicon, where Kuhn had earlier likened the process by which historians come to understand antiquated science as a special type of translation. He retracted these claims, insisting that the process is one of language learning, not translation. Kuhn often claimed that incommensurable theories are untranslatable. However, he also emphasized that translation is neither needed in the comparison of incommensurable theories nor in the hermeneutical history method necessary to understand antiquated sciences. To overcome the barriers posed by incommensurability to understanding antiquated sciences and to understanding the special technical vocabulary used by contemporaneous phylogenetically related subdisciplines, it is neither necessary nor possible to translate between them. Rather, one must become bilingual, learning to use and keep separate and the incongruently structured lexical taxonomies underwriting different laws and theories. Methodological incommensurability. As Kuhn refined his notion of incommensurability as a special type of conceptual incompatibility, some commentators began to distinguish it from methodological incommensurability. Methodological incommensurability is the idea that there are no shared objective standards of scientific theory appraisal, so that there are no external or neutral standards that unequivocally determine the comparative evaluation of competing theories. This idea has been recently discussed in detail under the rubric Kuhn undetermination. The basic idea was developed out of Kuhn and Feyerabend's rejection of the traditional view that a distinguishing feature of science is a uniform, invariant scientific method that remains fixed throughout its development. Feyerabend famously argued that every proposed methodological rule has been fruitfully violated at some point in the course of scientific advancement, and that only by breaking such rules could scientists have made the progressive steps for which they are praised. He concluded that the idea of a fixed, historically invariant scientific method is a myth. There are no universally applicable methodological rules. The only methodological rule that is universally applicable is anything goes, which buys its universality at the cost of being completely empty. Kuhn challenged the traditional view of scientific method as a set of rules, claiming that the standards of a theory appraisal, such as simplicity, accuracy, consistency, scope, and fruitfulness, depends on and vary with the currently dominant paradigm. He is often cited for having pointed out that as in political revolution, so in choice of paradigm, there is no standard higher than the assent of the relevant community, as is having argued that there is no neutral algorithm for theory of choice, no systematic decision procedure, which properly applied must lead each individual in the group to the same decision. Kuhn developed the idea that such epistemic standards do not function as rules that determine rational theory choice, but as values that merely guide it. Different scientists apply these values differently, and they may even pull in different directions, so that there may be rational disagreement between scientists from incommensurable paradigms who support different theories due to their weighing the same values differently. Combating conceptual conservationism. Paul Feyerabend on incommensurability. An examination of Feyerabend's use and development of the idea of incommensurability of scientific theories reveals just how widespread it was to 1962. It also reveals the veiled common core of Feyerabend's philosophy of science, which otherwise appears to be a series of critical papers on unrelated topics. The common core is its use of the idea of incommensurability to challenge many different forms of conceptual conservatism in science and philosophy. Conceptual conservatism unjustly favors existing ideas over potential improvements offered by incommensurable alternatives. Feyerabend uses the notion of incommensurability to attack the following forms of conceptual conservatism: Heisenberg's idea of closed theories, 1951, attempts to distinguish philosophical accounts of ontology from physics, 1954, and the foundational role of the stability thesis in logical positivism, Bohr's principle of complementarity, and the logical empiricist model of explanation and reduction. He also used the idea of incommensurability to attack forms of conceptual conservatism implicit to the model of theory testing promoted by classical empiricists, the logical positivists, the logical empiricists, Popper and Kuhn, Kantian transcendental necessities, traditional philosophical conundrums like the problem of the existence of the external world, the problem of the existence of other minds, and especially the mind-body problem. Certain aspects of Wittgenstein's later philosophy, as well as the linguistic philosophical movement that takes the utility of everyday concepts as given and merely attempts to analyze them without changing their meanings. Popper's conception of verisimilitude and scientific realist characterizations of scientific knowledge and scientific advance. Feyerabend argued that all of these views cannot accommodate the fact that the history of science reveals revolutionary development in which incommensurable alternatives replaced existing ideas in the course of progress. Explanation, reduction, and empiricism. In his landmark 1962 Explanation, Reduction, and Empiricism, Paul Feyerabend initially introduced the term incommensurable as a part of the criticism of the conceptual conservatism that he found in Nagel's theory of reduction and the Hempel-Oppenheim theory of explanation. He argued that the formal accounts of reduction and explanation are impossible for general theories because they cannot accommodate for the development of incommensurable concepts in the course of scientific advance. Feyerabend used the notion of incommensurability to characterize the relationship between two successive fundamental universal scientific theories interpreted realistically as purported descriptions of reality. By limiting incommensurability to universal theories, Feyerabend meant only those that apply to all objects in the universe. By limiting incommensurability to Feyerabend meant those that have ontological implications, those that have implications about the very nature of reality. Universal fundamental scientific theories can be incommensurable only if they are interpreted realistically, according to Feyerabend, because otherwise they cannot compete as the one true theory and are thus not mutually exclusive. By calling two such theories incommensurable, Feyerabend meant that they were conceptually incompatible. The main concepts of one could neither be defined on the basis of the primitive description terms of the other, nor related to them via a correct empirical statement. As a consequence, it is impossible to reduce incommensurable theories formally. In 1962, Feyerabend illustrated the incommensurability of scientific theories with a comparison of 6 pairs of central concepts drawn from 3 episodes of fundamental theory change in the course of scientific advance. 1, the dynamic characterization of the impetus and the impetus theory of motion and the concept of force in the conceptual apparatus of Newtonian mechanics. 2 and 3, the concept of temperature and entropy and their transition from a phenomenological thermodynamics of kinetic theory. And 4, 5, and 6, the concept of mass, length, and time and the transition from Newtonian to relativistic mechanics. Feyerabend subsequently added the example of geometric optics and wave optics. In 1962, Feyerabend also claimed that incommensurability occurs between traditional fundamental theories in philosophy and consequently arises in the discussion of the mind-body problem, the problem of the reality of the external world, and the problem of other minds. Feyerabend argued that such age-old philosophical problems have not been solved because the disputants resist the kind of meaning change necessary for the dissolution. Concepts are incommensurable, according to Feyerabend, because they belong to mutually exclusive theoretical perspectives. These perspectives mutually exclusive because they give incompatible accounts of the nature of reality. Feyerabend argued that because the meanings of their terms are provided by the theories to which they belong, when there is theoretical change, there are meaning changes. Feyerabend argued that these changes in meaning affect our theoretical and observational terms, as well as our conception of the nature of reality. When this occurs, there's incommensurability, or as Feyerabend later characterized his view, a theory is incommensurable with another if its ontological consequences are incompatible with ontological consequences of the latter. The ideas tended to capture conceptual incompatibility due to changes of meaning that occur in theoretical transitions that affect our ontological beliefs. Two fundamental theories are incommensurable because the meanings of their terms are determined by the theoretical principles that govern their use, and their principles are qualitatively incompatible. Feyerabend used this idea of incommensurability to attempt to expose a dogmatic element that contemporary empiricists share with school philosophies such as Platonism and Cartesianism, for whom empiricists had tried to distance themselves by insisting on an empirical foundation for scientific knowledge. The dogmatic element is due to the assumption that the meanings of empirical terms remain stable through theoretical transitions, or what Feyerabend called the principle of meaning invariance. Feyerabend argued that this principle is inconsistent with the existence of incommensurable concepts. Feyerabend drew two main consequences from the insight that some pairs of successive scientific theories are incommensurable. First, successive scientific theories that are incommensurable have no logical relation because their concepts have different meanings. They cannot be brought into formal logical relations. Second, a revision of the logical empiricist conception of scientific advance is required. Older theories and the concepts used to state them are not corrected or absorbed and thereby legitimized. Rather, they are rejected and replaced, having been falsified. In this way, the logical empiricist, conceptual conservative, or retentive accounts of reduction and explanation are undermined. They cannot accommodate the development of incommensurable concepts in the course of scientific advance. In 1965, Feyerabend attempted to clarify his notion, claiming that two theories are incommensurable when their meanings of the main descriptive terms depend on mutually inconsistent principles. He also claimed that two theories are incommensurable if the new theory entails that all the concepts of the preceding theory have zero extension, or if it introduces rules that change the system or of classes itself. On this account, in order for there to be incommensurability, the situation must be rigged in such a way that the conditions of concept formation in one theory forbid the formation of the basic concept of the other. Still later, he claimed that with the term incommensurability, he always meant deductive disjointedness and nothing else. These subsequent formulations were all intended to capture the same idea. Feyerabend's route to incommensurability. Although Feyerabend first used the term incommensurable to describe successive scientific theories, in 1962 he had been developing his conception of incommensurability for about a decade prior to meeting Kuhn in the late 1950s. According to Feyerabend, he first discussed his notion of incommensurable concepts with the Kraft Circle from 1949 to 51 while working towards his doctoral thesis on protocol statements. The Kraft Circle was a student group named after Feyerabend's PhD supervisor, Victor Kraft, which was modeled after the Vienna Circle, of which Kraft had been a member. Prominent guests such as Elizabeth Anscombe and Ludwig Wittgenstein attended some meetings. Feyerabend traced the origins of the conception of incommensurability to those ideas as represented by Thesis I in an attempt to a realistic interpretation of experience, which is considered a condensed version of his 1951 doctoral thesis. In 1958, Feyerabend criticized two conceptions of meaning. He argued against the logical positivist idea that the meaning of an observational term is determined by immediate experiences, as well as Wittgenstein's idea that the meaning of an observational term is determined by its use. Instead, Feyerabend argued that the meaning of a term, even an observational term, is determined by its theoretical context, or more precisely, by the theoretical principles that govern its correct use according to our best theories. On the basis of such a conception, Feyerabend developed Thesis I, according to which the interpretation of observation language is determined by the theories that we use to explain what we observe, and it changes as soon as those theories change. Feyerabend proceeded to argue that when older theories are replaced, the meanings of the observational terms used to test those theories change. Just as in 1962, the result is incommensurability, the idea that successive scientific theories are conceptually incompatible and consequently logically disjoint due to differences in the meaning of the observational statements used to test them. Feyerabend's Thesis I is thus an earlier version of the incommensurability thesis. In 1958, with the notion of incommensurability, Feyerabend challenged an implicit conceptual conservatism and logical positivism, the assumption that theoretical terms derive their meaning solely through their connection with experience, and that experience itself is a stable or unchanging foundation on which theoretical meaning can be based. instead of such a bottom-up version of the relation of the experiments of theoretical knowledge according to which experience determines the meanings of our theoretical terms. Feyerabend argued for a top-down version according to which our best theories determine the meaning that we attach to our experiences. According to Feyerabend, experiences cannot be taken for granted as some kind of fixed neutral basis for comparing theories. Rather, it takes on its particular character in light of the theories we bring to it. At the time Feyerabend was developing these ideas, he was working very closely with Karl Popper. There has been much controversy concerning Feyerabend's evolving relationship to Popper, especially given its tumultuous trajectory, the revisions Feyerabend made concerning his debt to Popper, and the reprints of his original paper, informal accusations of plagiarism by Popperians, and Feyerabend's subsequent increasingly vocal denials of his debts to Popper. It has, however, always been clear that Feyerabend developed his ideas on incommensurability while working as a vocal proponent of Karl Popper's critical rationalist philosophy, and that there are many different interpretations of the relationship between their ideas. Bashir, 2015, recently emphasizes just how Popperian Feyerabend's philosophy was at the time, and cast Feyerabend's idea on the incommensurability as a positive extension of many of Popper's views. Oberheim, in 2006, argues that the incommensurability is exactly the point at which Feyerabend breaks the Popperian framework. Many, including Popper, seem to interpret Feyerabend's conception of incommensurability as a rather misguided development or even misunderstanding of Karl Popper's view, which Feyerabend often repeated, sometimes seemingly as if it were his own. In any case, incommensurability marked the point after which Feyerabend and Popper's philosophies dramatically part ways, as they lead to very different conceptions of progress. Feyerabend's route to the idea of incommensurability of scientific theories was heavily influenced by a number of prominent individuals who had been discussing a wide range of related topics. An investigation of the sources of these ideas reveals some of the founding father of the notion of incommensurability in the contemporary history and philosophy of science. Okay, Mr. Boston, God bless. Thanks for tuning in. In the Saturday night Gear and Review, Church of Entropy. Progress Through Meaning Change, Pierre Duhem. Feyerabend drew heavily from Duhem's The Aim of Structure of Physical Theory, 1906, in his development of the notion of incommensurability of scientific theories. Many of the main points Feyerabend emphasized by calling scientific theories incommensurable had been developed already by Duhem, who had argued that logic is insufficient for determining the outcome of theoretical disputes in the natural sciences, and who documented the difficulties historians have in understanding and development of the natural sciences due to meaning change. Duhem also already highlighted the communication difficulties between proponents of competing scientific theories because of the differences in meanings. For example, Duhem claimed that what a physicist states as the result of an experiment is not simply the recital of some observed fact, rather it is an interpretation of those facts on the basis of the theories the scientist regards as true. It follows, according to Duhem, that in order to understand the meaning that scientists ascribe to their own statements, it is necessary to understand the theories that they use in order to interpret what they observe. Thus, Duhem had stated an early version of Feyerabend's incommensurability thesis. Moreover, Duhem explicitly limited his discussion to non-instantial physical theories as opposed to mere experimental laws. This is very similar to the criteria that marks the most significant differences between Kuhn and Feyerabend's development of the idea of incommensurability, and that also delimits Einstein's use of incommensurable when describing the problems of theory comparison. After explaining the meaning of a term depends on the theory to which it belongs, and that a consequence of theoretical advance is meaning change, Duhem continued, if the theories admitted by the physicist are those we accept, and if we agree to follow the same rules in the interpretation of the same phenomenon, we speak the same language and can understand each other. But that is not always the case. It is not so when we discuss the experiments of a physicist who does not belong to our school, and is especially not so when we discuss the experiments of a physicist separated from us by 50 years, a century, or 2 centuries. Duhem continued how many scientific discussions there are in which each of the contenders claims to have crushed his adversary under the overwhelming testimony of the facts. How many propositions are regarded as monstrous errors in the writings of those who have preceded us? We should perhaps commemorate them as great troops if we really wish to inquire into the theories which gave their propositions their true meaning. These passages make the same points that both Feyerabend and Kuhn made with their claims about incommensurability of scientific theories because older ideas are misunderstood as a result of taking them out of their theoretical context. Proponents of incommensurable scientific theories misunderstand each other, both claiming to have the facts on their side. Kuhn and Feyerabend both claim that in such a situation, each empirical argument can become circular. The square root of 2 and complementarity, Niels Bohr. In his autobiography, Feyerabend acknowledges Niels Bohr's direct influence on the development of his notion of incommensurability in the 1950s. Feyerabend recalled a conversation in which Bohr had talked about the discovery that the square root of 2 cannot be an integer or a fraction. According to Feyerabend, Bohr presented the event as having led to the extension of a concept of number that retained some properties of integers and fractions, but changed others, and claimed the transition from classical to quantum mechanics was carried out in accordance with precisely this principle. Feyerabend also used the notion of incommensurability in a publication on Bohr's complementarity thesis, where Feyerabend argued that Bohr's complementarity thesis is an example of an unjustified conceptual conservatism, taking issue with Bohr's contention that all quantum mechanical evidence will always necessarily be expressed in classical terms. He presented Bohr's defense of the principle of complementarity as based on the conviction that every experience must necessarily make its appearance within the frame of our customary points of view, which is currently that of classical physics. However, according to Feyerabend, even though classical concepts have been successful in the past, and even though at the moment it may be difficult or even impossible for us to imagine how to replace them, it does not follow that classical framework could not one day be superseded by an incommensurable rival. Consequently, it does not follow that all of our future microscopic theories will have to take the notion of complementary as fundamental. Instead, according to Feyerabend, a theory may be found whose conceptual apparatus, when applied to the domain of validity of classical physics, would be just as comprehensive and useful as the classical apparatus without coinciding with it. He claimed that such a situation is by no means uncommon. This is clearly an earlier version of his incommensurability thesis on Feyerabend's fallibilist view of empirical knowledge. No element of our knowledge can be held to be necessary or absolutely certain. In our search for satisfactory explanations, we are at liberty to change any parts of our existing knowledge, however fundamental they may seem, including the concepts of classical physics. Kant on wheels and universal theories, Albert Einstein. Albert Einstein used the term incommensurable to apply specifically to difficulty selecting and evaluating specific theories before Kuhn and Feyerabend, and there are strong reasons to believe that Feyerabend's development of incommensurability was directly inspired by Einstein's use of the term. In his autobiographical notes, 1949, Einstein attempted to explain that assessing the relative merits of a universal physical theories involves making difficult judgments about their naturalness. That requires making judgments based on the reciprocal weighing of incommensurable qualities. The second point of view is not concerned with the relation to the material observation, but with the premises of the theory itself, with what may briefly but vaguely be characterized as the naturalist or logical simplicity of the premises of the basic concepts and the relationship between these which are taken as a basis. This point of view, an exact formulation of which meets with great difficulties, has played an important role in the selection and evaluations of theories since time immemorial. The problem here is not simply one of a kind of enumeration of the logically independent premises, if anything like this were at all unequivocally possible, but that of a kind of reciprocal weighing of incommensurable qualities. There are good reasons to believe that these admittedly cryptic remarks directly inspired Feyerabend's use of the development of the idea of incommensurability, although Feyerabend did not cite from Einstein in 1962, he does quote from Bohr's paper in the very same edited volume. Moreover, there are striking similarities between Feyerabend and Einstein's use of the term. First, both make a distinction between universal theories and theories that do not apply to the totality of all physical appearances, and then use this distinction to limit the application of incommensurability in the same way. The problem of weighing incommensurable qualities in selecting and evaluating theories is explicitly only meant to apply to such universal physical theories and not just any pair of scientific theories. Second, Einstein's theoretical attitude is explicitly a form of neo-Kantianism, very much like that of Feyerabend and Kuhn's. According to Einstein, his theoretical attitude is distinct from that of Kant only by the fact that we do not conceive of the categories as unalterable, conditioned by the nature of understanding, but as in the logical sense, free conventions. They appear to be a priori only insofar as thinking without the positing of categories and of the concepts in general would be impossible as in breathing in a vacuum. Thus, in the same basic perspective that both Kuhn and Feyerabend delineated when they developed their ideas of incommensurability. For example, Kuhn says, I go around explaining my own position, saying I'm a Kantian with movable categories, an idea developed in detail by Hoyningen and Kuhn. As per Feyerabend, he set out such a Kant on wheels approach, to use Peter Lipton's apt expression at the beginning of explanation, reduction, and empiricism. Feyerabend overtly adopted such a neo-Kantian metaphysical perspective with changing categories in order to pursue the question, if universal theories determine all of our experiences of the world, how can experiences be used to test such theories? Third, the main example Feyerabend used to illustrate that and how incommensurable theories can indeed be compared on the basis of a crucial experiment was Einstein's quantitative prediction and Perrin's subsequent confirmation of Brownian motion, which served as a crucial experiment between classical and statistical thermodynamics, one of only 3 examples of incommensurable scientific theories in Feyerabend. Feyerabend argued that although Brownian motion was already a well-known phenomenon, it became evidence for statistical thermodynamics and against classical thermodynamics only after the development of the kinetic theory, which was needed to interpret it as such. Even though there was a crucial experiment between these 2 universal theories, the theories have no common measure, as the observation of Brownian motion that confirms statistical thermodynamics were not couched in neutral observational language. The observation only became evident after they were interpreted according to statistical theory. Einstein discussed exactly this episode at length in his autobiographical notes, where he used the term incommensurable to apply to difficulties in judging the merits of universal physical theories. Fourth, later Feyerabend often defended his view that there is no fixed scientific method by citing Einstein. The external conditions which are set for the scientist by the facts of experience do not permit him to let himself be too much restricted in the construction of a conceptual world by the adherence to an epistemological system. He therefore must appear to the systematic epistemologist as a type of unscrupulous opportunist. Although Feyerabend's development of the idea of incommensurability of scientific theories was received by the philosophical and scientific communities as propagating radical, irrational ideas about science, he was actually trying to develop something he found in Einstein. In the preface to the German edition of Against Method, Feyerabend wrote, I want to emphasize yet again that the views in this book are not new. For physicists like Mach, Boltzmann, Einstein, and Bohr, they were a triviality. But the ideas of these great thinkers have been distorted by the positivist philosophers beyond recognition. The mental and the material. Feyerabend and Kuhn explicitly drew from Wolfgang Kohler's work in Gestalt psychology in the development of his notion of incommensurability. Moreover, Kohler had already applied the notion of incommensurability to scientific theories. Kohler's use applies to different areas within natural science, not to successive scientific theories, such as in early Kuhn. Kohler's use of the term incommensurable to describe the relationship between the concepts of psychology and physics was the main source of Feyerabend's development of the idea of incommensurability. Feyerabend's discussion of incommensurability in the formation of the mind-body problem derives directly from Kohler's claim. However, Feyerabend's Wittgensteinian strategy for overcoming the incommensurability in the dissolution of philosophical conundrums is not Kohler's. Feyerabend suggested that the insolubility is due to the unwillingness of philosophers of different persuasions to change the deeply entrenched meanings of their own terms, and that in the case the mental should be reinterpreted so that is compatible with materialism. Feyerabend's later notion of incommensurability. While Feyerabend's notion of incommensurability did not significantly change throughout his earlier writings in the philosophy of science and his later more general philosophy, Feyerabend extended the application of the term beyond universal scientific theories. For example, he used it to characterize the transition from Greek archaic aggregate worldview of Homer to the substance worldview of pre-Socratics, and therefore, in a very broad sense, discussing incommensurability frameworks of thought and action, incommensurability in the domain of perceptions, incommensurability discoveries and attitudes, and incommensurable paradigms, where such incommensurability involves the suspension of some of the universal principles of the received view. Feyerabend characterized his wider notion of incommensurability as a historical anthropological thesis, but also applied it to different stages of the development of thought and perception in the individual. He also further developed his notion of incommensurability, claiming that it involved major conceptual changes of both overt and covert classifications, so that incommensurability is difficult to explicitly define and can only be shown. Still later, Feyerabend argued that potentially every culture is all cultures, apparently retracting a wider cultural notion of incommensurability. A comparison to Kuhn and Feyerabend on incommensurability. Initially, Feyerabend had a more concrete characterization of the nature and origins of incommensurability than Kuhn. On Feyerabend's view, because the nature of objects depends on the most advanced theories about them, and because the meaning of observation statements depends on the nature of those objects, the interpretation of observational language is determined by theories we use to explain what we observe. Kuhn, by contrast, was initially much less sure about the exact meaning of his notion of incommensurability, especially regarding world change, which he saw as the most fundamental aspect of incommensurability. Kuhn frankly confessed to have been at a loss. In a sense, I am unable to explicate further the proponents of competing paradigms practice their trades in different worlds. He suggested that we must learn to make sense of statements that at least resemble these, and then spend a great deal of effort attempting to do so. Furthermore, Feyerabend's concept of incommensurability of scientific theories was much more restricted than Kuhn's. For Kuhn's, incommensurability had three prima facie heterogeneous domains, holistically bound: a change of problems and standards, a change of concepts used to state and solve them, and a change of worldviews in which they arise. Feyerabend's focus, on the other hand, was initially exclusively on concepts occurring in universal or fundamental theories, together with their ontological implications. Ironically, however, in developments after 1962, both authors move in the opposite direction. Kuhn gradually eliminated everything from his notion of incommensurability that does not concern scientific concepts and ended more or less where Feyerabend began. Feyerabend, by contrast, increasingly emphasized aspects of perceptual change and also changes to the set of legitimate problems a discipline should handle, and his later philosophy emphasizing one of Kuhn's original point, the role of non-binding epistemic values in theory change. With respect to the range of theories that are subject to incommensurability, Feyerabend's concept is again much more restricted than Kuhn's. For Feyerabend, only universal, fundamental, non-instantial theories that are interpreted realistically can be incommensurable. Feyerabend was interested in fundamental universal theories that apply to everything because he believed that only such comprehensive structures of thought have ontological implications that are capable of sustaining entire worldviews. He restricted incommensurability to non-instantiated theories, which he distinguished from empirical generalizations on the basis of the differences of their test procedures. Generalizations of the form all A's are B, regardless of whether the A's or B's are observable, are tested by inspecting instances. Due to these restrictions, only universal, fundamental, non-instantial theories. For Feyerabend, incommensurability of scientific theories occurs comparatively rarely. Kuhn includes a wider range of theories as candidates for incommensurability. For him, even smaller episodes like unexpected discoveries might be incommensurable with the earlier tradition. The difference in the range of incommensurability between Kuhn and Feyerabend's version finds its most striking expression in the way they regard the transition from the Ptolemaic to Copernican theories. For Kuhn, the differences between these two theories comprise an exemplary illustration of incommensurability. For Feyerabend, however, because planetary theory lacks the quality of a universality, there is no incommensurability. Furthermore, in his later writing, Kuhn insisted that the version of incommensurability he championed had always been local incommensurability, a notion that restricts conceptual change to a few typically interconnected concepts. Thus, there may be empirical consequences of incommensurable theory pairs that can be immediately compared. Both Kuhn and Feyerabend have often been misread as advancing the view that incommensurability implies incomparability. In response to this misreading, Kuhn repeatedly emphasizes that incommensurability does not imply incomparability. Theory comparison is merely more complicated than imagined by some philosophers of science. In particular, it cannot be made point by point. It is not algorithmic procedure, nor one that requires translation into neutral observational language. Different epistemic values such as universality, accuracy, simplicity, fruitfulness may pull in different directions, allowing for the possibility of rational disagreement. But even a full point-by-point comparison of incommensurable theories is impossible, and even if theory comparison does not have the status of proof, a comparative evaluation of incommensurable theories is still possible and rational in a means ends or instrumental sense. For example, according to Kuhn, it is rational to choose theories that are better problem solvers because they better solve the ends of science. This property of theory choice makes the overall process of science both rational and progressive. With the notion of incommensurability, Kuhn was not so much challenging the rationality of theory choice as trying to make room for the possibility of rational disagreement between proponents of competing paradigms. In fact, according to Kuhn, incommensurability is far from being a threat to the rational evaluation of truth claims that it has frequently seemed. Rather, it's what is needed within a developmental perspective to restore some badly needed bite to the whole notion of cognitive evaluation. It is needed, that is, to defend notions like truth and knowledge from, for example, the express is of postmodernist movements like the strong program. To the extent of the misreading of incommensurability as implying incompatibility is even more dramatic in Feyerabend's case. The far cry from the claiming that incommensurable theories cannot be compared, Feyerabend explicitly and repeatedly argued that incommensurable alternatives actually offer a better means of comparing the merits of theories than the mere development of commensurable alternatives. He illustrated this point with an example of the crucial experiment between incommensurable theories. He argued that even though the central concepts of statistical and classical phenomenological thermodynamics are incommensurable, it is still possible indirectly to stage a crucial experiment between them. This was the centerpiece of Feyerabend's argument for pluralism. The argument turns on the claim that the refutation of classical phenomenological thermodynamics could not have been conducted without the development of statistical thermodynamics, which is an incommensurable alternative. Feyerabend concluded that some observations can only be interpreted as refutations of an existing theory after an incommensurable alternative has been developed with which to interpret them. His unorthodox image of scientific progress is delineated as an increase in a set of incommensurable alternatives, each forcing the others into greater articulation. The source of the misunderstanding concerning incomparability appears to be Feyerabend's one-time suggestion that incommensurable theories may not possess any comparable consequences. However, here Feyerabend was arguing that although the same experimental setup might produce a numerical result that can be used to confirm both of the two incommensurable theories, in order to use the result to confirm a theory, it must be interpreted by that theory. Given that the two incommensurable theories will use qualitatively incompatible concepts to interpret quantitatively identical results, they will interpret the same quantity sentence as different qualitative statements. Feyerabend concluded directly thereafter, hence, there may not exist any possibility of finding a characterization of the observation which are supposed to confirm two incommensurable theories. This does not rule out the possibility of using a neutral observation language to compare the empirical consequences of two incommensurable theories. Yet Feyerabend did not conclude that this inhibits their comparison, but rather that there is no need for a neutral observation language in order to compare them. Feyerabend also mentioned other possibilities of comparing incommensurable theories. Some of these involve making subjective judgments about how to weigh different values that may pull in different directions, methodological incommensurability. Finally, there is one central substantive point of agreement between Kuhn and Feyerabend. Both see incommensurability as precluding the possibility of interpreting scientific development as an approximation to truth or as an increase in verisimilitude. They reject such characterization of scientific progress because they recognize and emphasize that scientific revolutions result in changes in ontology. Such changes are not just refinements of or additions to the older ontology, such that these developments could be seen as cumulative additions to already established theoretical views. Rather, the new ontology replaces its predecessor. Consequently, neither Kuhn nor Feyerabend can correctly be characterized as scientific realists who believe that science makes progress towards the truth. Okay, so I've been going over 5.5 hours, so I'm going to have to put off computer simulations and science till next episode, which I'm not sure if it's probably not going to be next week. It'll probably be 2 weeks. And, I got 2 more. So I have a few related topics, maybe computational philosophy, the Copenhagen interpretation of quantum mechanics, experiment in physics, operationalism, mind-body identity, and then some related topics. And we'll see if I get to all of them. But so, yeah, feeling good about my research. Mr. Boston, appreciate you being active in the chat. Thanks for joining the Discord. So hopefully I have a lot to talk about, a lot to think about. Deep stuff. We went really into detail. Kuhn, Feyerabend, incommensurability, mathematical and scientific explanation, and objectivity. So we've covered the bases now for all of the main aspects of the philosophy of science. There's a ton of issues, and from here, after I cover a few more topics in the philosophy of science in the last two episodes, I will pivot back around to metaphysics. Probably like Mr. Boston, a lot of my listeners, and even myself personally, I'm actually more interested in the metaphysics. But I think the philosophy of science, okay, I did it first, was, yeah, God bless Mr. Boston, was to say, well, what is science? So like metaphysics is going to be, well, what science is not, or at least from the Carnapian, we'll have to look into these deeper things. Like we looked at, talked a lot about causation today for explanation, and such thing like cause and explanation are really properties of metaphysics, not of science. So, to do the due diligence in what is the limits of science, and then from the limits of science, we get into metaphysics, and then you're there to speak about in more grounded, grounding also a metaphysical concept, explanation of spiritual phenomenon. And the metaphysics, I'll get into things like dualism, monism, and concepts of the soul, transmigration of souls, and these various things that are, you'll say, what is the limitations of science, that we could actually talk about these issues in understanding of what's beyond the ability of science to talk about. So have a great week, everybody. Sunday night, Church of Entropy, scheduled for a year in review. So, happy to have guests. I'll be more active with the chat. Hopefully I'll do a week in review on Sunday also, and get back into, read some more essays. And then the next year, continue with my research, and wish everybody the best. And restore America, restore ourselves, restore our communities, restore humanity. Try our best. So you see Duvid's putting out the due diligence, really working hard. Just have my concentration for over 5 hours on this singular issue. Hey, Skyworks, yeah, God bless. Hope to see you Saturday night for year in review also. And preparing this stuff, I read through this multiple times. I outlined it. I'm reading many of the source materials and the literature. So I'm really getting a deep dive into it. And I'm definitely happy if I could provide value to other people also, and you create a community of people interested in this type of research. So God bless. Signing off. It's possible I'll be streaming with Stephen James tomorrow. I think he said last week that he wants to go back to streaming tomorrow. So I'll post that on my social media if that happens. And so God bless.